Namaskar, good morning, and a warm welcome to everyone present here today. It is an absolute honor for us to welcome you all to this international workshop on stratosphere-troposphere interactions and prediction of monsoon weather extremes, that is STIPMEX, at the Indian Institute of Tropical Meteorology, Pune.
Today marks the beginning of a journey where we will dwell into the depth of scientific inquiry, exploring innovative ideas and foster a collaborative spirit that is essential for advancing and understanding in the field of weather and climate.
To start with, we invite our guests to kindly take the seats at the dais. So today, Chief Guest Dr. Rolf Muller is with us. He is Director, Atmospheric Processes and their role in climate, APARC, that is a core project of this World Climate Research Program, WCRP. Please, sir. Guest of honor, Dr. Mark von Hopp, member APARC. Sir. Guest of honor, Dr. Estelle D. Cunning, head World Weather Research Program, WWRP, at the World Meteorological Organization. She is joining us online.
We also request Director R. Krishnan, IITM, to please come to dais, and Dr. Suvarna Fadnavis, convener of the STIPMEX workshop. Thank you everyone for gracing this occasion. We now request to welcome our guest with a bouquet.
Kindly be seated, sir. It is our tradition to invoke blessings and seek divine grace to ensure a successful and inspiring event. We will commence with the ceremonial lighting of the lamp, which symbolizes the dispelling of darkness and the ushering in of knowledge and wisdom. I now like to invite the dignitaries to join us in lighting the lamp.
Thank you all the dignitaries.
Moving ahead, we now invite Dr. R. Krishnan, Director IITM, to kindly deliver the welcome address.
Dear Dr. Ravichandran, Secretary, Ministry of Earth Sciences, Government of India. Dr. Ravichandran is not able to join this meeting in person due to other commitments. He has sent a message, recorded message that will be played. And our today's chief guest, Dr. Rolf Muller, and guests of honor, Dr. Estelle D. Conning and Dr. Mark Van Hobe, Dr. Suvarna Fadnavis, Dr. Partha Mukhopadhyaya, and all the distinguished dignitaries and esteemed participants and many senior scientists. Namaskar and good morning to all of you. It's my great pleasure to welcome all of you to this international workshop on stratosphere-troposphere interactions and prediction of monsoon weather extremes, STIPMEX, that is being held at our institute, the Indian Institute of Tropical Meteorology, or IITM Pune, during 2 to 7 June 2024. Yesterday we had a training workshop, so the formal, we had a training session, and so today formally the workshop is starting. And so the STIPMEX workshop is jointly organized by the Ministry of Earth Sciences, Government of India, IITM Pune, the International Monsoons Project Office, the India Meteorological Department, World Meteorological Organization, the World Climate Research Program, WCRP, the World WWRP, the World Weather Research Program, APARC, that is Atmospheric Processes and their Role in Climate, ACAM, Atmospheric Composition and the Asian Monsoon, WWRP, WGTMR, that is the WWRP Working Group on Tropical Meteorology Research, SSIRC, the Stratospheric Sulfur and its Role in Climate, Jülich Forschungszentrum. So you can clearly see that many major international organizations and even the national institutions in India have come together to put this important event together to discuss about the dynamical, chemical, radiative and convective processes of the atmosphere during the Asian summer monsoon. So when you look at the themes of the STIPMEX workshop, it's very comprehensive and very impressive. So the workshop discusses about the atmospheric composition, chemistry and dynamics in the monsoon, upper troposphere and lower stratosphere, and export of monsoon air to the global stratosphere. Observations in the monsoon region with special focus on recent field campaigns such as the Stratoclim, Eclipse, Phileas Batal. And also it talks about the variability of the monsoon active and break spells and related troposphere and stratospheric processes. Interaction and feedback of the Asian summer monsoon with large-scale atmospheric patterns such as the Brewer-Dobson circulation, the QBO and the ENSO. There's also a session on the response of the Asian summer monsoon to volcanic eruptions, including the recent Hunga Tunga eruption, the large wildfires, anthropogenic emissions and potential stratospheric injection, SAI, which is now WCRP calls it as the climate intervention, which has been launched as a lighthouse activity. The Asian tropopause aerosol layer et al. And its impact on stratospheric aerosols, modeling and observational studies. The mechanisms and physical processes behind extreme weather events. So extreme weather event has also been combined along with the STIPMEX workshop, which is an important plan it's a very good idea, and also understanding the interactions of extreme weather and large-scale atmospheric processes using models and observations, and challenges in forecasting extreme weather events with longer lead time at higher spatio-temporal scales in operational models. So clearly these are all cutting-edge problems and we really understand very little of some of these issues despite all the advances that have taken place. So I'm really very happy that this workshop has put together this fantastic program and bringing both the weather and climate people together to discuss. And there's a lot of interest in the atmospheric chemistry that is being generated in the Indian scientific community. So this workshop is really very timely. And so I extend my very best wishes to all of you for a very productive and stimulating workshop and wish you all a wonderful stay in Pune. I also take this opportunity to sincerely thank all the delegates and participants, especially many of you who have traveled long distance to Pune to attend this very important workshop. Happy to see so many people, friends from abroad and also from India. So I'm really grateful to my colleagues from IITM and all the co-organizers for the great efforts in putting together this fantastic program, for their meticulous planning, coordination, and organizing this large-scale event. If you need any assistance or logistic support, please feel free to contact our colleagues and volunteers at IITM. Thank you all once again, and welcome to IITM Pune. Jai Hind.
Thank you, Dr. Krishnan. We are delighted to hear your inspiring and encouraging words. Your vision and leadership have been instrumental in bringing this event fruition. Before moving further, we request the Director IITM to felicitate our guest with a memento.
Sir.
Thank you, sir.
Ladies and gentlemen, our Honorable Secretary, Ministry of Earth Sciences, Government of India, Dr. M. Ravichandran, has sent his inaugural address through a video message. He could not join us due to some other prior commitments. I now request to play the message from our Secretary.
Guest of honors, Dr. Muller, Director, Atmospheric Processes and their Role in Climate, APRC, International Project Office, Dr. Mark Unko, Member of APRC, Dr. Stella de Koen, Head World Weather Research Program of WMO, Dr. Krishnan, Director, Indian Institute of Tropical Meteorology, IITM, distinguished invitees, delegates, my colleagues at IITM and Ministry of Earth Sciences, ladies and gentlemen. A very good morning to all of you and welcome to IITM Pune. I am extremely sorry that I couldn't be there today due to other pressing tasks here in Delhi. The International Workshop on Stratosphere, Troposphere Interaction and Prediction of Monsoon Weather Extremes, STIPMEX, will address the link between the stratosphere and troposphere and its impact on predicting extreme monsoon weather events. Recent studies have highlighted that the stratospheric processes are important for improving the predictability of the troposphere, especially during the monsoon season. Despite this, the complexities of the underlying mechanisms of stratosphere-troposphere coupling processes are difficult to incorporate in the numerical model. Furthermore, the role of stratospheric chemistry cannot be overlooked as it regulates the levels and distribution of key climate forcing agents. Stratospheric ozone depletion and subsequent recovery have been identified as drivers of significant climate changes in the troposphere. Additionally, the effects of stratospheric aerosol and water vapor on radiative forcing must also be considered, given their potential contribution to global climate change. The forecasting of high impact weather events, such as tropical cyclones, has seen significant advancements in the recent decades. These improvements can be attributed to the enhancement of the knowledge, observation data, particularly over oceanic regions, as well as improvements in model physics and resolutions. These factors have collectively contributed to the improvement of accuracy of weather forecasting. Despite these advancements, frequency of extreme weather events is on the rise globally. This trend underscores the need for even more precise forecast regarding the timing, the location, and the intensity of such events, with a focus on providing longer peak times. However, achieving this level of accuracy remains a challenge for the numerical weather prediction communities. As weather extreme events become more frequent and severe, the pressure is on to enhance forecasting capabilities to meet the growing demands of accurate and timely predictions. Addressing this challenge is paramount in order to better protect communities and minimize the impact of these high impact weather events. Challenges often bring about opportunities for innovation. In the case of forecasting extreme weather events, advancements in technology and techniques offer a promising solution. By enhancing global convection models and incorporating stochastic approaches and fusion of AML techniques, the accuracy of extreme weather event forecast can be significantly improved. I urge scientists, delegates, especially younger researchers and students, to tap into the wealth of the observational and pre-campaign data to develop AML models and downscaling techniques. These tools can aid in predicting extreme events more effectively, ultimately saving lives and property, a critical need in today's world. This workshop sessions focusing on stratospheric chemistry and dynamics as well as monsoon extremes. Experts will delve into the complexities of stratosphere-troposphere coupling processes and the challenges of predicting extreme monsoon weather and shed light on future pathways. Considering the importance of STIPMEX, organizations such as WMO, WWRP, WCRP, APARC, Force Concentrum, Zurich, Germany, and Ministry of Earth Sciences have generously supported and facilitated this workshop. The presence of a diverse group of international scientists underscores the significance of the topics to be discussed during the workshop. I hope for a fruitful and successful exchange of ideas and knowledge on these important topics and urge to come up with a recommendation for further advancements in these areas. I extend my best wishes for the success of the workshop, STIPMEX. Thank you.
Thank you very much, sir, for your encouraging address, extending cordial wishes and support to STIPMEX. Ladies and gentlemen, we feel honored to be joined by Dr. Rolf Muller as the chief guest of the program. It is my privilege to briefly introduce him to our audience. Dr. Rolf Muller is highly accomplished physicist and chemist with extensive experience in atmospheric sciences. Dr. Rolf Muller has held several prominent positions, including Deputy Director of Institute of Energy and Climate Research at Forschungszentrum Jülich since 2012 and has been there since 1995 as senior scientist. Adding to this, his multidimensional activities includes contribution to WMO ozone assessments and IPCC reports, servicing an advisory board like European Space Agency, reviewing scientific journals and funding agencies, and teaching at the Institute of Energy and Climate Research at the University of Wuppertal, Germany. With this, I invite Chief Guest Dr. Rolf Muller to kindly address the gathering. Sir, you may please.
Yeah, hello everybody. Thank you for the nice words, for the nice introduction. I remember something about 7 years ago, I was exactly in this hall here, and Savannah Fatnavis told me that this might be a venture of a big workshop, and it is extremely encouraging. It's very positive to see this is happening, and it's great to see you all here. So welcome to this workshop. I think it will be a very, very successful endeavor. One thing I would like to emphasize, what is very good, is that there was an initiative to encourage young people, early career scientists, to participate in the workshop and to take on the work, see what others are doing. And I think that this is an important part of this workshop, is to bring the younger generation closer to the scientific question. And as Dr. Krishna has pointed out, there are many. It's a lot of things that we still don't know. And the deeper you look, the more delicate the problems get, and it is astonishing. The general understanding is there, but if you want to answer specific questions, there's a lot to be learned. This is one reason why I'm here. I think, yes, presenting our own activities, presenting the aircraft campaigns would be important, and interacting and seeing your views on the recent results, or very recent results in some cases. On the other hand, it's also, certainly for me personally, and I'm sure I'm speaking for many of us here, it's also to learn the experience, especially about what is known about the monsoon, about extreme events. And this will be a very valuable point, very valuable aspect for many of us, and certainly for me personally. Certainly the monsoon area is an area where the stratosphere, or higher altitudes, and the lower altitudes are strongly coupled. You have these convective events moving things upward, and then even in the monsoon, in the higher altitudes, that is something that we are focusing on our research, at least so far. They have this big anticyclone where the air is slowly rising, circulating, and getting to a higher and higher altitude, and we'll see some results over this week on what people find if they do actual measurements in detail. And there aren't too many actual measurements, and so far I think IITM and their collaborators are a very successful group of people sustaining balloon measurements in the long run in India and in the Indian region to help and address, first of all, the issues itself, and of course the interannual variability, because you do an aircraft campaign that's for one particular year, and the monsoon will be, as you know much better than we do, is much different from year to year, and this variability is also something that we're interested in, and that helps us to learn about the processes, and this is eventually what we're interested in, the processes regulating the chemistry and the transport in this important region. And for us, as I said, the importance is to have a very, nowhere else in the world is it's that strong and that pronounced a combination of local, lower altitude pollution and other impact, chemical impact, and transport to high altitudes. And from the monsoon, of course, it's confined in the monsoon circulation, but it's not staying there forever. It's distributed, especially in the northern hemisphere, but altogether globally. So the monsoon, in that sense, is a global aspect, and it's globally interesting, and this is why a lot of important institutions are supporting this work, and this is why a lot of people are focusing on this area. And of course, when I talk about the link between the lower altitudes and the higher altitudes, the stratosphere, it's where the ozone layer is located. It's not only influenced by the monsoon, but by other processes as well, chemical, dynamical aspects. And as was mentioned before, the WMO ozone assessments, of course, are an important part of the assessment of the ozone layer. So with that, I wish us all a very successful workshop, lots of interactions, and as I said, personally, I'm very interested and eager to learn more about aspects of the monsoon from all of you here that I don't know so well at this point in time. So thanks very much, and thanks for being here, and thanks for inviting me, and I hope you have a nice and important workshop.
Thank you, Dr. Miller, once again to be here with us and for sharing your valuable knowledge and insights. Moving forward, we are privileged to have Dr. Mark von Hobb as our guest of honor. Dr. Hobb is a distinguished environmental chemist with a strong academic and research background. He earned his PhD from the Max Planck Institute for Chemistry in 2000. Since 2001, he has been a researcher at Forschungszentrum Jülich, developing in situ trace gas sensors and leading significant projects like European Union's Reconcile project from 2009 to 2013. His work has focused on halogen chemistry in ozone depletion and sulfur compounds, notably the carbonyl sulfide. He developed the first cavity-enhanced spectrometer for carbonyl sulfide measurement and co-authored a key review on stratospheric aerosols. He has participated in major airborne campaigns such as that in Stratoclim 2017 and Phileas 2023, and he is developing lightweight instruments for greenhouse gas measurements and pollutants. Dr. Mark is an associate editor for Copernicus journals ACP and AMT, and a co-author and reviewer for WMO ozone assessments, and a member of various APARC activities. He also reviews research proposals for NASA, NSF, ERC, and many other organizations. With this brief introduction, I invite Dr. Hobb to kindly address this gathering. Thank you.
Well, thank you for that kind introduction. And I would also like to welcome you all here to the STIPMEX workshop on behalf of my home institute, Research Center Jülich, as well as the APARC Scientific Steering Group, and also as a member of the STIPMEX Scientific Steering Committee. I'm certainly very happy and very proud and honored to be here as a guest and to be able to say a few words at this inauguration ceremony, which I think is very nice with the lighting of the lamp, and it's certainly a very nice cultural experience here. Let me start with a few words of gratitude to all the institutions and individuals without whom this event would not have been possible. Explicitly, I think I have to thank the Indian Institute of Tropical Meteorology here in Pune and also the Indian Ministry of Earth Sciences. Both institutions generally host, organize, support, and sponsor this event. And the leadership of these institutions, Dr. Krishnan, the scientists, the staff from these organizations, they all put a tremendous amount of planning and work into this, and I think we have to really thank all of them for what they have done. And a special mention to Silvana Fatnavis, with whom we in Jülich have been collaborating for more than 10 years now, I think, and she expressed the idea and the wish to have a big conference on Asian monsoon science here in Pune already many years ago, and it's been a while and it's taken long, but now finally we're gathered here in this place, and I think this will be a great conference and a wonderful experience for all of us. So really thank you, Silvana, for making this possible and for pushing so hard over all these years with COVID and all the different things and obstacles, and finally making this happen. Well, the interest in the transport of air from the ground to the upper troposphere and the stratosphere has certainly grown a lot over the past 2 decades, and it's now clearer than ever what Bill Randall wrote in his famous science paper back in 2010, that the Asian monsoon is the main gateway of gases and material released by human activities into the global stratosphere. And when I look back at the last 10, 15, 20 years of research and the many important results and publications we have seen, I'm particularly pleased to see the growing involvement of institutions and scientists from Asia and from India in particular in research of the tropopause region here. And you should, by all means, play a leading role in these efforts, because the Asian monsoon, it comes here right at your home, at your place every year, and this is where it all happens. So it should really be you who should be highly involved and lead this research. And when I, as a member of the organizing committee, started reading all the abstracts in February, it was fantastic to see all the nice abstracts from the Indian community, especially many of them from researchers in the early or mid-career stages. So you really do a lot of good work, and I think we see a lot of good talks from IITM and other institutions here at this workshop in the coming days. So that's very great to see. And yeah, I really look forward to see these presentations, to view the posters also, and to talk to you about your research. So it would be nice to talk to as many of you as possible during the coming few days. And I certainly hope that this workshop will be a real landmark and makes this important research by you and by the Indian and Asian scientists much more visible. And in this context, let me remind you that we have a special issue coming up in the journal Atmospheric Chemistry and Physics, the Copernicus journal. So everyone who presents here, who has a poster, is invited to write that up as a paper and submit it to this special issue. And there will be support for the submission fees and things. So that shouldn't be an obstacle to you writing a nice paper for this special issue. So hopefully we'll see lots of the results that will be presented here also in the form of peer-reviewed papers later on. One thing that I noticed about the abstracts and the scientific studies when I read them is that the majority of them is actually on analysis of satellite observations and also global modeling studies predicting the monsoon, predicting the stratosphere and the interaction with climate. And this is great and important, of course, because it's really these global atmospheric models that help us to put everything into context and to make these predictions into the future in a world of changing climate. And such predictions are obviously of vital importance to everyone on the planet, every human being and all the creatures. And maybe it's even more important to people here in these regions where climate change causes extremes that may be a bit more threatening even than in the parts of the world where I come from, where it's maybe not as extreme as it is here. So that's all the more reason for you to be involved and engaged in this research. And it's certainly not a coincidence, but it was planning that the topic in the focus during the second half of this workshop, the extreme events, that this is coupled to the stratosphere-troposphere interactions because it's all interlinked. And as an observational scientist, you have said that in the introduction, developing instruments, I certainly want to encourage you to not only continue these efforts in developing models and making predictions, but also to consider engaging in more observations. During recent aircraft campaigns like Stratoclim, ACLIP, Phileas, we have seen how valuable these in situ measurements, measuring the air right where we find it in the tropopause regions, are to fully understand the fine details of transport and chemistry in the upper atmosphere during the Asian monsoon. But these snapshots, they look at rather small regions for only short time periods, and they're certainly not enough. And more regular observations, for example, from small balloons, could be extremely valuable for model development and validation. And even observations at the ground, there are too few of them, and they're very important because we often have the problem when we look at the data up higher and in models that we measure or model the air in the lower stratosphere and get huge uncertainties in the composition because there's too little information on what is actually coming up from the ground. So to make measurements of the lower levels is also important to understand what happens at the upper levels. And I will explain a little more on that tomorrow in my presentation and make a pledge to go out there and make more ground measurements of trace gases, long-lived trace gases. And with that, I stop here my welcome speech and really look forward to a great conference. And thank you all for being here, and I look forward to and be inspired by the presentations and by the posters. They're important as well. Thank you very much.
I extend a great thanks to you, sir, for your encouraging address. So now, moving ahead, it's an honor to have with us Dr. Estela de Koning, originally from South Africa, where she worked for South African Weather Service during 1997 and 2016 as chief scientist of the Nowcasting and Very Short Range Forecasting Research Group. She joined the World Meteorological Organization in 2016 and is currently the head of World Weather Research Programming. She obtained her PhD in 2011 from the University of South Africa, which focused on application of meteorological satellite products for short-term forecasting of convection in Southern Africa. The EUMETSAT Nowcasting satellite application facility software was installed at the South African Weather Service under her leadership and is operationally available for Southern Africa, namely the South African Region Specialized Meteorological Centers website. She is the author and co-author of several national and international peer-reviewed papers, chapters in books, as well as WMO publications, such as WWRP's Seamless Predictions of Earth System from Minutes to Months in 2015, and Guidelines for Nowcasting Technique 2017, and Guidelines for Satellite-Based Nowcasting in Africa in 2023. With this, I request ma'am to join us online.
Good morning and a very warm welcome to all of you, distinguished guests, honorable guests, and everybody in the audience that contributes to this wonderful event. Thank you for this opportunity to say a few words of welcome on behalf of the World Weather Research Program at this international workshop on stratosphere-troposphere interactions and the prediction of monsoon weather extremes. The World Weather Research Program of the WMO plays a crucial role to advance our understanding of weather phenomena, including the prediction of weather extremes and their impacts, such as monsoons, as well as the interactions in the entire Earth system, thus including the stratosphere and troposphere interactions. WWRP also supports the involvement of early career scientists in all our activities. So I'd like to echo the comments of previous speakers that it is a really good effort to see that a lot of early and mid-career scientists are involved in this week's program. Streams and interactions between all the components of the Earth system are integrated into broader efforts to monitor and understand the entire Earth system. The WWRP and the WCRP both support the Monsoons Office in Pune as an example of our collaboration. Another key aspect of the World Weather Research Program's work is the research related to the development and evaluation of numerical weather prediction models, through which we aim to understand these underlying processes that drive our extreme weather events. Through collaborative research projects, the WWRP facilitates the exchange of model development, the techniques that are best, the best practices, the World Climate Research Program, and the Global Atmosphere Watch. This collaboration ensures that research findings and observational data related to many topics, including weather extremes and interactions between all the components of the Earth system, are integrated into broader efforts to monitor and understand the entire Earth system. The WWRP and the WCRP both support the Monsoons Office in Pune as an example of our collaboration. Another key aspect of the World Weather Research Program's work is the research related to the development and evaluation of numerical weather prediction models, through which we aim to understand these underlying processes that drive our extreme weather events. Through collaborative research projects, the WWRP facilitates the exchange of model development, the techniques that are best, the best practices amongst meteorological institutes worldwide. The WWRP also, and lastly, provides support to training and capacity development activities to meteorological professionals, researchers, and specifically scientists from developing countries. By enhancing the technical skill and the knowledge of practitioners in the field of weather prediction and atmospheric science, we contribute to the improvement of global capacity to predict weather extremes and the related understanding of Earth system interactions. The WWRP has several new projects in our new implementation plan, and one of these focuses on tropical cyclones, but we also have 7 groups of experts looking at various aspects of research. One of these is the Tropical Meteorological Research Working Group that was also mentioned before, and this group has close links to monsoon research. IITM has kindly offered to host the International Monsoons Workshop in March 2025, and we are working closely with them in the coordination of this event. Prediction and prevention, or early warnings of extreme events, are very important parts of the United Nations initiative called Early Warnings for All, with a specific aim to provide access to early warning systems for all people, specifically those in developing and least developed countries and small island developing states. To the most vulnerable of people, these warnings are life-changing. We need to have not only knowledge, but also accurate prediction of extreme events with the needed tools, the needed data, the models to enable Met services to issue timely warnings of the associated impact-based forecasts. This is done through Pillars 1 and 2 of the Early Warnings for All initiative. But having wonderful knowledge and wonderful tools don't mean anything if this does not land in the hands of people making the decisions. So Pillars 3 and 4 of the United Nations Early Warnings for All initiative focus on communication of warnings and the extreme events, and then enable emergency response agencies to coordinate rescue operations and provide assistance to affected communities more effectively. Real-time weather forecasts of extreme events allow for better preparedness and response to disasters, reducing the loss of life and the loss of property and damage to our valuable possessions. We would like to thank IITM for hosting this international workshop on stratosphere-troposphere interactions and the prediction of monsoon weather extremes, which clearly addresses many of the global issues, such as the Early Warnings for All initiative of WMO, but also many of the aspects that are important to the WWRP. I'm convinced that there will be many useful outcomes and discussions during this week, and I wish you a very fruitful conference. Thank you so much.
Thank you, Dr. Estel, for your insightful address. Ladies and gentlemen, we are proud to inform you that this workshop has received an overwhelming response from over 300 plus abstracts from national and international participants. The abstract proceedings are a testament to the hard work and dedication of all the participants and contributors. It is time for the official release of this abstract proceedings, which encapsulate the essence of the research and discussions that would be taking place over the course of this event. To mark this important occasion, I would like to request our chief guest, Dr. Rolf Müller, to kindly release the abstract proceedings of this workshop. Sir.
Thank you, Dr. Muller, for releasing the abstract proceeding. Now I request Dr. Suvarna Fadnavis, Senior Scientist IITM and Convener STIPMEX, to please come forward and propose a vote of thanks. Madam, please.
Good morning to all. Honorable Secretary, Ministry of Earth Sciences, Dr. M. Ravichandran, our Chief Guest, Dr. Rolf Müller, Director of Atmospheric Processes and Their Role in Climate, APAC, Guest of Honor, Dr. Estel D. Koning, Head, World Weather Research Program, WWRP, Guest of Honor, Dr. Mark von Hope, Member, APAC, SSG, Respected Dr. R. Krishnan, Director of IITM, all delegates, and my dear colleagues. It is a great honor and privilege for me to extend a very hearty vote of thanks to you all on this occasion of International Workshop on Stratosphere-Troposphere Interactions and Prediction of Monsoon Weather Extremes, STIPMEX. I must express wholehearted thanks to our Honorable Secretary, MOES, Dr. M. Ravichandran, who has constantly supported and motivated us for research excellence and collaborations. Sir, your encouragement has been invaluable for STIPMEX. It is an immense pleasure to thank Chief Guest Dr. Rolf Müller, Director APAC, for accepting our invitation. Your participation has added a distinct charm to this event and made it more special. We are extremely grateful to our guest of honor, Dr. Estel D. Koning, Head, WWRP, for joining us online and for addressing us. I would like to extend heartfelt thanks to our guest of honor, Mark von Hope, Member APAC, for an invaluable support from APAC. There have been many facets of this event where his contribution helped smooth execution of STIPMEX. Thank you, Mark. I would like to take this opportunity to express my sincere gratitude to our respected and beloved Director, Dr. R. Krishnan, for his continued guidance and encouragement to make this workshop feasible on this large scale with global visibility. On behalf of entire organizing committee, I convey hearty thanks to honorable delegates, and each one of you for gracing us with your valuable presence. Thanks to journal chief in editor, atmospheric chemistry and physics, who agreed for special issue on the proceedings of on the paper presented in STIPMEX. I would also like to thank Ministry of Earth Sciences, WWRP, APAC, Forschungszentrum Munich, Germany, who have provided tribal support to delegates of STIPMEX. The support rendered by Dr. Kamaljit Ray, Dr. Shikha Joan, and MOS Program Office in obtaining all necessary approvals and clearances from government for conduct of this workshop is gratefully acknowledged. Finally, I express my sincere thanks to all members of various committees, including reception, hall management, catering, publication, purchase, cultural, accommodation, administration, transport. Thanks to all of you. Your collaborative hard work made this event so special. Thanks to media and press for accepting our invitation. I am sure that we will have very interesting discussions and fruitful collaboration during STIPMEX. Thank you all.
Thank you, Dr. Fadnafis, for your cordial vote of thanks. May I now request our dignitaries to take the reserved seats in the front row. Thank you once again for your presence and support, sir. Your participation is greatly appreciated and adds immense value to our workshop. We now proceed with the next segment of this inaugural program, which will commence with a keynote talk by Dr. Michael Hofner, Karlsruhe Institute of Technology, Germany. Dr. Hofner is a renowned expert in atmospheric trace gases and remote sensing and has made significant contributions in this field. Today, Dr. Hofner would be talking on composition, origin, and fate of the Asian tropopause aerosol layer, a view from the aircraft and satellite by infrared remote sensing. I request Dr. Hofner to kindly deliver your keynote talk. Thank you.
Okay, yeah, thanks a lot. Namaste. Oh. Further down. Let's see. Okay, it's working. Very nice. Okay, yeah, thanks a lot for the invitation, and I will talk a little bit about mainly our measurements and measurements from aircraft, from satellites, about the composition of the Asian tropopause aerosol layer. And just to start with, Jean-Paul is here, and he, let's say, detected for the first time the aerosol layer, and in the upper atmosphere of the Asian troposphere, the Asian monsoon, and after this detection, so the questions were, so what's the composition and the phase of these Atal particles? What is their source? Can they influence perhaps the nucleation of cirrus clouds and have an indirect radiative effect, possibly larger than their direct effect? And what is their fate? Do they enter the lower stratosphere? Do they perhaps influence ozone? And so on. So these are some of the questions I try to tackle, however, I will not solve them, of course. Yeah, so something about measurements, and Mark already mentioned the in situ measurements. I just make another point about remote sounding measurements. They have to go, of course, together, but of course remote sounding is also quite a little bit valuable. And just that you can see what you can see here. So how we do it with one of the instruments, and this is called a limb. These are called limb spectroscopic measurements. What means limb? Limb means we are receiving radiation from the atmospheric layers by looking into these layers from top to bottom, bottom to top, or at once. And then we are looking not at the Earth's surface, but just through the atmosphere down into space. And we receive in the infrared, in the middle infrared, we receive the radiation emitted by all the trace gases and aerosols in these layers. And you can imagine that at these tension points, because at the layer, the tension points, the path through the atmosphere is longest. We are quite sensitive at these layers, and so we can get also height resolved information about the composition of the atmosphere. What about composition? So this is a spectrum, we call it a spectrum in the middle infrared. So this is wave numbers, perhaps people are not so used to wave numbers, so this is about 10 micron. So it's the middle infrared where the atmosphere loses its radiation, mainly through emission in space. So we are about here. You can see many trace gases here. The most important, you know, is CO2, H2O, and ozone. So these are the main emitters in this atmospheric or in this spectral region. But there are also many other emitters there. You can see like you know, H2SO4 particles, SO2, but also, and I will mainly discuss talk here about NH3. So these are these lines here, you can see here. And this is ammonium nitrate. This is this little bit broader feature in this spectral range. Okay, so that's how we do our measurements, and we get this spectrum at each of these altitudes. So then we can analyze through remote remote sensing measurements or the analysis of these spectra, the composition of the atmosphere. We do this with different instruments. So our main instrument is called the Gloria instrument. You can see a limb observer of radiance imaging. And this is an instrument we developed at KIT together with Forschungszentrum Jülich. And it is a good instrument, a Fourier transform spectrometer. So you know, with these new techniques of infrared imaging, so you make just the image of your infrared spectral region, you make an image, so you have a two-dimensional image, and behind each of these pixels, you get all these spectrum through making an interferometer behind the image. So you get all this information about this, trace gases, at each of these pixels. And therefore, and from this you can derive the composition then of the atmosphere you are looking at. Okay, then we have this on board of different aircraft. Here is the Halo aircraft. We are looking here outside. So to the right, outside, we are flying. We are looking again, so we have different views. Just when you look out of the aircraft window, you have a view of the limb. You see the clouds, and you see normal space, and then you look out, and you see here outside, so this is the infrared view, and each of these pixels, you have the spectrum, and then you can derive trace gases, for example, water vapor profiles at each of these positions. And so you get this a long track. You can see here the time, and here the altitude. You get profiles along of your flight, mainly below your flight altitude of the aircraft. So it's just below, and you get profiles, and you can see here you don't get profiles down to the Earth because there are clouds, and perhaps you know in the infrared, especially when you're looking through in limb through the clouds, it's like a black body, so you cannot derive where there are clouds, but you can derive information down to the cloud top about the composition. Okay. Then, yeah, we put this, so these are also, let's say, satellite instruments which did limb sounding of so infrared limb sounding. So very first one was from Jülich, Wuppertal perhaps, I don't know. So Jülich and Wuppertal. And then we got the Envisat satellite from ESA, where we had this MIPAS instrument on, and our Gloria instrument from our institutes have been flown during the Stratoclim campaign, and also most recently in the last year during the Phileas campaign. I will mainly talk also about this, but let's just first go a little bit step back and see that also we need laboratory measurements. So from laboratory measurements we get our information about the spectral features here, and then from the spectral features we need to do quantitative analysis, and you have to model them, and when to detect them. For example, ammonium nitrate. It was not known before. We had to go to the AIDA chamber. It's a big cloud chamber at our institute, and to measure the spectral features that we can compare it with our measurements in the atmosphere, and then to make quantitative analysis of this. Another point is to measure NH3. So ammonia, gaseous ammonia, is very difficult to measure in situ. So it is sticky to the tubes and so on. So we think, or we got the first impression that it is possible to do it with remote sensing, because we have this nice, so that's again the wave number scales, about 10 micron, and we get this when we looked during Stratoclim, we saw these features here, spectral lines, they are called. And so these are simulations without, and the measurements here. And you can clearly see big of these, the large features, and this was clear and really the first proof that NH3 is up there at 10, 12 kilometers in the atmosphere. So this was quite, let's say, nice measurement. So and these were then from the Stratoclim campaign, our results. So here, we flew, this was mainly our flight over India, where we then derived the HNO3, the NH3. So this was this ammonia, gaseous ammonia, and the particles, the ammonium nitrate particle spectral signal, and we could derive also the volume density or the mass density at these different altitudes. And here again you can see we measure where there are no clouds. When the clouds start, then it's more difficult to measure. So that's here at these positions there have been clouds, and in between there were calibration measurements. Okay. So in the meantime, we did also an analysis of another flight. Okay, you can say one flight, there is just one, let's say, ammonia there. We did another flight. We did this on 29th, and we measured here over Nepal, looking here to the right, and we could also see, these are the profiles. So this is, let's say, just this land path where you can see where these these profiles were made, and these are the vertical profiles along these observational lines. And you can see here we got up to 1.5 ppb of NH3, which is really a large amount of NH3 at 13 kilometers altitude already in this flight. And you can see there is some distinct layer of NH3, not below, not above, but at these altitudes here. And could show that, it was mainly, mainly an uplift through, strong convection from a region here in the northern part of India where there was a lot of NH3 measured on ground by satellites. And normally you would say, okay, you have convection, and then with convection there is a lot of water, and NH3 is very soluble, so you will wash it out. So, and that's one of the questions, why isn't it washed out? And I come to this first here. Why is it not washed out? And there are different explanations. So most recent, let's say, explanation from 2018 was that it is in the droplets, and as soon as the droplets freeze, then the NH3 is just by the ice pulled out of the droplet. So this is one explanation, that it's just the droplets which encounter NH3, which are not going down or raining out, but then at some point they freeze and it's driven out of the ice crystal, this NH3. Another paper which was already published in 2002, it was only modeling. They didn't have any measurements at that time in these altitudes, but at least their explanation was that what their model did, that it is due to the NH3 solubility in liquid water, and this is very pH dependent. So and through this dependence, you can lift up the NH3. So it's still the questions. We don't know why it's up there, but there are different explanations. It can be important, just some other papers here, why it may be. So NH3 is of course precursor to the production of ammonium nitrate particles at these altitudes. And now we have seen they are most probably also solid. So we looked in the laboratory and we saw that these are very efficient ice nucleating particles. So mineral dust is very ice nucleating, has a high ice nucleating efficiency, and mineral dust, and then these are even higher, have a higher ice nucleation potential than mineral dust. There were also in the CERN cloud chamber measurements quite recently that nitric acid, sulfuric acid, and ammonia, they form these particles much faster than any of these two compounds. And they also did some simulations and saw this ice production that spread across the mid-latitude northern hemisphere. So that's a modeling activity up to their, let's say, only laboratory measurements. And there are also other, modeling studies of ammonia and nitrate in the upper atmosphere of the tropics. Okay, nice. We had this already. Then let's go to some newer work. We had a STRATOCLIN campaign here. We have these two flights I've just shown. And there we had also a South Track campaign in 2019 with the instrument where we flew here to South America. Now, why do I mention South America here? Because, one source which was often modeled of NH3 brought up is due to biomass burning. We know that biomass burning includes, at least at the ground, or measurements have been made that NH3 is also in biomass burning. And now we want to see how good are models. How good are your models or general global models in capturing this NH3, this ammonia at these high altitudes. So we did comparisons with two CAMS runs. First, a reanalysis run, forecast run. Forecast run is mainly has a newer chemistry, newer parameterization, and a better resolution, horizontal resolution than the reanalysis runs. So you will see comparisons to both runs now. And that's the first one. That's the monsoon cases. So our monsoon case, there is ammonia measurement by Gloria. You can see what I've just shown. There is these high values of the high concentrations of ammonia here at these altitudes, around 10, 12, 14 kilometers. And that's a CAMS reanalysis. At least it gets the, not exactly the position right, but it gets the values right. So the CAMS reanalysis has some values, and the forecast even gets somehow these positions quite right where it is. So somehow this comes, whatever processes it includes, it gets up the NH3 and not all is washed out. And also this other flight here over India, we can see the Gloria measurements of high NH3 at these altitudes. And in the CAMS reanalysis, it's just a little bit there, but it's quite relatively good captured by the forecast, which has a higher horizontal resolution than the reanalysis. So we see, okay, we are happy. Okay, the models, they can simulate the NH3, perhaps for the wrong reason, but at least they simulate NH3 at these altitudes. Then just looking at the biomass burning, case in front of let's say here, Southern America. We saw there was a big biomass burning season in 2019 with a lot of fires in the Amazon region. And we saw this by our measurements with PAN, with our instruments. So PAN is peroxyacetyl nitrate. It's a biomass burning tracer. That were our measurements. Just we flew here, so we measured altitude resolved, the PAN distributions, and this could be really well captured by the CAMS reanalysis and by the CAMS forecast. So this is quite nice that we could measure this large plume coming out of the Amazon region. However, in case of NH3, reanalysis and the forecast, they strongly overestimate, because we could perhaps only have a slight detection of NH3. You can see here it's going up to 100 ppt, and this is going up to 500 ppt here. Only indication for NH3, but there is no NH3 at these altitudes from the biomass burning. So there is a vast difference between the models and the measurements in case of biomass burning bringing up NH3 into the upper troposphere. That's again just another flight, but it is saying us the same. NH3 is overestimated by the model in case of biomass burning. So, okay, models saying it's good in the Amazon or in the monsoon region, but in the Amazon region it totally fails. Okay, so don't always believe in the models. The reasons might be just a short look that the sources are overestimated. That's IASI, this is CAMS. So IASI has not really this, but at least it has this strong indication here in the CAMS model and over the Amazon region. So IASI is a little bit lower values than what is used by the model. Things may also be underestimated. We looked for clouds as things and so on, but yeah, it's not really clear why the models, and it's difficult to explain why the models so strongly overestimate the NH3 in the biomass burning plumes. Okay, then the Phileas campaign. Next campaign was the Phileas campaign, 2023, was already mentioned. There were different topics to look at during the Phileas campaign. One of the topics were how do gas phase and particulate constituents evolve in large-scale eddies, which are shed from the monsoon and the cyclone. And this is, okay, perhaps it's just a view to the North Pole, because then you can see here that's the region of Alaska, where there were a lot of flights, mainly in the last phase of the measurement campaign. And here the region over the Mediterranean, where we had 2 flights over the Mediterranean Sea, where we wanted to look at the western edge of the Asian monsoon, and here we looked at let's say, the eastern outflow from the Asian monsoon into the stratosphere also. Okay, again, these pictures here, time along the flight, altitude, and this was the one flight in the Mediterranean area, and it's already ammonium nitrate. And ammonium nitrate, we had seen from PAN, from other substances, that in this region we got a lot of information. We were nearly in the western part, most westerly part of the Asian monsoon region, and here we saw also traces, but quite clear traces of ammonium nitrate still over the Mediterranean Sea, while ammonia, so this is ammonia here, is nearly depleted, only small patches, one small patch of ammonia. So it's mainly in ammonium nitrate here. So, but it's still in the troposphere. It's deep in the troposphere. So it has not entered the stratosphere at this point. And let's go to the eastern part over Alaska. So over Alaska, we had 2 flights, but this one flight is I show here. This has ammonium nitrate clearly in the stratosphere. So this is the stratosphere, that's a tropopause, that's the lower stratosphere. We measure it up to the aircraft altitude. Maybe even it's also higher than the aircraft altitude, but we cannot measure altitude resolved about the flight level. So this is really the first time that we can see that ammonium nitrate, the particles, the solid particles, are really transported somehow into the lower stratosphere from the monsoon, where we always measured these particles inside, mainly inside or near at the dropper pause. But it is clearly now in the stratosphere, and maybe you can say it's formed in situ. We looked at NH3, and you can see here NH3, it's not shown here, but there are no indication of NH3. So NH3 is totally, there is no form of NH3, it's not there. But ammonium nitrate particles, so somehow the particles, they made it into the lower stratosphere. And the question is now, of course, what will they do in the lower stratosphere? Will they survive? Will they interact with ozone? Or what is, so that's really then the open questions we have to solve. Models perhaps have to look at. Okay, and then, I have still 2 minutes. In these 2 minutes, I want to make some, or to show you some, let's say, proposal of us coming from this instrumentation of our aircraft, where we proposed a similar instrument to ESA, to the European Space Agency, that they will put this instrument also on a satellite. We have shown it is possible to measure this from the aircraft. We have the instrument also on a balloon and make stratospheric measurements. And now it would be nice, of course, to put it on a satellite, but of course, in space agencies, they have to be convinced. So with this instrument, we want to look into height resolved measurements of trace species and temperature, from 6 kilometers up to 110 kilometers, and get altitude resolved measurements of these species. So there are, let's say, different objectives here. So the middle atmosphere, circulation changing, what's the wave driving of the circulation, what is the coupling with the upper atmosphere, and here what is the input by biomass burning, volcanic eruptions, and convections from below, so from the troposphere in the atmosphere. So this interaction is one of the main objectives also of this mission. So the mission is, as I said, it is also an infrared limb sounder. Like this, looking at making such a picture each 50 kilometers. So, and then we have these measurement tracks here, and there we can derive also altitude profiles along these tracks over the whole globe. And for example, here, when we concentrate here on the monsoon region over India, this was the measurement track of our Gloria flights, or of our at 14 kilometers here. That's an example at 14 kilometers of NH3. This was, let's say, the MIPAS, the old MIPAS instruments resolution, let's say, or sampling. And this would be the sampling in 3 days with this CAT instrument. Of course, not only at 14 kilometers, but also height resolved at different levels. So this would be a large advancement in the measurement capabilities also globally, which is shown then here. This is a simulation of NH3 of 1 day of measurements. Of course, we cannot make in 1 day a total global coverage. However, we can do it nearly global coverage in 3 days. Okay, should stop here. But still 1 minute. And this is just the CAMS, what we have seen CAMS, the model can simulate NH3 quite well here in the monsoon region, and this would be the retrieval at 15 kilometers, which we simulated with this CAT instrument. You can see here patches, of course, the patches are the clouds, but still there are a lot of measurements left for 1 day, and when you have many days there, you can quite well recover these pictures, and the mission is proposed to take 5 years, perhaps up to 10 years, and we will see if this will come. Okay, so just a summary. So Stratoclim campaign, Envisat satellite has shown ammonium nitrate and ammonia are abundant in the monsoon upper troposphere. So the airtel, just to say, I concentrated on this, but the airtel does not consist only of ammonium nitrate. It also consists as our in situ colleagues have shown, of organic nitrates, for example. So there are organic substances also. So in the south track, we have seen that CAMS has the model has problems to simulate in biomass burning plumes NH3, but it simulates well in the Asian monsoon region for whatever reason. Then in Phileas, so the main result of Phileas was that we first detected ammonium nitrate filaments outside the monsoon region, not deep, but in the clearly in the lower stratosphere. And then we hope that we will get this instrument in the beginning of the 2030s. So we made it through ESA. There were 2 selections, and now we are, let's say, in the final. We are in a competition with one other instrument which will fly there, and the decision will be made in July next year. And of course, we hope that this instrument, and also concentrating on the middle atmosphere, on the transition between troposphere and stratosphere, will make it in this round of the ESA. Okay, so thanks a lot for your attention. Question?
Are there any questions?
Michael, you mentioned the source track measurements, and you mentioned the issues with the source strength above ground. And of course, a naive step would be to think, if the source strengths are problematic, couldn't you do something about it, or how could you improve them, or how did you derive them? Or if you know the measurements up there, could you do something about better knowledge of the source strengths at the ground?
Yeah, one should test if it's just only the source. I would say it's not only the source strength, but one should of course test this. But somehow they bring it up. I think also when the source is less, they will bring it still up there. But I think fires are also difficult to model. So I mean, you know it better than me and. But of course, you could assimilate, let's say, IASI measurements for the source strength. But I don't know IASI measurements if they are, how good they are in case of fires. I'm not sure about the accuracy of. Yeah.
Yeah. Thank you very much, Dr. Michael Hoffman. That was a very nice talk. I was wondering, so you showed this in the upper troposphere and maybe lower stratosphere in the monsoon anticyclone. You have this ammonia and ammonium nitrate. So do you also see this in the other months? You showed July and August, some of these planes.
Yeah.
But do you see them, for example, in April or May?
Yeah, we have looked at MIPAS measurements. So this was this old satellite, and it starts in June. We don't see it in the months before.
And the other question is, see, we have this anticyclone during the boreal winter. We have the anticyclone over West Pacific, over the maritime continent, Indonesia and the region like STIPMEX.
Mm-hmm.
So, is there some evidence for this ammonia and nitrate, let's say in December, January, or February? Because convection is very deep, the monsoon is very strong. Do you see that in those regions?
In those regions, we have not really looked in detail at those regions. I don't remember that we have really seen. I think we have looked at the satellite and did not really capture one clear signal. But
because they also have forest fires in those areas. So there's a lot of biomass burning going on. And so whether you can see these ammonia in that region.
Mm-hmm. Yeah, might be to look also at this.
So you are saying you did not see the South America, is it? South American monsoon?
Yeah, so South American, it was just the fire season in September, October in South America.
Yeah, but then the convection is during December, January, February.
Yeah, that's true.
It's like April here, like,
Mm-hmm. 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 Yeah.
Thank you, Michael. I have 3 questions. First one, one by one. What would be the reason between the mismatch between ammonia and ammonium nitrate in altitude? In the peaks that you showed, ammonia is lower in altitude than ammonium nitrate. What do you think? What's the reason?
Perhaps we can just go back to the. No. Sorry. This one.
Yes.
I think you and you point out that this is that here the main ammonium nitrate is here, and we have the So yeah, we are speculating. I mean, so this one here fits quite a little bit in this area, and maybe inside here there's still ammonia, and outside here somehow ammonia has already been converted into ammonium nitrate, which is then lifted up. But Bärbel can explain this better than into near this region. But we don't have really modeling about this. Yeah. So, yeah.
Thank you. So, my understanding is the sources of ammonia are coming from agriculture, especially in the northern part of India. So, if you had to convince decision makers to reduce the amount of ammonia in northern India, what would be the main argument?
I don't know. Do I have an argument from this to reduction of ammonia? I'm not sure if I can make a sequence of arguments, because at least I don't know if this ammonium nitrate here, it will influence cirrus clouds, how strongly it will influence cirrus clouds, if more cirrus clouds are good or are bad. This would be the reason then to make the argument chain from reducing ammonia to this. I think there are other reasons to reduce ammonia, mainly on ground, because of health issues and so on. Yeah.
And finally, your measurements you showed in Alaska, you show ammonium nitrate in the stratosphere. You run some back trajectories to find out that it was coming from the Asian monsoon. How sure are you that it's coming from the Asian monsoon and not?
We had analysis, so from the ICAN-ART model at the time, which indicated that air is coming from the monsoon. We have seen elevated PAN, peroxyacetyl nitrate, which might also come from local sources, but perhaps also from monsoon. And I think the group in Jülich, Bärbel, and so they are doing extensive analysis of these. And I think they also agree that it comes from the monsoon, if I'm not wrong, Bärbel.
Very interesting discussions and nice talk by Michael. Just one quick question we'll take and then we break for tea.
I'm not an atmospheric chemist, but I'm learning a bit here. Can you say something about sulfates also? I mean, you have mostly looked at ammonium and ammonium nitrate and ammonia.
Yeah.
And I think there is a lot of sulfate aerosols as well. So can you, I have no idea, so maybe you can enlighten me by saying something about, I don't know whether you measure it, but whether sulfates are important and sulfates, are they carried to the stratosphere during this monsoon period, etc. Yeah, thank you.
Okay, I don't know if I can enlighten you, but sulfate, there was, before Stratos-Link campaign, there was of course the notion that sulfate may also be a large component of the ATAL. So our in situ colleagues who measure sulfate together with ammonium nitrate, they also say, okay, sulfate is increasing there, but it does not, at least to my knowledge, it does not really have a strong peak there, where the ammonium nitrate and the organics have a strong peak. So it is increasing in the stratosphere, they see it increasing in the stratosphere. And what I forgot to say, in our, to produce the solid ammonium nitrate particles in the laboratory, we need a little bit of sulfate. We need a little bit of, otherwise they stay liquid, this ammonium nitrate particle, they stay in liquid phase, they don't nucleate. if we put a little bit of sulfate in it, then they nucleate and they become also solid particles. So that's an importance to have also sulfate, and also the CERN people, they showed that the nucleation is much faster if you have also sulfate there for particle nucleation. Yeah. Thanks for the question.
Thank you, Michael. So we'll
Yeah.
take this discussion further, maybe break time.
Yeah, please,
Thank
please.
you.
Thank you once again, Dr. Hoffner, for sharing valuable insights. Your contribution has set a high standard for our workshop and has inspired us to engage more deeply with the subjects at hand. I request Dr. Suvarna Fadnavis to kindly felicitate Dr. Hoffner with a memento.
This is IITM building here on the.
Thank you. Thank you. With this, we have now concluded the inaugural session of this workshop. Before we break for a high tea, I would like to make a few announcements. Participants and delegates from abroad, we require to collect copy of your visa for our administrative purpose. You could do this by visiting our registration desk, where our team will help you to take a copy of the same. Please ensure you have done this before lunch break today. From this hall, we will first gather for a photo session outside of this Meghdut auditorium. Media personnel could gather in the front row for further interactions. Following the photo session, we will proceed for the high tea that has been arranged adjacent to this Meghdut auditorium outside. Please note that we are discouraging the use of plastics. In line to that, we have provided metal bottles along with the kit, so kindly help yourself. Also, posters from the participants are being displayed in the pandal area for everyone to view at their own convenience. During the first 2 days, that is on 3rd and 4th June, the posters that are relevant to stratosphere-troposphere interactions would be getting displayed, and the posters that are relevant to the theme on prediction of monsoon weather extremes would be getting displayed in the next further 2 days. Abstract book is available online, so you can visit our website and just take a look on that. And we request you to kindly keep visiting the website for further updates. If you encounter any difficulty, feel free to approach our volunteers wearing yellow tags like me. So they will be available to assist you for any help you might need. And we also request session 1 speakers who have not uploaded their presentation, so kindly you can upload it here in this laptop before we begin the first session after tea break. Thank you one and all for joining. Let us now break for the group photo. Please assemble here at sharp 11:15 Indian Standard Time for the first scientific session of this workshop. Thank you.
Workshop, which is Atmospheric Composition, Chemistry and Dynamics of the UTLS. This session will be chaired by Dr. Mark von Hopp from Jülich, Germany. Dr. Siddharth Shankar Das could not join us today. So over to you, Dr.
Yeah, thank you very much. So the first session is on atmospheric composition, chemistry and dynamics of the UTLS. And as a first speaker, an invited speaker is Professor Greg Carmichael from University of Iowa in the United States. And he will be telling us about advancing atmospheric composition predictions and services to meet the growing societal needs. So the floor is yours. Thank you.
Okay, can you hear me? I think so. Okay. It's my pleasure to be able to participate in this important meeting. Again, my name is Greg Carmichael. I'm at the University of Iowa. I chair the Scientific Steering Committee for the WMO Global Atmospheric Watch Program. And that's one of the 3 research programs within the WMO, along with the others that are co-sponsoring this meeting, the WWRP and WCRP. I'm going to talk just in general about the importance of atmospheric composition and not specifically to the topic, but clearly the Asian monsoon is influenced by atmospheric composition, and the Asian monsoon has a profound impact on the distribution and fate of atmospheric composition. And so I think it's relevant to all the things we're talking about in this meeting. And so when we think about atmospheric composition, it certainly matters that when we're here in India, and it certainly matters to air quality. We're well aware of that in India as well as all around the world. But we also understand that atmospheric composition plays important roles from direct radiative effects, from microphysical effects, from effects, feedbacks in the biosphere, and effects on the cryosphere. So really in all components of the Earth system that are important to weather and climate and other important issues, atmospheric composition plays an important role. And I think in recognition of that, more and more efforts are put into place to increasing the capacities to observe atmospheric composition and to more explicitly include atmospheric composition into the various relevant components of the Earth system. And so the premise, of course, and I think it's absolutely true, that monitoring and prediction of atmospheric composition plays critical roles in supporting societal needs. I just mentioned the air pollution, human health. It's the driver of climate change. But we know a lot, but there are considerable challenges that remain in our ability to provide the reliable and user-driven atmospheric composition information for many parts of the world. I would say for all parts of the world. And really what we need moving forward is concerted effort, and whether we're focused on the monsoons or we're focused on early warning for all, the advancing atmospheric composition information systems are really needed, and that's needed really to reduce the impacts to society. And so I think in our communities, in the atmospheric composition community, but also I think in the weather community, our real overall objective is to continue to improve our analysis and predictive capabilities. We really need to predict our prediction capabilities, and that is dependent upon our knowledge. And so as our knowledge increases, will increase the predictability, and then the use of our models and other drive services to society will be enhanced. And I think it's very clear, whether we're talking about air quality, weather, climate, society recognizes the needs for this information, and we're recognizing the closer linkages between weather, atmospheric composition, and climate-related services. This diagram shows here, I think, every major Met Service center around the world is working more closely on seamless prediction, the more coupling, and at least in the same common system, Earth system modeling framework, of being able to derive the weather, climate, and environmental services. It's also widely recognized that, as also talked about in the opening ceremony, this information is needed by society, and so it's needed at higher resolution, and it's needed at longer lead times to provide the sorts of response that society can take to that. And really, to improve our predictability in this space, it requires advances on all the fronts that are needed for a complete prediction system. The observing system, the modeling system, the ability to assimilate that information together. And I think the point that we often fail to just take for granted, but the other part of the infrastructure that's absolutely critical is the human capacity. And again, I'm very pleased that in this meeting, great efforts went to really have a very, very large number of young scientists. And I'm very happy that that takes place, and I'm really looking forward to hear from you and the exciting things that you're doing. So the Global Atmospheric Watch Program at WMO is really focused on providing atmospheric composition, coordinating atmospheric composition observations globally, and to provide that information that is open sourced, of high quality, that can be used for a variety of different applications. It's a WMO program. It's actively engaged in 100 different countries, and we're well known for our long-term systematic observation. And that is, as you can see, this diagram is centered to what the Global Atmospheric Watch program is used for. And one of the ways that the observations are used is directly to support conventions, and we already mentioned, and since at this particular meeting, the role of upper tropospheric stratospheric ozone is well recognized and will be talked about throughout this meeting. This information is used to, for example, to help support the ozone conventions and the ozone assessments. Same thing is true for the Paris Agreement and for the long-range transport agreements that are related to air pollution. Certainly on the climate change side of it, which is critically important, and I'll talk about that later, some of the new services related to carbon dioxide. This information is directly related to human health, the impacts of atmospheric composition, and when one derives the societal impacts of atmospheric composition taken together, that's by far the largest factor from society. It exceeds all of the severe weather, et cetera. The health loss due to air pollution is if one looks at it in economic terms or in deaths. And then another important component of atmospheric composition is, along with weather and climate systems, is to provide warnings, and I'll talk a little bit about that. So when we think about atmospheric composition, one thing that our community needs, and I think was already talked about earlier, that we need to strengthen the atmospheric composition measurement and data infrastructure. Compared to a talk given 10 years ago, we've come a long ways in terms of atmospheric composition measurements. We can look in India, the expanding role, even at this institution, of taking in situ surface-based observations for air quality has expanded greatly. And they're of great importance, but the fact of the matter is that almost everywhere in the world, the current observing system for atmospheric composition are fundamentally inadequate to provide the sorts of service that we need, that society needs in this regard. I'd like to take just a moment to talk about, we're here in a premier weather research institute. The capabilities predicting weather has increased dramatically over the years, and that's been, we've increased the capabilities of models, we've increased the capabilities. I think we lost a battery here. But also because of the expanding observing network of meteorology, right? And so if one looks at the observing system for meteorology that allows us to provide this, in greatly increased capacity of prediction. And so I think that from my mantra standpoint, over time we need to make the atmospheric composition observing system look more like the meteorological observing system. It won't look the same, of course, but it doesn't have to be several orders of magnitude less defined than weather because of the significance to society. But the good news is, in terms of the atmospheric composition observing system, it's expanding greatly. Again, under the WMO-GAL program, we coordinate a large part of this observing system from in situ measurements, the aircraft observations that are routinely based, the ozone sounds, and all the infrastructure that goes into having reliable observations through the ozone sounds. These great advances in the low-cost sensors. And then on the other end of things, it's exciting because the number of instruments being flown in space devoted to atmospheric composition are expanding greatly for a variety of different activities, including already 2 geostationary satellites dedicated to atmospheric composition. A third is will be launched in not too distant future. And then even upon that, operational geostationary atmospheric composition observing systems like the one that NOAA is planning to launch so it's really exciting in that expansion. And then on the other side of things, there's more and more science-based missions. One mission that I'm involved with in planning at NASA is the AOS observing system, which is really focused on active instruments for both aerosols and clouds and precipitation. So we'll have, again, we'll have simultaneous measurements of aerosols, clouds, convection, and precipitation to help improve our process understanding, which will then improve our predictive capabilities. Again, one of our main goals, and I think most relevant to the discussion in this conference, is increasing our predictive skills. And one thing that the GAL program, and we're just entering into our first phase of our new strategic implementation plan, is really focused on improving the capabilities in Earth system models to add atmospheric composition information. And that's coming in through a variety of different components, but that's really to bring into this Earth system modeling framework to provide the capabilities for a variety of applications in terms of atmospheric composition. So specifically, what are some of the things that we're focused on in the next 4 years? I mentioned the atmospheric composition into the Earth system models. Certainly in this meeting, we'll hear a lot about the interactive components and the importance of aerosol interactions with the monsoon systems, the coupled chemistry and meteorology and the climate feedbacks. We have a long ways to go in terms of chemical data simulation in coupled Earth system models, and so that's an important component that we're focused on. And again, the things that we're most interested in terms of warning are very relevant to what we're discussing here, because they're the sources of the aerosol that drive, and those are dust, air pollution, and fires. And we have active components and early warning system developments for each of those categories. And then some of the fundamental things that are important to air pollution and to flux emissions from greenhouse gases is the role of the atmospheric boundary layer. And there's many, many things of interest in there that cut across atmospheric composition, weather, and climate. So right now we have early warning systems that are put into place. The sand and dust storm is our most sophisticated, and that's an operational element in some regions. We've just stood up a new early warning system for vegetative fires and smoke pollution, and so this will enhance the capabilities to detect, predict occurrences of smoke and smoke plumes and quantifying that. And then, of course, in the air quality component, predicting air pollution at scales from urban to global, and again, relevant to, and do those in a coupled Earth system model, so we'll have the feedbacks and the interactions between interactions of systems, for example, like monsoons. And the next one we are planning to set up is this Global Greenhouse Gas Watch, and I'll talk about that in just a moment. So on the air quality side, which is very relevant here in terms of prediction of air quality, it's an important service. In India right now has an operational air quality forecast that was originally developed here at IITM, and I was involved in that along with Gufran Beg. We started working that in 2008 for the Commonwealth Games, and that's now extended into operational elements that in joint with the Indian Department of Meteorology. And so there's lots of important activities in the air quality space that are relevant to what we're discussing here. Also, a growing element is the important role of atmospheric composition in extending our capabilities in seasonal to subseasonal prediction. We have ongoing projects with WGNE in terms of trying to quantify the role of atmospheric composition in its ability to improve seasonal to subseasonal prediction. And here, lots of experiments going on, but in terms of column ozone and in terms of aerosols, these results are showing that it does make an important contribution. And that's one of the motivations that we keep seeing more and more operational centers putting more and more atmospheric composition capabilities into their services. Certainly, the connection between climate change and atmospheric composition is obvious. Climate is changing because of human-induced increases in greenhouse gas concentrations. And here, and those that have been in India, that live in India or have been in India recently. I was just in Delhi for the wonderful 126 degrees centigrade day. So heat waves are increasing dramatically, and certainly the human health impact of that atmospheric composition response is large in terms of mortality. And so it's growing in terms of its importance as we lead to warmer and warmer climates. And I think it's important, and it was talked by Estelle in her mentioning of the World Weather Research Program, this cascade of impacts that happen under these heat waves. Heat waves exacerbate air pollution, and then you can see all sorts of the physical responses of the system that cascades to already in India and Delhi. We were seeing reductions in power generation, water scarcity. All these things are exacerbated by these heat wave events, and that goes on to all sorts of things. And so this cascade of activities is really important for us to understand, and that's why the UN and WMO has this highest priority of further developing this early warning capability for all. And the other component is this connection that I mentioned between climate change and air quality. We know it's been there, but also some recent study by what we've been involved with is looking at the co-occurrences of these heat waves and this heavy haze pollution. And I'll just show the summary here, focusing in on this particular study looked at China and India. But if we look just at the India side, you see the two circles there. One circle is for the heat waves, heat extremes, and the other one is for the heavy pollution events. And the inner circle is what's the assessment of those frequency of occurrence today, and the co-occurrences, which is the intersection of those. And then if you go out to 2040, 2050, using the CMEP sorts of analysis, you can see the significant enhancement of the co-occurrences of these heavy heat waves and the heavy pollution events. So these are really, really important. And again, the sorts of interactions that we need to understand. We need the atmospheric composition observations to help us understand that. We need those represented in the models and the feedbacks that those occur in the Earth system models if we're going to better understand this and be able to anticipate these events. So the big atmospheric composition elephant in the room, of course, is carbon dioxide and the greenhouse gases. And that is an activity that the GAO program, it coordinates all of the greenhouse gas observations that are used to do all the IPC and assessments and to determine the trends of greenhouse gases. And we have a new activity that I'd like to talk about today. So clearly we need to reduce the greenhouse gas emissions, but right now, lots of things going on in terms of the formal frameworks within the UN system. But so far, all of those are voluntary. The US makes their voluntary what our commitment is, and then over time we assess whether we're meeting those commitments through bottom-up inventory processes. But it's very, very complicated, and it's a well-coordinated and orchestrated and important process. But the fact of the matter is that climate changes and climate responds not to what we promised, but what the greenhouse gas concentrations are in the atmosphere. And so if we look at the greenhouse gas record, this is a current record of CO2 for Mauna Loa, for example. And we can look at the impact of first the UNCC Rio, and then of course Kyoto, and then of course Paris. All of these very important commitments to reduce, but the fact of the matter is the concentrations of CO2 continue to rise. And so clearly, all the UN system and all the governments are really, we want to move forward in a way that we can make this bend the curve in reality and not just talk about bending the curve and reaching carbon neutrality. And so the issue, of course, is how do we verify emissions is key to that. And so the former framework of IPCC, and when India reports its emissions, when US reports their emissions, it's a bottom-up inventory. You take activities, you have emission factors, and that's a slow process. Takes a couple years in order to do that. So by nature, the inventories reported are a few years out of date. But we have the capabilities, of course, and it came up earlier about the ammonia issue. If we have the observations of ammonia, if we have models that have some skill in predicting ammonia, and we have an assimilation system that can relate the observations through the models to the emissions, we can do inverse modeling, and so we can do top-down estimates of those emissions. And that's the system that we have that capability for greenhouse gases now. It's research capabilities in many pockets of the world. And so we take observations of CO2. We have models that have some skill in predicting. We have the emissions built into these. And so we can use all that information to infer the net fluxes at the surface and what they have to be in the model world for that to be consistent with the observations. And so this is an approach that's is of growing importance. Both are important. And by doing both together, then over time we'll get reconciliation. We'll understand the top-down, and the top-down will come closer together. And that will be kind of the basis that we'll have to have a common knowledge to understand how emissions are changing and how those changes relate to composition. So we're getting ready to launch. So next week I'll be going to the WMO Executive Council for the last leg of getting approval for the Global Greenhouse Gas Watch. And this is an internationally coordinated operational monitoring of greenhouse gas fluxes in support of climate change mitigation action under the Paris Agreement. So you can think of numerical weather prediction, like we have centers around the world that are all producing this, but it being coordinated under WMO in terms of providing interchange of data, metrics and openness and those sorts of things. And so that's what we're proposing to stand up here. It'll be an integrated global greenhouse gas observing system spanning surface to space base. It'll be 24/7 operational, put into place, stood up beginning this year, planned to operate for the next 3 or 4 decades. It will be producing greenhouse gas concentrations of CO2, methane, and nitrous oxide concentrations on an hourly basis globally. And then net fluxes will be inferred on a monthly basis. And so we'll have information, at initially at 100 kilometers, but quickly to move to finer scale. So within India, within any large information, we'll have estimates of net fluxes, and then we'll be able to show whether the net flux is going up or down, and all this information will feed the Paris Agreement. It will feed a whole bunch of downstream influences. The private sector, where there's $100 billion of assets being sold in terms of carbon offsets, going into reforestation and other aspects, but no one knows whether that's a real asset or not. You don't know how the forests are managed. This will be information that will also help verify those assets, and will give, of course, more financial incentive for those assets to be played. So. And as I mentioned, it's already been approved. It was approved at last Congress to develop the implementation plan. I co-chaired the plan of development of this plan, and next week it will go to Executive Council, and hopefully we'll get the green light. And here's the plan for that. So it'll be the initial pre-operational phase will begin now and extend for the next 3 years. Then we'll enter into the operational phases. And so this will be a complete system, like weather system, in situ, satellite observation. And in order for this to happen with any, we really need to grow the observing system. So hopefully this will stimulate a lot of advancement in terms of surface-based observations of carbon dioxide. At the same time, we're greatly enhancing our space-based capabilities. That's happening both from governments, from the private sector. And so hopefully this will be a real great example of a really an interoperable, dependent atmospheric composition, atmospheric physics, and operational infrastructure. So with that, again, just talking about the importance of atmospheric composition. And again, hopefully I convinced you that we're all on the same, I think we're all on the same side here. Atmospheric composition matters. We need to grow the capabilities of that, and we need to keep improving our capabilities in the Earth system modeling. So thank you.
Yeah, thank you, Greg, for this very nice and very interesting talk. And are there questions in the audience?
So very nice overview. So just a comment from you on this climate and heat wave things which you have shown. So what sort of data was used to make those kind of assessments? Because we, even sitting here, face to get the data. So what was because that very, sorry for this, a very large number of deaths has been shown over India in that cartoon which you have shown. So just a comment on data.
Okay, so just to clarify, so there's two pieces of information I gave you. One was the study of the mortality related, the global mortality, and that's a study that, you know, again, heat waves and then the correspondence. I wasn't involved in that study directly, so it's a peer reviewed, but you can understand, I don't know the total methodology. But similar to air pollution, where we have understanding of responses of heat waves and studies in some cities, and then they extrapolate that to do the global analysis. And then in terms of the co-occurrence of the heat waves and heavy haze events, you know, that was done for the India and China. China, we had much more access to the observational data. India, we had what we had, and then we also had reanalysis for the current situation. And then the future situation was all based on CMEP sorts of model runs under changing climate, and then did the same analysis using the same metrics today, and then the occurrences of those metrics-based heat waves and metrics-based heavy haze events. Yep. Yep.
So another question by Dr. Krishnan.
Greg, that was a very nice talk. You showed that the global atmospheric measurement of greenhouse gases. So is that at the surface, or is it having at different levels in the atmosphere?
Yeah. So the current observing system for greenhouse gases has a lot. What determines the kind of the best estimate of the greenhouse gas concentrations are surface-based observations. But we have a lot of other tall tower measurements. We have some remote sensing capabilities, and then we have growing capabilities from satellite for measurements of CO2 and methane specifically. Yep. Yep. And so the observing system that we'll use in this new infrastructure will be all of the above. Yep, will be put together.
So there'll be three-dimensional fields.
Absolutely. And then the assimilation system will fill in those gaps. Yep. Yep.
Okay, time for another quick question, if there's one. Oh, online. Are there any questions online? There's a chat. Maybe you can click on the chat. Don't see any questions.
Yep. Yep.
Then I thank you again for this presentation. And I'm happy to announce our next invited speaker, which is Dr. Mi-Young Park from NCAR in Boulder, Colorado. And she will be telling us about the relationship between water vapor and the cold point tropopause. Mi-Young, the stage is yours.
Can you hear me okay? This is, okay, maybe I'm okay. Should I go ahead? Okay. So I'd like to thank all the organizers for having me over here. Hi, I'm Mi-Young Park from NCAR. I'd like to bring some of Boulder to Pune. So this is a picture of a mountain I go for a hike a lot. And I'll be talking about relationship between water vapor and cold point tropopause during boreal summer. Okay, here are 4 things I'm going to talk about today. Number 1, water vapor climatology over Asian versus North American monsoon regions. Number 2, cold point tropopause in the UTLS region. Number 3, I'd like to introduce you a little bit about cosmic 2 temperatures and atmospheric waves. And number 4, future plans. some in situ measurement, and a global chemistry climate model, WACCM. So to warn you, this is work in progress. So water vapor plays an important role in many aspects of the climate system by affecting radiation and cloud formation and atmospheric chemistry and dynamics. And stratosphere is very dry. Then, is it important? Stratospheric water vapor is an important driver of decadal global surface climate change. This is a figure from Solomon et al. Published in 2010. X-axis is year from 1980 through 2010, and y-axis is radiative forcing change from 1980. At about 2000, there was a sudden drop in stratospheric water vapor abundance, and it decreased radiative forcing change rate. And there are two curves. One is blue, that means with water vapor. One is red, without water vapor. So adding stratospheric water vapor will accelerate the warming of surface temperature. Lower stratospheric water vapor also impact atmospheric circulation. So more water vapor in the lowermost stratosphere will decrease temperature locally, and this will increase the temperature gradient, and eventually the subtropical jet will shift it upward and poleward, and then we get strengthened stratospheric circulation. Let's talk a little bit about water vapor tape recorder. This is all about seasonal variation in water vapor in tropical stratosphere. The seasonal variation in water vapor entering the stratosphere follows the cold point temperature, setting the base for the tropical tape recorder during the dry phase, which you can see from this figure, purple to blue color. And during the wet phase of the tropical tape recorder, enhanced water vapor over the northern hemisphere summer monsoons makes its way into the lower stratosphere. In addition to the seasonal variation, there is also an interannual variability in tropical water vapor. As you can see, one good example is the Hanga Tonga eruption. It happened January 2022. So just in case you've never heard of tape recorder, you've never seen a tape recorder, I found this image from Google. But this is not perfect, this is broken. So let's talk a little bit about water vapor in the stratosphere during summer. So these are the figures showing, so I think bugs really like me. So on the right side is the water vapor average for June, July, August, the satellite from ACE FTS satellite at about 15 kilometers. So x-axis is longitude, y-axis is latitude. There are two hot spots, one over Asia, one over North America. So high water vapor sits where convection is strong, as shown as white solid line. When you look at the figure on the left, it looks a little bit different. So when you substitute one H from H2O to deuterium, it becomes HDO. So HDO is heavier than water vapor. And the ratio we say is delta D. And when water vapor condenses, the heavier isotopologues removed first. What that means is when water condenses, delta D decreases. So when you look at the figure on the left, over North America, there is enhanced delta D due to convection, but over Asian monsoon area is depleted. So even though there are two hot spots in water vapor, they have different characteristics. Now, let's talk a little bit about the processes bring this high water vapor into the lower stratosphere. There are multiple processes, but one is large-scale transport. As you can see from the figure on the left, over Asian monsoon area, there's deep convection near the surface, brings high water vapor up to a certain level, and then it gets confined with an anticyclone. So this is shown from my paper in 2009. Also, there's another paper by Plugger et al. They're emphasizing the transport from high latitude into the monsoon area. And there's also deep convection that contribute to high water vapor. This is an example shown in Yu et al. Paper published 2020. Over North American monsoon region, there's convection, as you can see at the top figure, and there's water vapor. At the bottom figure shows this convective influence. But convective influence in water vapor is not as clear as you would like to be. So this is a figure I made from CH3 ISS water vapor for August 2017 and 2018 over North American monsoon regions. The colors represent water vapor mixing ratio, and the green dots represent deep convection based on GPM measurement. So 2017 August was wet year. 2018 August was dry year. But it's hard to make a conclusion based on this figure what convection does. So I would say convective influence on water, lower stretch of water vapor is a little bit unclear. So I just mentioned to you about CH3 ISS. The CH3 ISS is a satellite, measures also water vapor. The satellite was launched in February 2017. So we have about 6 years of data. And what's really nice about CH data, it also measures aerosols, NO2, and ozone, in addition to water vapor, with really high vertical resolution, between 70 degrees south and 70 degrees north. And if you look at this figure, it's a little bit noisy because the sampling is a little bit limited, but it captures the important features of water vapor in the stratosphere. Water vapor tape recorder, and also Hanga Tonga eruption. Then what can we do with this high vertical resolution? We should use it. One thing you can do, we can look at the detailed structure of water vapor and temperature over North American monsoon regions. That's what I did a couple years ago. So there are two figures you're looking at right now, one over Asia, one over North America. X-axis is temperature, Y-axis is water vapor, but the scale is reversed. So if you go to top, it's more dry air. So as you can see, over Asia, air is much drier and colder. And over North America is wetter and warmer. Okay, we've learned a couple different characteristics over Asia versus North America. And if I repeat the same figure over different years, over North America, there are larger year-to-year variability than over Asian monsoon area. So I just mentioned to you about this relationship between water vapor and temperature over Asia and North America. Another way to look at this relationship is, let's look at the relative humidity. So this is also a map that I produced using CH3 ISS data. Now I'm looking at relative humidity in color, and gray solid line is cold point temperature. So there are two distinctive features here. Relative humidity is much higher over Asian monsoon region than North America because the water vapor is enhanced over both areas, but over Asia, cold point is colder and higher. It makes air much wetter. And then over North America is warmer and dry. Okay, this is all consistent. I'm not making anything up. In terms of temperature data, I promised to you, I introduced you to Cosmic 2 temperature. Cosmic 2 is an equatorial constellation of radio occultation satellite that was launched on 25th of June 2019. So we have quite a few years of data accumulated now. Cosmic 2 temperature has really, really high vertical resolution. So what you can do with high vertical resolution is to look at equatorial waves. Because waves has really narrow vertical scales. So Cosmic 2 temperature is useful in looking at vertical structures of equatorial waves. And also, because of the sampling, now we can make global map every 6 hours. This is very useful. So I just said, okay, let's look at some wave structures if we can find anything in the tropical stratosphere. What you're looking at, there are two figures. Top figure is something called total variance. We calculated temperature variance based on cosmic 2 data in the tropical stratosphere 8 degrees south to 8 degrees north. X-axis, once again, time from 2019 through 2024. And as you can see, there are some high values of temperature variance coming down almost pretty much every 2 years, looks like it. And when you look at zonal wind at the equator, there's some feature you can recognize. What it is the bottom figure, as you can see, purple is westerly shear phase, and green is easterly shear phase of something called QBO. The QBO is the dominant climate variability in the equatorial stratosphere between about 16 kilometer to 50 kilometer. As you can see, westerly and easterly shear phase alternate with an average period of 28 months. So when westerly shear is coming down, there is high temperature variance. What does that mean? So QBO westerly shear is contributed largely by Kelvin waves. Then we can look at the wave structure based on the temperature data. Now let's go back to a little bit of water vapor over monsoon area. So I'm looking at water vapor versus temperature variance. We just learned that we can look at the waves. Figure on the left is average water vapor mixing ratio for just 2017 August from MLS. It's another satellite from NASA. Over North American monsoon region, over Asian monsoon region, there are two hotspots showing high water vapor values. Now, on the right-hand side, I'm showing you the cosmic 2 temperature residual variance. Suppose this high values of invariance is wave activities. Overplotted solid line is cold point. What can you see? There is a really high variance, which means more wave activities over Asian monsoon, but not over North America. What happens, we compare this with some kind of source. Let's assume convection can trigger waves that you can see in the temperature. So now I'm looking at a map of climatology of deep convection on the left, and on the right is still temperature variance with cold point. Convection is strong over Asian monsoon or North American monsoon, but wave activity is much stronger over Asian monsoon area. So wave activities, because of the high vertical resolution and high temporal sampling of cosmic 2, we can even look at diurnal cycle in temperature and connect to the convective activities. The two figures on the left is temperature anomalies in the tropics, 0 to 16 degrees south. On the right is deep convection. The deep convection is shown around between 0 to 60 degrees longitude and 300 longitude is where Africa and South American continent is located. Deep convection over continental area can trigger tropical waves. That's what you're seeing on the figure left. Westward propagating waves are seen clearly on this figure. One thing we're just learning now is that if we organize convection in current local time, not UTC, we can actually capture convective activity more accurately. So this is one of the projects we're working on right now. Try to look at convection based on current local time, not UTC, and connect to equatorial waves and eventually to water vapor variability. So I'm going to talk a little bit about Eclipse campaign. I plotted a couple of things. Dr. Ren Smith will talk about it tomorrow morning. So during eclipse, so eclipse happened in August in 2022. It was really wet. So this wet feature was connected to convection, or what was it? So I just looked at this convective map, especially for August 2022, and compare with MLS water vapor at 83 hectopascal along with cold point. Figure on the right is just said is map of convection provided by Ray Ueyama at NASA Ames. During August 2022, convection was most frequent over Bay of Bengal and west of the Philippines compared to climatology. And in August 2022, during eclipse field campaign, there's more water vapor over the continent, and convection and cold point maximum is located a little bit offside. This cold point tropopause pattern looks a little bit like wave feature. We don't really understand yet, but this is on our to-do list. Now let's look a little bit about in situ measurement. So in situ measurement is really critical in understanding the atmosphere, but it's limited temporally and spatially. But we're going to use it, what we have. So this is specifically focusing on eclipse field campaign. There were 2 aircraft measurement. One was NASA WB-57, one was an NSF-G5. So there are 2 figures. X-axis is water vapor, y-axis is altitude. As you can see, there's really low water vapor measured during eclipse by NSF-G5. So we are going to characterize this event or climatology based on this data in the future. And during eclipse campaign, there was also a balloon measurement, because balloon can go up to 28 kilometers, maybe over 30 kilometers. It can enable us to look at water vapor in the stratosphere, and also exactly how temperature relates to water vapor. So this is also an ongoing study that I'm working on currently. So one more thing I'd like to talk about today was Global Chemistry Climate Model, WACCM. So we have satellite measurement of water vapor temperature. And also, we do have in situ measurement of water vapor temperature from some field campaign. Now we need a model. With model, we can do different things. That's what's cool about global chemistry model. The whole atmosphere community climate model, WACCM, is a comprehensive numerical model spanning the range of altitude from the Earth's surface to the thermosphere, about 140 kilometers. As the figure on the left shows, so we have CAM, only goes up to 45 kilometers, and WACCM goes up to 140 kilometers. We also have WACCM X. If you want to learn more about WACCM and other global models at NCAR, go to this website. So people, okay, now I have satellite data, I have global model. What can I do? I want to compare them. When you want to compare them, we use something called specified dynamics version of the model. So I'd like to show you this water vapor tape recorder. Top figure is the measurement from the MLS satellite that I showed you earlier in this talk, between 15 degrees south to 15 degrees north, and the time is from 2017 through 2024. You can see water vapor tape recorder and also Hanga Tonga eruption. So in modeling community, how can we simulate this? So many colleagues of mine, they worked on it, and then now a WACCM 6 SD specified version of the model run has this Hanga Tonga eruption in the model. I thought this is something really cool to look at. One other thing I can do with model is something called, so we can look at changes in water vapor in combination with changes in circulation. So with the model simulation, you can obtain something called transformed Eulerian mean. We have velocity and also mass stream function. By looking at mass stream function, you can follow where the air goes. So this is an example that I have done previously related to QBO. So QBO has easterly phase and westerly phase. And those two phases have different circulation affecting our tracers. So there are three figures here. On the left is Wacom 6 water vapor average just for QBO easterly phase between 2005 to 2020. And in the middle is the same simulation, but now this is mass stream function from Wacom 6 for QBO easterly. So when you make QBO easterly, QBO westerly composite and make difference between these two, you can quantify what the QBO does to the circulation and water vapor. So on the figure right, this is difference between QBO easterly and QBO westerly phase for mass stream function. And positive value is clockwise circulation, and negative value is counterclockwise. So there is a stronger clockwise circulation in lower stratosphere, and above, there's stronger counterclockwise circulation, and air can go from the tropics to mid-latitude. So this is useful in quantifying changes in circulation along with tracers. So I'm going to do this analysis maybe with North American monsoon or just Asian monsoon cases in the future. So I have not done it yet. So now this is summary slide. So during the Northern Hemisphere summer, stratospheric water vapor is enhanced over Asian and North American monsoon regions in the UTLS region. However, the correlations between water vapor, cold point, and convection are still unclear. Large-scale transfer plays a role in controlling lower stratosphere water vapor in boreal summer. Convection might control water vapor indirectly by modifying atmospheric waves through affecting local temperatures. This is what I'm working on right now. And I've looked at a little bit of ACLIP campaign, how water vapor and cold point temperature were a little bit different than climatology. And lastly, along with observational data set, a global chemistry climate model will provide quantitative information on the changes in large-scale circulation in the UTLS region. So thank you for your attention.
Yeah, thank you, Myung, for this wonderful presentation. Are there any questions?
Thank you, Dr. Myung. It was a nice talk. So you showed that after Hunga Tonga, this water vapor in the stratosphere.
Yes.
2023, I think this took place in the beginning of 2023, this eruption. 22, no, end of 22, or end of 22, early 2023.
January 2022 was when the eruption happened.
Okay. Yeah. So the temperature, the global mean temperatures in 2023, they crossed 1.4. Was there a role of any water vapor on this? Because it was anomalously very high.
So there was a paper written by some colleagues at NASA. They looked at how this water vapor played a role in changes in temperature and ozone in the stratosphere. And because of this because of this high amount of water vapor, temperature in the stratosphere decreased, radiation cooling happened, and then ozone decreased as well. The paper is just published in 2023.
What surface temperature? Surface temperature.
Sorry, I couldn't hear you.
Surface temperature.
I'm not sure about surface temperature. Can anyone answer about surface temperature? I've looked at temperature in stratosphere. Thank you.
Thank you. I see two hands, one there, and then I come to you.
I think bugs really like me. I just keep having bugs flying.
I have a question on the convection, role of convection on water vapor in UTLS region. Here.
Yeah, okay.
So, is the, like we have similar conclusion on basis of like water convection is not able to put it straight there, but there might be. But have you checked with like without deep convection into winter or some other season, like whether that can put some water vapor in UTLS or not? Because in monsoon we have seen like it's not directly so. but in winter or?
So for monsoon, what I can explain to you right now based on my own knowledge is, so water vapor is a little bit complicated in a way that it's affected by temperature. If there's deep convection, can bring high water vapor, but if the air is too cold, water vapor cannot survive. So the reason why over North America convection can bring high water vapor and still survive is the temperature is not too cold. So I'm just imagining if it's winter time, temperature is really cold, and convection can bring water vapor, can condense and maybe fall down. I'm not an expert in that, but I'm happy to talk about it more with you.
In one of your slides, you have shown that over the Asian summer monsoon region, compared to the North American monsoon region, the convective turbulence, which actually creates your waves and instabilities in the UTLS, actually controls more, has more control on water vapor as compared to the American monsoon region. So do you see that it is co-located? Whatever turbulence is taking place in the troposphere or in the lower atmosphere, whether it is getting reflected in the water vapor and wave activity in the Asian summer monsoon anticyclone or the same region, or wave dispersion also is playing a significant role?
That is a really good question. That's what I'm working on right now. But I have one piece of information I can provide to you right now is that in 1980 there was, or older than that, something called Gill solution. If there's a convection in the tropics, the response is a little off from the convective center. This atmospheric wave response can be not co-located with the convective center. That can be related to what I just showed to you. I need to do more work on that to give you a better answer, but thank you for the question.
Thank you.
So one more quick question, hopefully, from Michael.
Yeah, quick question. Do you know if the eclipse measurements at the high altitudes of the was it somehow influenced by the Hunga-Tonga water vapor?
Measurement
of the WB, the 57.
Well, so I don't think I'm not even going to try to answer that question. So Hunga-Tonga was in southern hemisphere January 2022. Apparently this water vapor was injected to stratosphere. It's still circulating, but in August 2022 over Asia, the location is not quite Hunga-Tonga location, but there could be an influence, but I'm not going to try to answer, but it's a really good question.
Okay, I think we have to go on. Thank you again, Mi-Young. And now we have four more presentations in this session, because unfortunately we had one cancellation and they should be 12 minutes each. And the first one is actually online. So maybe you can switch to the Zoom and hopefully our speaker is there. That's Agil Kotayil. Hopefully I pronounced this correctly. From CUSAT in Kerala, India, who will tell us about the influence of monsoon subseasonal variability on the occurrence of subvisible cirrus clouds. Thank you.
Hello, can you hear me?
We can hear you.
Yes, sir.
You can start, and please unmute your mic and start your presentation.
Yes, I think I can start, right? I mean, I'm audible?
Yes, maybe you could do full screen, please, if that's possible.
Yeah, I will try. Okay, good morning. I am Ajil from Cochin University of Science and Technology. The topic of my talk is the influence of monsoon intraseasonal variability on the occurrence of subvisible cirrus cloud over Asian monsoon region. And these are my collaborators in this study. Subvisible cirrus cloud are thin, high altitude cloud, basically composed of ice crystals. Unlike regular cirrus cloud, these are so thin and nearly invisible to our eyes. Despite their faint appearance, they play a major role in stratified troposphere exchange process and moisture transport within the UTLS region. And conventionally, it is classified as a cloud with optical depth less than 0.03. And these are more frequent in tropics and plays a major role in Earth climate by affecting radiative balance. Boreal summer intra-seasonal oscillation is among the most pronounced subseasonal variability in the tropics, occurring during boreal summer, that is June to September month, and has a period of around 30 to 60 days, and basically it propagates from northward to northeastward, propagating oscillations. And this oscillation is basically divided into 8 different phases, and it influences the monsoon rainfall through active and break, and it is strongly linked to active and break cycles of intense summer monsoon rainfall. And in this study, we are interested in quantifying the influence of this monsoon intra-seasonal oscillation, that is BSISO, on the occurrence of subvisible cirrus cloud, especially their formation mechanism using satellite observations and Lagrangian modeling. So these are the data used in the study. We used Calypso observations of subvisible cirrus cloud during June to September for 3 years, that is for 4 years, that is 2007 to 2010. So we have also used GridSat data for the same period to identify the convective sources of the cirrus cloud, where we have used the infrared brightness temperature, window brightness temperature. And the model employed here is the Lagrangian model Traxila, which is a modified version of FlexPath. And back trajectories are analyzed, simulated using this model based on wind from ERA 5 reanalysis, clear sky radiative heating rate. And this is the methodology employed in the study. The air parcels were released from altitude, from the subvisible cirrus cloud altitude detected by Calypso satellite, and the trajectories are run backward for 45 days. And when the air parcels encounter the deep convective sources, which is detected using GridSat measurements, then particle parcel is marked as the convective source of SVC. This again the pictorial illustration of the whole methodology. And the air parcels were released from the altitude where the Calypso detected the subvisible cirrus cloud, which is basically between 14 to 18 kilometers. That is where we see a subvisible cirrus cloud in the over the tropics. And at each time step, which in backward in time, so we calculate the saturation mixing ratio, and we calculate the minimum saturation mixing ratio along the trajectories. And when the saturation mixing ratio at the source, that is at the point where the parcels intersect the convective cloud, which is detected from GridSat measurements, when it is greater than the minimum saturation vapor pressure ratio multiplied by a constant, which take into account the supersaturation along the trajectories, then we say that these are the convective sources of subvisible cirrus cloud. We essentially launched the parcels from whole Asian summer monsoon domain, where the Calypso detected subvisible cirrus cloud. Now coming to some preliminary results of our study. And this shows the SVC source distribution during monsoon season for 2017-2010 for the subvisible cirrus cloud detected from the Calypso. And as you can see, the majority of the sources are located over northern Bay of Bengal and adjoining Indian landmass region. And these are the subvisible cirrus cloud sources, but for different phases of boreal summer intra-seasonal oscillations. Propagative amount of subvisible cirrus convective sources. For example, sources are more towards north and northeast in phase 1 and 2, while for phase 5, so you can see that these sources are located towards south. So the BSISO modulates the source density of subvisible cirrus cloud over Asian monsoon region. These are the same thing, but for 16 to 18 kilometer, that higher altitude. And here, though the spatial distribution of convective source remains same as in the previous figure, but the difference is that the source density is getting more stronger in this particular altitude range, and it is clearly modulated by different phases of monsoon intra-seasonal oscillations. This is again the quantification of source density over Asian monsoon region for different phases of BSISO for different altitude range. That blue shows the quantification for 14 to 16, and the other color shows the quantification within 16 to 18 kilometers. And there also you can see that the subvisible cirrus cloud sources get modulated by different phases of BSISO. And in some phases you have strong sources, and some other sources you have less sources. This again the age, which is the time taken for air parcels to reach from observation point, and our observation point is the subvisible cirrus cloud dictated by Calypso, and the source is the point where the trajectories intercept the convective cloud, which is dictated from grids and measurements. And the time between these 2 points is called transit time or age. And there also you can see a clear differences between different phases of BSISO. Some phase you have, it can be transported very fast, and some phases, yeah, you take longer time to reach at that particular altitude for the source. This is the quantification of SVC source formation over the monsoon region, basically. And the first plot shows the regional distribution of in situ SVC fraction for different phases of BSISO, for 8 different phases. And one thing which is clear is that, okay, BSISO actually modulates the regions where the SVC forms due to in situ. What I have shown here is the in situ fraction. And the second plot shows the overview of the contributing factor for the formation of SVC, that is convective as well as in situ. And within this 14 to 16 kilometer altitude, around 50% of, or maybe more than 50% is formed due to SVC clouds are formed due to in situ, and rest are formed due to basically it is from convective origin. And this is the same thing for higher altitude, that is 16 to 18 kilometers. So here also, yes, the SVC, in situ SVC formation is modulated by different phases of BSISO, but the difference is that there are more likelihood of the chances of forming in situ at that particular altitude is more than the lower altitudes. And here around 70% of the formation mechanism, SVC formation mechanism, is due to in situ, and the rest can be attributed to convective. So coming to conclusions, SVC source density is more over northern Bay of Bengal adjoining Indian land masses during Asian monsoon season. And BSISO phases influence the north-south distribution of source SVC source density. And source density as well as the transport time varies with respect to which phase the BSISO is in. And regional distribution of in situ fraction is modulated by BSISO, and in situ formation is predominant for 2 altitude ranges, that is 14 to 16 and 16 to 18, with more percentage of occurrence within higher altitude, that is 16 to 18 kilometers. And thank you, and thank you for giving me the opportunity to present my work. Thank you.
Yeah, thank you for this nice presentation, and thank you for keeping the time limit so well in this case. Are there questions? Some of the other online participants want to ask a question. Well, if this is not the case, then I thank you again for this presentation. Obviously, it was so clear that no questions are left open. And our next speaker is from Japan, from Chiba University, Dr. Dmitry Belikov, who will show us a study on the influence of the Asian summer monsoon on the UTLS based on methane distribution.
Okay, good morning, everybody. It is a great pleasure for me to make my presentation in this nice audience. My name is Dmitry Belikov. I'm from Chiba University in Japan, so actually not like Japanese. So maybe you are surprised. So in this work, we are trying to use methane as a good tracer of the muson activity. Actually, a lifetime of methane is about 9 years. So it's quite good to track the transport with a length of about 1-2 months. And actually, the methane is quite good studied using different methods. So here we use satellite remote sensing and modeling data. And actually, methane emission is also quite good studied. And the spatial and temporal patterns are quite well described. And actually, the main problem with methane is chemical loss due to OH radical reactions. And variability of these and trend of these reactions is very, very, very difficult to explain and describe. So actually, you maybe know that India is on the top of methane emission. And this slide describes the emission factors described by Chandra et al. So many factors, including rice, wetlands, cattle, and so on. And actually, majority of the soils are located in northern part of India. And actually, this is a zone of very active transport due to Asian monsoon. Okay. If we look at the seasonal variation of methane emission, the top of emission is exactly during the monsoon period, during the July, August, and September. So firstly, we will try to use GOSAT observation and model to describe the vertical transport and also seasonal variability over the of the methane over the major zone of India. So model, IITM model, quite well describes the convection, especially powerful convection during the monsoon period. But using of GOSAT data from shortwave infrared band, not very well because heavy clouds and heavy aerosols does not provide enough information in, over the India. That is why we switched to new data. This is also again GOSAT data, but thermal infrared band, which resolve vertical profiles with 22 levels, which is quite enough. And also the number of observation data quite good, especially in northern part of India. So we repeat the same analysis by splitting India into 10 regions. The most interesting to look at the northern part, EGP zone. So actually here, both region is split into sub-panels. And the left one is a pre-monsoon, April, May, June, and right one is exactly monsoon period. So you can see how much methane is pumping up from the near surface level to the free troposphere and low stratosphere, exactly. If you look at the time series, you can see that exactly during the Asian monsoon, there is large difference between upper troposphere and near boundary layer. The concentration of methane very, very different here. And you may be surprised that concentration at the 300 hectopascal is much higher than the concentration in the near surface. Even the flux of methane is very, very high during this period. But it means that a lot of methane is pumping up to the upper part by powerful convection. So if you look at this scheme, these three zones are quite well described. So very powerful emission near the surface, convection, and enhancement of substances in the upper part of atmosphere over India. Some substances like aerosol, methane, and other stuff. But this part was described by our analysis. Actually, the methane, which is accumulated here during the monsoon period, transported by several branches. We describe it left branch. So there is a powerful jet which stream all the methane to T zone over the Africa. Then there is one more jet which transport the methane to the south hemisphere. So this is mechanism of interhemispherical transport. And there is large difference between monsoon period and pre-monsoon period exactly over the Indian Ocean. We are trying to estimate this effect and found that during the Asian monsoon, there is blocking effect over India and effect over Indian Ocean, and more enhancement over the African zone. So we estimated this effect and found very interesting feature that over the eastern part of Africa during the monsoon, there is enhancement of interhemispherical transport. While over the Indian Ocean, this is like more opposite effect when the air is transporting from south hemisphere to north hemisphere. And the last topic which we are using, we are trying to estimate the factor like OH radicals influence on the methane. So actually, there are two approaches to estimate these factors. One is more like climatological, another is test version, which is estimated using methyl chloroform inversion. The difference between these fields is quite minor. It's about plus minus 6%. But the effect on the transport of methane and the flux emission is very, very strong. If we describe the effect of OH difference on the methane, we can see this is a difference on the fluxes, very large effect over the India. And this is effect on the concentration. Again, we can see very different distribution with plus minus 10 ppb. That is quite huge. And this effect is slowly propagated to the upper troposphere. So here is a near surface level, this is middle, and this is a lower stratosphere. We estimated this difference during the short period from 2006 to 2013. During this period, OH difference is described here. So firstly, OH start to decrease and then increase. And we found that during the first period, there is enhancement in methane, which is caused by decrease of OH and less uptake, less loss in the surface. But in the upper part, this is opposite direction, this is opposite process. And again, this is enhancement. Both, this is like one year transition of OH, of methane concentration due to OH radical. And after that, there is back transition in 2012 when more enhancement of OH, more loss of methane due to chemical reactions near the surface. But in the upper part, we can see very enhancement in methane. This effect is not yet described well, and we are working on that. So this is my summary. So we are trying to use methane as a tracer to describe medium-term transport with a duration of several months. The major factor of which influence on methane over the South Asia is a change in local emission and influence of monsoon. So the effect of monsoon is described both in subregional and interhemispherical transport. And due to the effect of Asian monsoon, we see the block over the Indian Ocean in the interhemispherical transport, but more enhancement in over Africa. And also, we describe it that our observation from GOSAT thermo-infrared band provide very good coverage and density, which is suitable to describe the OH and methane behavior in the upper part of atmosphere. And the next our study is to describe the effect of OH field and OH loss on the methane in the upper part of troposphere. Thank you very much. That's all.
Thank you. I found that interesting, especially that interhemispheric transport. I wasn't aware of that up to now. Are there any questions? Rolf.
You mentioned the OH fields that are changing. Do you have any idea why there should be a change in OH, plus minus 6%?
Very good question. Actually, it's very difficult to describe what is a factor, which is a factor main responsible for OH variability. Because OH, a radical lifetime of which about several seconds, it's very difficult to measure or describe somehow. Only some indirect methods are available. Only some assumption and estimation through inversion of isotracers like methylchloroform is available. So we can only estimate some interannual variability, which is like plus minus 6% relative to the climatological mean. But if we need more information, we should go more to chemistry, and OH also related to the ozone production, especially tropospheric ozone, CO reaction, and OX reaction. So many reactions are responsible for the OH, and so very difficult to describe which one is the main factor.
Okay, Savannah.
Very interesting talk. Just a small query that I am also fascinated with this intrahemispheric transport. So what is the mechanism which is causing this intrahemispheric from northern hemisphere to southern hemisphere transport? That is occurring at in the UTLS region.
You mean this one?
Yes, yes.
The main transport factor here is several jets. So it is global jets, which works usually from time to time, sometimes more strength, sometimes a little bit more weak. But this enhancement just transported by several jets. One is jets from here to here. Next is African jet from tropical zone to South Hemisphere. So I hope I answered, but maybe we can discuss it later if you have more detailed questions.
Okay, yeah, thanks for the talk. Just a question about the Tanso FTS measurements. So you mentioned there are 22 levels, but
yeah,
they are not independent retrievals. So the real vertical resolution, how is the real vertical resolution?
Yeah, it's a very good question. So actually, technically, it's quite difficult to provide very nice measurements because you are right, all 22 levels are dependent to each others. And the retrieval itself, it's quite complicated process technically. And degree of freedom, so it's not so high in this product. But the main feature of this product, that sensitivity, maximum sensitivity in the free troposphere. So some products like this one, this is shortwave. The sensitivity near the surface. Very nice to describe the fluxes or something, but no information from free troposphere. Here, more information from upper part. So if you're interested, I can show you some slides which describe well about the degree of freedom, about the sensitivity.
Okay, thank you. I think we have to go on. Our next speaker is from India again. It's Dr. Sanjay Kumar Mehta from SRM in Chennai, who will inform us about the relative roles of convection and advection in the sustenance of the Asian monsoon anticyclone.
Dr. Suvarna Fadnavis, for giving me opportunity to deliver the research on Asian summer monsoon anticyclone. So I am Dr. Sanjay Kumar Mehta from SRM Institute of Science and Technology, and my co-authors are listed here. So today I'll be presenting about the relative roles of the convection and advection in the sustenance of the Asian summer monsoon anticyclone. I guess this is the first workshop which is actually connecting, or the first time being conducted, which is connecting the Asian summer monsoon and the upper troposphere. So though the Asian summer monsoon circulation is the part of monsoon, it is hardly dealt with the monsoon studies. Asthma has become one of the hot topics since last 2 decades due to the availability of the MLS data, which provided the signature of the surface pollution reaching the lower stratosphere. After the work of Randall et al., 2006, several follow-up studies, it is realized that asthma plays a vital role in the pollutant transport during the monsoon season. After this workshop, I think this asthma will not only be concentrated for the pollutant transport, but also will researchers will work on the connecting these stratospheric dynamics to the monsoon dynamics. Though there has been plenty of effort in connecting the monsoon has been done, as the monsoon is directly connected to the Indian economy, Indian policymakers mainly focus on the monsoon studies, and the upper tropospheric and lower stratospheric research is not sufficiently explored. Though there have been several works establishing the role of the monsoon or convection on the stratosphere-troposphere change process, as well as to understand the tropopause variability. However, still the tropopause height cannot be modeled, as several aspects in the short-term scales are not clear. It has been already understood that stronger convection leads to the frequent occurrence of the coldest tropopause. Recently, we have examined the variability in the extreme cases of the tropopause, showing the distinct feature which is shown in the upper part of this figure, upper part of the slide. Also, such thermal structures result due to the several extreme weather conditions, including the occurrence of tropical cyclone and thunderstorm, etc. The thermal structure due to the cloudiness associated with the tropical cyclone is well reported by the Boendi et al. So the structure what I have shown here, the lower temperature, lower case, it is actually matching with this thermal structure reported earlier. The anomalous temperature changes were also recognized due to the major volcanic eruption. However, during 2000, there were several volcanic eruptions which had increased the load of stratospheric aerosol, and these others observed that the presence of atoll, which is being investigated in the great extent. We also reported that how much is the effect from the minor volcanic eruptions actually do in the lower stratosphere. So over this Asian monsoon, the tropical easterly jet stream mostly occur at about the same altitude as the tropical tropopause during the monsoon season. Most of the time, the zonal wind profile and the temperature show often similar patterns connected through the thermal wind equation. Our studies, recent our studies, that shows that the tropos height and TJ height often show similar phase. The ASEAN monsoon undergoes intra-seasonal oscillation of active and break phases. These weather conditions during the monsoon must have significant impact on the upper troposphere via the asthma, and hence could also affect the pollutant transport. The research proposal, including the other objectives, the relative roles of the advection and convection, cirrus clouds and temperature interaction were coined together to pursue it under the scheme of promotion of academic and research collaboration funded by the Government of India. Under this, we have actually worked of the present objective. So as we know, the asthma can be defined using various diagnostics such as wind divergence, potential vorticity, Montgomery function, or geopotential height. Its representation based on the commonly used existing method that makes a climatical range of the geopotential height at a given pressure level is not robust and fails in several circumstances, especially for the shorter scale representation of the asthma. So in this study, we had proposed new GPS method to define the asthma based on the location of the subtropical jet stream and the tropical easterly jet stream. So we can see from this figure is that the red one depicts that the conventional way of defining the asthma, and the black one we have actually proposed. So as asthma, one of the important feature appearing as the response of the diabetic heating caused by the essence of a monsoon is the upper level at anticyclone circulation, generally referred to as essence of a monsoon anticyclone. The asthma is characterized by the enhanced concentration of the carbon monoxide, several other tracers such as methane, water vapor, and the reduced concentration of ozone. The pollutant and wet lower tropospheric air is transported upward, resulting in these concentration anomalies in the asthma region. The investigation of the detailed pathways of the boundary layer to the asthma is currently area of active research. The Bergman et al. Investigated the pathway and identified a vertical conduit in the region from the Tibetan Plateau to the Bay of Bengal. Based on the model simulation, Pan et al. 2016 proposed a chimney model, and the chimney model can be explained the vertical lofting of the tracer near the Tibetan Plateau and their outflow in the UTLS along the east-west oscillation of the asthma. At the same time, blower model discussed in the light of isentropic meridional transport, tracer trapped within the asthma into the extratropical UTLS. The transport of tracer and air masses within the asthma was discussed in terms of spatial structure of the anticyclonic circulation emphasizing convective transport. However, the relative roles of the advection and convection in the formation of and sustenance of the asthma have not been explored yet. So our objective in this study as follows: to characterize the level of convective outflow over the asthma region, which is important for the vertical transport of air, analyze the spatial distribution of zonal and meridional winds and temperature at different levels, demonstrate the advective and convective terms and their distinct feature, particularly over the Indian West Pacific region. So we have used the data sets, ECMWF data sets, and also the GPS radio occultation cosmic data sets. We use mainly the methodology that calculate the advective and convective term using the thermodynamic energy equation. We have also calculated the moist static energy and also the neutral buoyancy from following this Takahashi et al. So the term temperature, geopotential height. So we can see here the net heating we have plotted here during the winter and the summer monsoon, as well as the OLR and also the divergence flux. So we can see that Indian monsoon clearly marked three major converging belts: the Western Ghats, southern flanks of the Himalaya, and the tip of the monsoon depression from the central India to Bay of Bengal. Also, we have obtained this diastatic energy to look into that, how the asthma, the energy is forced into the asthma. So we have plotted here the moistostatic energy as well as the level of neutral buoyancy. Though the convections over the asthma region is there, we can see that the convection is much stronger over the Western Pacific compared to the asthma region. Here we have also looked into the wind around the asthma. So we have calculated the wind over the TJ region, the STJ region, as well as north, east, and west of the asthma region, the Tibetan Plateau side and Iranian Plateau side. So both the wind, meridional wind at the IP region, this Iranian Plateau and the Tibetan Plateau are related in the strength to the tropical easterly jet and the subtropical easterly jets. Temperature here we have shown that this is well known. We see that the temperature anomaly at 300 hectopascal, which show the asthma signature. As you go up at 100 hectopascal, it is the temperature anomaly vanish. And we have also obtained the meridional, zonal and meridional temperature anomaly, and it is here shown the pressure anomaly, which can be seen that it is over the asthma region in both zonal and meridional anomalies. Here we'll now investigated the convection and advection terms. So we have obtained that convection at 100 hectopascal, convective terms 100 hectopascal, 150 hectopascal, 200 hectopascal, and OLR, as well as advective terms. So from this, we can see that the asthma is associated with the cold advection and on its western edge, and the warm advection on the eastern edge. Further, we have investigated the time longitudinal structure of the advective and convective terms, and we have plotted that. We can see the subsidence over the western side, and the eastern side we have dominated by the convective term. In between, we have shown the asthma, the anomalies. So then we have also examined the relative roles. We have obtained this convection over India, as well as the convection advection over the cold advection over the India. They were related, and also the convection over India and the warm advection over the India. So they also was related. So the relationship between the convection and warm advection over the Western Pacific, it is observed that the convection and advection over the Western Pacific are mostly out of phase except for few years. It indicates that the wind variability at the upper trope is strongly influenced by the convection over the Indian region in contrast to the West Pacific region. So here is the summary. We have observed that the meridional and zonal winds bounding the asthma and the vertical motion underneath play a crucial role in the formation and sustenance. The asthma is thermodynamically characterized by the warm advection to the east and the cold advection to the west across the altitude, and the convection underneath, which is degraded with altitude. The convective or flow level is deeper over the Western Pacific region compared to the Indian region, even though the latter has the frequent convection during the summer monsoon season. The asthma region is characterized by the core of the cold convection to the eastern edge and the two cores of the warm advection to its western edge. The core of the warm advection in the west are stronger over the Indian region and weaker over the West Pacific region. The warm advection extends vertically from the 200 hectopascal to 70 hectopascal, where the cold advection extends from the 500 to 70 hectopascal. The cold advection is associated with the subsidence region, while the warm advection is associated with the convective region over the Indian monsoon and Western Pacific. Convection mainly dominates over the Indian and West Pacific region. The cold advection over the subsidence region and warm advection over the Indian region is closely related to the convection over the Indian region and vice versa. Thank you.
Thank you, Dr. Mehta, for this very nice presentation. I'm afraid we are a bit short of time for question, and I've just been told that the last talk of this session will be postponed to a later session because the lunch is already served.
Yeah. Thank you, Dr. Hobb, for chairing this session. So, Dr. Gopi Krishnan, are you here? No, okay. No, it's not online. It's not. You're not present online, right? No, he didn't. Okay, so we'll move on. So we come to the end of session 1, and I request our chair, Dr. Hobb, to kindly present the mementos to our speakers present here. We'll begin with Professor Greg Carmichael. Sir, could you please come here to collect your memento? No, you can stay here. Sir, please. Okay. Yes. Okay, next, Dr. Mijong Park.
Thank you for your presentation.
Dr. Dmitry Belikov. You can just go. Dr. Sanjay Kumar Mehta. And I request Dr. Krishnan to kindly give out the memento to our chair, Dr. Hobb. Thank you, sir. So with this, we come to the end of session 1. A couple of announcements. Lunch is served like outside the auditorium to the right. And international participants, please submit a copy of your visa at the reception desk by today. And the IITM Wi-Fi has the password of IITM guest all in small. Information for everybody. So the next session starts at 2 o'clock. Please assemble back here for the session 2.
Thank you. I think there's still a few people outside, but I don't think we can wait another 10 minutes. So I could go and scream over there.
Yeah.
I don't know if they will hear me from here. So it's my pleasure to co-chair this session this afternoon about the response of the Asian monsoon to volcanic eruption, wildfires, anthropogenic emissions, and potential tropospheric aerosol injection scenarios. So we'll have 3 invited talks, which will last for 20 minutes, plus 5 minutes of questions. And the first talk will be delivered by Dr. Krishnan about the role of the large volcanic eruptions on the ENSO and Indian monsoon coupling.
Yeah.
Thank you.
Thank you, Jean. Good afternoon to all of you. This is basically a work that was carried out by my student, Dr. Manmeet Singh, who is also a scientist here, and now he is at UT Austin. So this is from the 6th assessment report. We can see the increasing temperatures, mainly because of the increased greenhouse gas activities. Again, from the 6th assessment report and the CMIP 6 models, you will also see that these two periods where the episodic coolings are there, these are basically the periods of this Pinatubo eruption, and you had similar cooling during the El Chichon. So these volcanic eruptions can produce cooling, which can last for a couple of years. And now the question is, we have the Indian monsoon and we have the ENSO. These two are very complex dynamical systems. And whether large volcanic eruptions like the Pinatubo or the something like the Krakatoa, whether they can alter the coupling of these two complex dynamical systems. So as I said, the Indian monsoon, it's a very complex system set up by the thermal contrast between the Asian landmass and the Indian Ocean. We have the mighty Himalayas and the Tibetan Plateau to the north, and we have the strong cross-equatorial flow because of the north-south pressure gradient. And of course, due to the strong evaporation by the winds, which picks up a lot of moisture, which interacts with the Western Ghat orography and also the Burmese mountains, clouds are formed which release a huge amount of latent heat of condensation, which in turn can strengthen the winds. So it's really a coupled system, and also it also affects the upwelling of the oceans of the Somali coast. It also brings the nutrients to the surface. So there is a lot of ocean biogeochemistry. So the question that we are asking is, how do these, whether volcanic eruptions, how they affect this complex system? And so when we look at the time series of the All India rainfall, this is from the IMD and IITM, we can see the year-to-year variations in the rainfall. Many of these droughts, the deficient monsoon years, the ones that are shown by red, they have all coincided with several of them with the El Nino years. So whenever the El Nino events are there, like last year 2023, we also had a kind of deficit monsoon which later on made up subsequently. And whenever there are La Ninas, we tend to get wet monsoon over India. And this has been known long back since the time of Gilbert Walker, when he tried to see the predictors for the monsoon. So there is an out-of-phase variation, a seesaw variation in the pressure between Darwin and Tahiti. And so there are changes in the east-west Walker circulation. When the trade winds slow down, basically the convection shifts to the central Pacific, and then there is the emergence of El Nino, warm sea surface temperature anomalies developing in the central and eastern Pacific, and it has global impacts. Yeah, and also from the ocean now with this tau array, we also understand how the ocean heat content can evolve during El Nino years. This is from the 1997 when we had a super El Nino, one of the major El Ninos. You can see when the West Pacific is fully charged, this is in January 1997. Once the trade winds relax, the heat content tends to move eastward like a Kelvin wave. And by end of 97, you have a fully developed El Nino. This is in the ocean temperatures, and these are the anomalies. So this is really a coupled phenomena. So these are oscillatory systems. The ENSO is an oscillatory system. The Indian monsoon is an oscillatory system. And the ENSO influences the Indian monsoon. And this was way back in 1999. One of our colleagues, Krishna Kumar and Balaji and Mark Kane, they wrote a paper. They showed that this ENSO-monsoon relation has been weakening in recent times. And they also attributed this may be partly related by the warming, because of the warming of the Eurasian continent. And this may be leading to a weakening of the relationship between the ENSO and the monsoon. This is the correlation coefficient. They have done a kind of moving average. So in the recent years, this correlation is weakening. This was what they showed. And subsequently, there is an important paper that came out from the Germans, Marwan and Kurth. So they argued that instead of just looking at correlations which are linear relations, we should look at the phase variation of these oscillatory systems like the ENSO and the monsoon. And how do you look at the phase? They say they came out with this idea of the phase reconstruction to look at the self-sustained oscillatory system, oscillations. And when two systems which exhibit self-sustained oscillations, they are brought into contact, and they can actually get coupled. And this was noticed long back by Huygens, a famous Dutch mathematician, astronomer, and physicist. So when you have two pendulum clocks which are coupled through a kind of common support, which is not very rigid, then they can start vibrating, and they get into a kind of phase coherence. Because each system, each pendula, they start feeling the presence of the other. And so they came out with a technique to identify this kind of coupling of the phases, the phase synchronization, based on a nonlinear analysis. And they applied it for studying the phase dynamics of the ENSO and the Indian monsoon. What they identified was two epochs. One is 1886 to 1908 and 1964 to 1980, where these two, the ENSO and monsoon, were significantly, they had a coherence. And so what they argued was, one of the interesting findings that they came out was, some of these periods when there is a strong coherence between these systems, they were preceded by large volcanic eruptions. I'll show that in my next figure. And so they kind of speculated that whether these volcanic eruptions can be an external forcing and can put these two coupled systems into a kind of phase synchronization. So this is a method, I will not get into the details. Basically, for the phase coherence analysis, they do a kind of Hilbert transform, very much like the Fourier transform. And the phases are basically complex numbers. You have a real part and the imaginary part, and you can basically get the phase through this relationship. And also there was a subsequent study, instead of using the real part and the imaginary part, you can actually take the time derivatives of that, the y dot and the x dot. And you can use that to construct the phase difference. And I'll come to that in my next slide. So what they argued was, so you have the time series of the All India rainfall and the ENSO time series, the NINO 3 index, and you apply a Hilbert transform. And this is the kind of NINO 3 and its Hilbert transform. You can see that it is going around, it's not going around a common one single attractor, but if you take the derivative of the NINO 3 index and the derivative of the Hilbert transform, you can see that it is going around a common attractor in a phase space. That means it is having a self-sustained oscillations. And after each cycle, if you add a 2 pi, so you can see how the phase is actually propagating in time. And this shows the phase propagation of NINO 3 and the monsoon, that is the dashed line. So the solid line is for the NINO 3. So this tells that this phase propagation is slower compared to the Indian monsoon rainfall time series. The next picture, somehow this is not working. Yeah, so basically when you look at the phase, you have the phases of the ENSO, you have the phases of the monsoon. You can take the phase difference between these two quantities and plot it as a function of time. What you notice is these are the periods when there is a coherence. When you have this constant phase, it is not, the phase difference is constant, and this is one epoch. And you also find a similar epoch when there is a kind of constant phase is not changing. And interestingly, it turns out that these periods were preceded by big volcanic eruption. This is the volcanic radiative forcing. I think this was the Krakatoa eruption here, and this is the this is the Pinatubo here. I think this is Santa Maria or something. So so they kind of speculated that whether these volcanic eruptions are putting these oscillatory system into a kind of phase coherence. And by the way, these two epochs, Dr. Kripalani, who also looked at the correlations, simple correlations with running mean correlations, he found these two epochs showing even the amplitudes of these two systems were very strongly coupled during these two periods. So it's not only the amplitudes, even the phases are very coherent. So it's a kind of epochal behavior that you see. And so the question arises what is the role of these volcanic eruptions? And interestingly, in 2017, there was a paper by Kodri et al., where they used the IPSL model and looked at 5 major eruptions, Pinatubo, El Chichon, Mount Agung, Santa Maria, and Krakatoa. And what they found was typically after a major volcanic eruption, about a year later, you kind of get a El Nino-like pattern in the central and eastern Pacific. And so how does this happen? Basically, when you start with a volcanic, so this was an eruption in June, and so it basically reduces the precipitation over the West Africa, and it triggers waves, near equatorial Rossby and Kelvin waves by August through November. And so this also affects the ocean because of the changes in the surface winds. It affects the sea surface temperature and the thermocline variations. And by a year later, you can see the westerly anomalies in the they move eastward, and these westerly anomalies kind of induce a warming pattern in the central and eastern Pacific a year later. So that basically it initiates downwelling Kelvin waves and leads to a El Nino-like pattern in the fall of the following year. So these were based on the IPSL coupled model, CM5 coupled model. So yeah. So these studies actually motivated us to look, this was a work by Manmeet et al., and whether we can fingerprint the effect of this volcanic forcing on the ENSO and Indian monsoon coupling. So basically the ENSO is it is central to the seasonal forecasting of the Indian monsoon. But of course it has non-stationary relationship, it varies with time, and it can limit our seasonal predictability. However, when you are introducing these big volcanic eruptions, you are by injecting aerosols into the stratosphere, and which can stay there for a couple of years, and they can alter the incoming solar radiation, and they can affect the El Nino and also maybe the Indian monsoon by the cooling. What is its impact on the ENSO monsoon coupling? That was our idea. So what we did was we looked at paleoclimatic reconstructions, historical data, last millennium simulations from the IPSL model, and we also used our IITM Earth System model, and we conducted large ensemble targeted climate sensitivity experiments. These were very short runs, and basically we argued that large volcanic eruptions, they can promote kind of phase synchronization of these two oscillations, and this happens because of an increase in the angular frequency of ENSO. So when you have a very strong radiative forcing, the angular frequency of ENSO increases, and that was our main, and so it has implications for the improving the seasonal monsoon forecasting. So this is the output from the PMIP3 from the IPSL model. We have the Nino 3 index and the Indian monsoon rainfall, and of course we see that these two systems are going around a common oscillator. So this is based on the last millennium. This experiment was done from 850 AD to 1850 AD, 1000-year run of the IPSL model. And this period had several volcanic eruptions during this period, and this is the radiative forcing shown in this bottom panel. You can see we computed, just followed Marwan Kur paper, computed the phases of the Nino and the ISMR, and took the phase difference. You can see some of these periods where you can see a kind of constant in the phase value. They are kind of preceded by volcanic eruptions. So this is based on large 1000-year simulation. And we also isolated periods, because ENSO can happen even in the absence of a volcanic eruption. So we identified those periods where you have an El Nino-like pattern, but which did not have volcanic eruptions in the last 4 to 5 years in the preceding past. And we also obtained El Nino periods from the model simulations when it was preceded by a volcanic eruptions in the last few years. So we did a kind of quantile mapping. What we find is, generally we find higher ENSO angular frequency following volcanic eruptions. So there is a higher propensity for ENSO to occur if there is a volcanic eruption in the preceding years. And so there is an increase in the angular frequency. This is our main point. So if you have a kind of volcanic eruption, the oscillations can get faster. The frequency of the oscillations can get faster. And so that is the idea. And so to test this idea, what we did was at the same time, our group in IITM was working on the CMIP6 model experiments for the IPCC assessment report. And we had this IITM Earth System model. And our group, people had also, Ayantika and Manmeet, they had already put the aerosols in the model and also the volcanic aerosols. We thought, why not we test it? So by 2017-18, we had a radiatively balanced system. And so using this model, what we did was we designed a large ensemble targeted sensitivity experiments, basically focusing on the Krakatoa eruption, which happened in 1883. And actually, when you see this particular case, it did not lead to an El Nino after the Krakatoa eruption. I will come to that point. So what we did was, because there was a long kind of cold phase of the PDO that was going on this time, and we had a 100-member realization. We started from different initial conditions because we are looking at the next few years. It also, the evolution of the coupled system depends also on the initial state. So we wanted to have different kinds of initial state. We had 100 members, out of which 29 corresponded to the cold initial state, that is a kind of La Nina phase. 47 were corresponding to the neutral initial conditions, ENSO neutral, and 24 were warm initial conditions, like a El Nino kind of state. And so we started the run from 1st of January 1883 and go through until 31st January, December 1885, and see what happens during this 3-year run. And so member by member, we see out of this 29, 7 of them from cold to cold, it went transition to a cold. 9 of them transitioned to neutral, 13 of them transitioned to a warm. Similarly, we do the same thing for the neutral and similarly for the warm phase. And we went on to take all this cold to cold, cold to neutral, we take only the cold, the transition to the cold phase. Here from the cold to cold, we have 7, neutral to cold is 11, and warm to cold is 8. So totally, the cold transitions, we have 26 members. So with these 26 members, we also increase the strength of the radiative forcing to 4 times the Krakatoa. Then see what will happen for these cases. And similarly, we looked at the cases that transition to a warm phase, cold to warm, neutral to warm, warm to warm, and then we reduce the forcing to 1/4 and see what happens, just to see the impact of the strength of the volcanic forcing. So this shows the difference. This is the difference. We take the member-to-member difference in the Nino 3, and when we plot these experiments, the delta Nino 3 index as a function of time from, we see that typically after, when you start from the neutral or warm ICs, a year later you are transitioning into a warm phase. And when we look at the kind of spatial pattern of the SST and the surface air temperature, so a El Nino-like pattern appears. And of course, over the land areas or the Eurasian continent, you have cooling, which is not surprising. And there is a reduction in the shortwave radiation forcing at the surface. So when we are cooling one of the hemispheres relative to the other, the studies have shown that theoretical argument shows that the ITCZ shifts to the warmer hemisphere. So precipitation increases in the southern hemisphere, and there is a decrease of precipitation over India and in the northern hemisphere. And this pattern actually gets amplified when you increase the radiative magnitude of radiative forcing to 4 times. And if you reduce it to 1/4, 0.25, and also the SST warming in the east also strengthens. But once you reduce the forcing, strength of the forcing, the precipitation anomaly, the magnitude reduces. And we also looked at other proxies. We had various paleoclimatic proxies from the ENSO, and we had 14 proxies, different proxies of ENSO, and we had 11 Indian monsoon proxies. We did a Bayesian analysis looking at the conditional probabilities and what will happen when you have a volcanic eruption and when you don't have a volcanic eruptions. Similarly, if you, and also we looked at PDOs preceded by volcanic eruptions. I'll not go into the details. So in general, we find that the coupling, but that means you have a El Nino and you have a drought, or you have a La Nina and a wet monsoon. So this is the conditional probability. So this is the same conditional probability if provided it was also preceded by a volcanic eruption in the last few years. So clearly you can see that these are the different 14 El Nino indices, and these are the 11 monsoon indices. Clearly there is an increase in the probability of the ENSO monsoon coupling when there is a when it is preceded by a large volcanic eruption. So there are other things, so I will not get into the details because of the limited time. So what is its implication for the monsoon prediction? This was the monsoon mission model developed by IITM, MMCFS2. This is the 1992 example, and this is one of the best models that we have, state-of-the-art models, which shows that the skill of the model forecast is probably the best. And we can see this is for 1992, this is the observed rainfall anomaly, and this is the IMD operational forecast, that is the MM2 model, and this is the NCEP. So clearly the model is unable to capture the blue line, it is showing out of phase. So prompted by this, we thought let us do a small experiment, and we looked at the Pinatubo eruption. These are the aerosol optical depths at 550 nanometer. This is stratospheric aerosol. This is the El Chichon, and this is the Pinatubo. This is showing just the latitude variation of the optical depths. And so you can clearly see that the scale of the anomaly, it's almost covering the entire north to south in both the hemispheres. And interestingly, we had two experiments. So this is the IITM ESM all forcing experiment. It has greenhouse gases, it has anthropogenic aerosols, it has also natural volcanic aerosols. And this is the blue line this is for the 1992. We have the observed CMAP rainfall anomaly, and this is from the IITM all forcing experiment. It shows a very clear decrease. Of course, two hindcast experiments we could not repeat for 1986 and 2000 at that point of time. We further had only experiment with all forcing, another experiment no anthropogenic aerosol. So only we had the volcanic aerosols. So again, if you have only the volcanic aerosols, you can see that there is a big reduction in the precipitation. These were 30-member simulations. So it looks like there is some predictive skill by using this stratospheric aerosols coming from the volcano. It can lead to this is the precipitation anomaly, this is CMAP observations, and this is the IITM ESM anomaly. You can see an increase in the precipitation to the south of the equator and a large reduction over the Indian subcontinent. So the question is, there has been now this discussion morning also about the Hunga Tunga eruption that happened in January 2022. The morning there was a slight confusion.
Excuse me, sir.
Yeah.
We have 2 more minutes.
Yeah, I'm winding it up. Yeah. So this eruption actually threw a lot of aerosols that went into the stratosphere, and also water vapor, which also entered the Earth's stratosphere. And when we look at the ocean Nino 3 index, again this is from NOAA, so 2020, 21, 22 was a kind of a triple dip La Nina, 3 continuous La Nina events. Then there was a quick transitioning to El Nino-like pattern, which lasted for about a year. And now again we are slowly entering into a La Nina phase. So these transitions are happening very fast. And whether the ENSO oscillation, the angular frequency has increased following, that's one of the question. And this is based on this is the latest picture of the Nino 3 SST Nino anomalies from different Nino regions. You can see the latest April 2024 and May 2024. You can see that cold anomaly is developing in the Eastern Pacific already. And but if you looked at the previous, that is from December 2023 to January 2024, the pattern was completely different. You had a very strong La Nina, El Nino-like pattern in the Central and Eastern Pacific. So the change has been very, very quick. And now, in fact, in the coming, I think by July, August, September, it is projected that this is the outlook, that La Nina is projected. And now what happens to the monsoon? 2023, we had a kind of although the all India monsoon was about -6%, many parts of India, North India and even peninsular India, rainfall was deficit, especially in the first 3 months. Only it made up mostly in the month of September. And these are the, this is from the SAGE satellite, 755 nanometer. These are the aerosol optical depth. We can see at different latitudes. So the question arises, what was the role of these Hunga Tunga aerosols in affecting the ENSO monsoon coupling? So I'm just posing this question. It appears from our study that the Indian monsoon can be better predicted after large volcanic eruptions, especially in the S2S timescales. This is basically, there's a synchronization of the ENSO and the Indian monsoon, and there's an increase in the angular frequency of the ENSO following these large volcanic eruptions. There are also other implications in terms of geoengineering implications, because it's going to shield the, these aerosols are going to cut down the solar radiation. And of course, it can reduce the kind of, temporarily at least, the human-made greenhouse gas warming, but it can have other impacts. And there could be other issues, ethical issues, and clearly a lot of work is needed. And so I think with that, I just want to end my talk. Thank you very much.
Thank you. I'm sorry, we don't have much time for questions, so we'll move to the next talk.
Okay.
Actually, the transition is good since you talk about geoengineering. Yeah. Dr. Simon Tilmas will be talking about stratospheric aerosol climate intervention efficiency, impacts, and uncertainties.
My name is Simone Tilmes, and I'm from the National Center of Atmospheric Research. I will talk about stratospheric aerosol climate intervention, or geoengineering, and I want to talk a bit about efficiency, impacts, uncertainties, but also risks. And I do give a more general overview. We will have more detailed impacts also on the Asian summer monsoon by the following speaker, Bala. And so to start with, this is just a slide. I mean, we're all aware that we are seeing increasing temperatures, increasing climate risks. And this is just a nice chart that I found that NOAA is putting out every month. It's actually global surface temperatures extremes since the 1950, and we see that we are in the 11th consecutive warm months now already. And with that, of course, people here, especially in India, have experienced the heat waves. They're getting stronger, they're getting worse, and there are more fatalities, and especially countries that do not have air conditions and other ways to adapt to climate change. And so where are we going? Well, we do know that we do have to drastically reduce the greenhouse gas emissions. What we see here is a chart of projected greenhouse gas emissions in the future. And so if we really want to get down and keep temperature targets at or below 1.5 degrees C, we will have to do drastic measures, much more than we're already doing, and phase out at least around 2050 or 60 the greenhouse gases, and also include negative emissions. I will talk more about that. But current pledges are just not there. We know that temperatures are increasing, potentially up to 2.5 degrees Celsius. And with this, of course, also the impacts on climate change. And there's also studies recently by Jim Hansen showing that we may actually not, what we often assumed, have a linear increase in temperatures, but there may be an accelerated warming. And this comes with the fact that we are actually globally, and also especially over China, have decreased sulfur emissions a bit. And those aerosols in the troposphere have in the past cooled the climate, will contribute to additional warming. And so, yeah, we may already, with this accelerated warming, be really close to the 1.5 degree target. The impacts and risks are increasing with increasing global greenhouse gases, as we know, and that is endangering more and more vulnerable societies and also ecosystems. And this is really the motivation. Why do people think about more geoengineering, climate intervention approaches? So
what are climate solutions? Obviously, mitigation is the top one that we have to do. We have to address the source of the problem, reducing greenhouse gases in the atmosphere. That also means we're looking a lot now into negative emission technologies. There's a lot of money research going on in these technologies, pulling out carbon out of the atmosphere through, for instance, afforestation, direct carbon capture, alkalinization of the ocean, and so on, which also requires, of course, storage of these CO2 that is pulled out to be efficient. But that is known to be very slow and will take a very long time. But while we're reaching already unprecedented temperatures and impacts, people think more and more about potential other approaches, which is the so-called solar radiation modification, which includes the stratospheric aerosol intervention, which I will focus mostly on in this talk, meaning that we actually want to increase the aerosols in the stratosphere and therefore the reflectivity of the planet, so the sunlight will be affected. And we saw that just in the talk before. We'll see more cooling. But then there are other approaches, space mirrors, brightening the clouds, so marine cloud brightening, and also surface reflectivity systems. The other part, of course, is reducing impacts and suffering through adaptation, but not everybody has the same means and ways to do this in different countries. And then also it is much harder for ecosystems to adapt. So we just heard about volcanoes. Volcanoes in general cool the climate. And of course, there's a lot of variability, and we saw the connections to the ENSO in the previous talk. But we did estimate that from regressions and other things that Mount Pinatubo have cooled about 0.3 degrees the surface temperature. So the idea is really that volcanoes may be used, or stratospheric climate intervention can be used similarly. And what you can see here is a nice video from Mike Mills. I mean, this is a model simulation, not a video, for aerosol optical depths. This is after the Mount Pinatubo injection. What you can see is a tropical volcano can, like Mount Pinatubo, injected large amounts of aerosols in the tropics. And then we have a lot of AOD first in the tropical regions, but very quickly you saw that the AOD globally is increasing drastically, which then results in the global cooling. And of course, after a few years, after a couple of years, this AOD will decline again. If we want to apply stratospheric aerosol interventions, what we do have to do, of course, then is provide continuous injections into the stratosphere, meaning annually certain amounts have to be injected. And also, we don't have to inject in the tropics, or at least at the equator. We can decide where to inject. We can inject at different latitudes, so the aerosol optical depth or the aerosol burden is more linearly distributed, that we get a more even cooling. There's a lot of studies going on now. What is a more optimal way to apply the stratospheric aerosol injections? And yeah, this is long-term application, so it means that there will be very different effects than just from one-term injection like volcanoes. Those have to be all looked at and clearly investigated. But currently, this method is thought to be the most effective global method, and we also see in models that we actually see a cooling. But how much cooling do we actually, how efficient is stratospheric aerosol intervention? Do we know how much cooling we can achieve? And even from Mount Pinatubo, we are not quite sure how much aerosol we have injected. We can see very similarly that models show quite a bit of a large difference, a factor of 2 on how much cooling can be actually achieved by the same amount of ejections. So here, the models injected 10 teragram SO2 per year, and you see that one model is achieving only less than half a degree of a cooling, while other models showed over 1 degree of cooling. And that's, of course, a bit of a concern, because we do need to understand how much cooling we can achieve. It means it will differ in terms of impacts. The more aerosols in the stratosphere impact the ozone layer stronger. It will impact the climate change stronger. And also economically, it may be very different costs and technical, in terms of technical aspects. If we look at some studies now that have been done in recent years, it shows that really this cooling could be caused in parts by how well models can actually simulate the aerosol burden in the stratosphere. So if we inject these 10 teragram of SO2 or 5 teragram of sulfur, a model, for example, here, this is a CSM model, it has a certain amount of burden of aerosol that stays in the stratosphere that leads to a stronger cooling than another model that shows much less of a burden increase for the same injection amount, leading to a lower cooling. And so we already see there's a lot of uncertainty in our knowledge, and that comes back to how do we prescribe aerosol? What microphysical models are we using? And that's probably only one aspect of the question and uncertainty. So coming a little bit, I want to talk about the feasibility technically. Yeah, people have thought about this. And Robert had a nice paper with a figure here. There is options, how do we do it? Maybe with aircraft, but most aircraft don't even go as high as what we need, like 20 kilometers, so new aircraft would have to be developed. There are other options that are much less possible, like balloons. We cannot really transport a lot of mass into the stratosphere with these parts. But in general, in terms of costs, people have estimated that it could be up to maybe $1.4 billion a year for 1 teragram of SO2. And if you think about that, we need 10 teragram SO2 about to cool 1 degree. So this can actually become more expensive than people always say it is cheap. But it's not that cheap for a country or for people to come up with 10 to 20 billion a year or even more. That still seems cheaper compared to the risk and effects of climate change. But anyways, how do we think about geoengineering or applications of these methods? Often it's talked about like a peak shaving scenario used as a stopgap measure, basically. So if we think about increasing greenhouse gases here as a business as usual, this is temperature on the y-axis. What we are doing, we're trying to mitigate as much as possible, reduce the greenhouse gases, and we adding a lot of potentially CO2 removal in the future. The idea of SAI is to really cut the peak of an increase of temperature above the level that is not what we want, so maybe above a certain temperature target of 1.5 degree, and therefore phase in and phase out this technology. But of course, this is quite an optimistic scenario because we will have to actually know or predict the future pretty much. We need to have strong carbonization. We need to have governance and ethical frameworks into place that we agree on how this may be done, what targets may be followed. And there's a lot of work of starting those ideas, but there's really no governments in place at the moment. And of course, we need assessment to really understand what the risks and side effects would be. We don't want to make it worse if we apply those methodologies. So people are thinking more of these strategies, and you could think that there's more ideal or proactive strategies could be done, but then there will be the question, what temperature target do we want to agree on? You know, we could maybe keep temperatures at 1.5 degrees. We may even cool the temperatures further down, which may be desired for some countries rather than others. But we also have to think about that this is quite, it seems to be more unrealistic. And many people think that it's much more likely that there will be more reactive application of this approach, that some countries or some corporation may start this and do not really think about the global good, but more about their own benefits. Which can be a big problem. If we think about a more coordinated approach, we can think about injecting in different latitudes that's most beneficial, more even cooling. But if a single nation or somebody would start at a single latitude, this can have large implications. So depending on how we apply actually these interventions, we can get very different impacts. And this is just one example, like effects on the tropical convergence zone. So if we think about that from the current mean, climate change will shift this, the ITCZ in part. Different injection strategies could make it worse or could make it better. So it's really important to think about these impacts depending on how these strategies could be applied. I will talk briefly about models. So obviously we use various type of complexity in climate models to study this. But if we really want to understand the full impact of climate intervention, not only the injections, but also the impacts on, all the way to for societies, we need very comprehensive Earth system models. And what we are using is the whole atmosphere community climate model, what Mi-Jong had introduced, that has a lot of couplings. But, so these models really need to include both troposphere and stratosphere chemistry, well-resolved cloud aerosol and chemical processes, interaction and coupling to the surface models like the land and the carbon cycle, sea ice and land model, because of the feedbacks that we have to study with these approaches. We also have to go down to much larger scale, smaller scales from the global to the regional, and to understand what are really the effects on water, food, and health. And also important in this regard is the evaluation of our models. We need to have observing systems into place to really understand also how well do we simulate volcanoes, background aerosols, ship tracks, and so on. And so this is just an overview of model simulations that we have done at NCAR, and this is really something we did for the community. People can use it to really assess and understand what are the impacts of climate intervention. We did 2 main simulations, large ensemble simulations, the geoengineering large ensemble simulations, which is a 20-member ensemble. It's an 8.5 background or baseline scenario, and then we apply SAI, stratospheric aerosol injections, over the period up to 2100, and you need to increase the injections more and more, of course, but this is really there to understand, to get a large forcing to understand the signal to noise of the injections, so really figure out what are the processes and what can we learn from those large interventions. Well, there are also more smaller scale interventions from this ARISE project. That is a 10-member ensemble. And so we are happy to give those to the community. We have analyzed those, and I'll just give a few examples for impacts due to the short time. This is, for example, a study by Isla Simpson in 2019. She used this large ensemble, so this lens simulation, 8.5 scenario with increasing forcings. And what you can see here is that this is precipitation changes versus global temperature change for climate change. We see the stars here, so over central India in June, July, August for precipitation in this area. Increasing temperature will increase the precipitation, but when we apply stratospheric aerosol intervention and counter the temperature, we do see an what do you call it? Well, I forgot. But we see a decrease in temperature, in rainfall, sorry, with the increase in the counter of the temperature. So very small application may not be actually having a strong impact, but the larger the application, the more rainfall may decrease. This is different at other places. For example, here over Amazonia, we see that a climate change will reduce rainfall pretty drastically right away and then continue to decrease, while stratospheric aerosol intervention may actually reduce that strong decrease a little bit. So it could be beneficial in some parts, and in others it may not. That's important to know. The other thing is that we also need to think about model differences. This was just one model. Now we had performed 2 different cases, the same simulation, basically the same RCP 8.5 scenario or similar SSP 8.5, but with 2 different model versions of the MECHAM model. And what we can see that in the end of the 21st century was very strong climate intervention application. We see the strong decrease in rainfall, as we have seen earlier in the previous slides over India. But another model is actually not showing that so drastically. So the question is, why is this? Do we actually understand what is going on? And so in the last year, Ashutosh Asharai, who has a poster out here has really looked more into the processes that lead to this decrease in the rainfall over the Asian summer monsoon. So we need to understand what different factors actually control this and why are the models showing different things. What is different between those? So that's quite interesting to look further and understand this. And this is also really important if we want to apply that we understand the different parts. And so one other thing is, of course, just rainfall is not a climate impact. There's many more things we have to look at. We had looked at effects on the ozone layer, but of course, aerosols in the stratosphere change the direct to diffuse radiation. This is a strong factor that can impact ecosystems. Temperature, of course, is a very strong factor in many places, but then rainfall and other things, potential acid rain distributions, changes in UV, can have a large impact too. There's a nice paper that really summarizes all these things that have to be looked at and hasn't yet in recent years. One more slide just quickly on the risks. There's much more to think about. The physical impacts is one thing, but what if we really wanted to go to a peak shaving scenario? What if there's a large volcanic eruption? Can we counter this properly? What if we have unexpected warming, potentially methane leaks, or other reasons why greenhouse gases would accelerate? And then, of course, the societal risks, moral hazards is one important part that we may just not reduce, or may reduce the mitigation incentive after starting. There's a lot of papers on question on risks, security risks, potential even increases of war or decreases of war, a lot of uncertainty. And finally, this is just a paper that we had recently, or have now in revision, that talks about really what do we need to assess, what are the assessment criteria for stratospheric aerosol interventions and scenarios and strategies. And we concluded that we really need to include not only the physical science, but also the social science considerations. So we need to consider technical and design requirements, responses and impacts, as well as societal considerations that are listed here in much more detail. And this really requires an interdisciplinary assessment and international collaborations to get there. And with this, I stop, and I hope I'm still in time for some questions.
That's perfect. Yeah, we have 5 minutes for questions. So, do we have any questions?
Simone, you mentioned the models. Do you wish to comment a little bit on what aspects of the model are particularly sensitive if you think about climate intervention?
Yeah, so one thing is, of course, the aerosols. How do we represent aerosols in the climate, in the models? And often aerosols are prescribed or parameterized quite simply. We have various forms of, just a bulk aerosol model versus a modal aerosol model, sectional aerosol model. So that part, you can get large differences, as I have shown, in how much burden you achieve through a certain injection. That's one thing, of course. But then the other part is also, it's important that we get really the interactions with the chemistry to simulate the dynamics, like aerosols induced heating in the stratosphere that changes the dynamics, changes ozone. Those things, if we don't have the coupling, many models don't have that coupling in the stratosphere. And then that's where we lack in really understanding what the effects would be. And then all the way, as I said, to the surface coupling also. We often don't even consider the carbon cycle being interactive. And that's also impacted by this type of intervention. Does that answer it about? Okay.
We have another
Hello.
question.
Yes, I would like to ask one thing. For geoengineering you were talking about, and after large volcanic eruptions, the temperature indeed is reducing a little bit. But the previous speaker also mentioned there is a chance of highly likely to be an El Nino.
Yeah.
And El Nino causes huge warming. And it happened after Hongatungi eruption. Recently, there was a huge warming. And even after Pinatubo and El Chican volcanoes, the similar things happened. And what is your opinion on that? If you were trying to cool the temperature, and if it is on the other way around, it is acting on the other way around.
Yeah.
And how do you implement that, and how do you think about those things? And volcano implications are huge, non-linear effect, not only linear effect. There are ozone depletion in the high stratosphere, and many other implications are linked together.
Right.
And you are only focusing on one impact just to reduce the temperature for next 1 or 2 years. And those implications, did you have in mind, or all the scientific community, do they have those considerations in mind before applying any geoengineering?
Yes, certainly we do have to look at all of those implications. And that's why I'm talking about an assessment that has to be really interdisciplinary, that we take into account all those different questions that a lot of people, especially communities that haven't looked at this question, they can look at the specific impacts and really contribute. So it's really important. We do have communities and researchers look at this and research the impacts. One thing is, yes, we do see that, for example, after volcanic eruptions, we see an increase of temperature over Eurasia in winter, for example. That's a key thing that we also see with stratospheric aerosol intervention. But we're trying to understand why. And often it leads, one thing that causes potentially ENSO changes or other things is also the heating of the aerosols. So people already think about, what if we would use other aerosols that don't heat the stratosphere? Will that actually change the impacts as well? And so there are many aspects, all the impacts and various local and regional changes depend so much on how it is applied and what material is used. There's even much more research to be done to understand all that as well. How do you get the most optimal application, right? And is that even something we can understand from our climate models? Thank you very much.
We have one question online for you, Simon. What is the reason for increased rainfall over southern India due to stratospheric aerosol injection?
Right, so what I was showing was really just one model study and specifically how it was injected, right? So another model study may not see that specific impact. But unfortunately, you're online because we have a really nice poster this afternoon that explains a little bit connection between changes in wave patterns in the stratosphere as well, and then the impact on rainfall in the specific model. So that's how much I can say for now.
Thank you, Simon, I think. Anyone? Thanks again.
Thanks.
So our next speaker will continue talking about geoengineering. Dr. Bala Gadvin Dasami from IISc Bangalore will talk about how would stratospheric aerosol geoengineering affect tropical monsoon rainfall.
Oh, is it not? No, it's not on yet. Pointer. Okay. Which one? This pointer. Okay. Okay. Yeah, I must first thank the organizers, Krishnan and Swarna, for inviting me to this conference. And in fact, most of the story has been already told by Dr. Krishnan and Simone. But anyway, I'm happy they didn't cover this particular simple aspects. I know, I mean, this conference, and I'm seeing a lot of complex process-based studies and also much more complex issues. So what I'm actually going to do is try to see, at least qualitatively, try to get some of the basic physics behind how SRM, I mean, basically in this case, solar radiation modification, how it could affect the tropical monsoon rainfall. So most of this work is, of course, not done by me, mostly by my postdocs and students. I thank all of them over the last 10 years or so. And you know, since we are anyway sitting in a small university, we don't have big resources like what IITM has or what Simone has. So most of our results are based on really very simple configuration of the climate model, basically the UNCAR CESM model. Only slab ocean version. Basically, we only take the mixed layer ocean so that we can get some understanding of climate change. And most of the results presented here are also equilibrium climate change. So this basically helps us, what I would say, isolate some of the processes. So for that purpose, for that particular scientific purpose, what we do is mostly idealized simulations where the forcing is large, because we don't want to get bogged down by the signal to noise ratio, signal to noise problem. I know the real world, of course, has tremendous, we are always living with the noise, but here we want to get some basic understanding. So we do basically use large forcing experiments, okay? So I think it's sometimes very good idea to give the conclusions up front so you know what is coming, right? So I am going to only talk about 3 mechanisms relevant to stratospheric aerosol intervention, or injections, and its impacts on tropical monsoon. This does not mean that there are no other mechanisms. This is what we have so far studied, and we are also currently investigating. I am sure there are much, much more than this, but this is something where we have now a little bit better understanding. The first one is basically what is really going on. One is the interhemispheric difference in AOD. So this appears to be a very important aspect if you do solar geoengineering. So basically, it could disturb the latitudinal position of ITCC and the monsoon. Already the previous speakers have a little bit talked about this, but I will just show results from our own study, right? So the basic science behind that is basically like in the seasonal cycle, ITCC basically would move into the warmer hemisphere. So that means if you put aerosols into one hemisphere fully loaded and other hemisphere leave it, this is an extreme example, the particular hemisphere would cool a lot, so the ITCC would move into the other hemisphere, right? So this can be avoided, as Simone talked about, by injecting aerosols at multiple latitudes. And this has been there are several papers on this, hundreds of papers on this right now. So, if you are interested, I would say, you just go and look at several papers authored by Simone and others. And the next important thing, this is probably the first one, global mean AOD, right? For instance, carbon dioxide increase, it basically causes global warming. Under global warming, the global hydrological cycle actually intensifies. So similarly, if I just look at what would aerosols do, particularly reflective aerosols in the stratosphere, they are going to cool the surface. So when you cool the surface, this is just the individual effect of putting aerosols. So the aerosols would actually cause a decrease in, if you just consider aerosol, it's going to cause a decrease in monsoon rainfall. This is a very simple fact, right? But interestingly, there is a science here that is hydrological sensitivity. That is basically, let's say, global mean precipitation increase per degree of global warming. It is actually slightly larger for the aerosols, particularly the reflective aerosols. So because of that, what's going to happen is, if you actually perfectly offset global mean surface temperatures, the global hydrological cycle actually will have a overcompensated kind of weakening, right? So many people have suggested that, okay, let's not really offset the global mean surface temperatures totally. Instead, let's do a moderate geoengineering. So people have always come up with solutions here. The last one here is the height of the aerosol. So there are not much studies in this. In fact, Simone has done some work where she has injected aerosols at 1 kilometer above the tropopause or 5 kilometers above the tropopause. But I think the problem with that kind of study is that million things going on, complex processes are going on. So it's very hard to delineate, the single aspects of these aerosols. So what we have done here is we have put same amount of aerosols at 2 different heights or 3 different heights and study the precipitation sensitivity. And interestingly, we find that precipitation shows really very little sensitivity to the height of the sulfide aerosol layer. So remember, this is again, big simplification of the problem, because in this particular study, the aerosols were prescribed. They were not injected. When you inject, of course, the aerosol height is going to change because of the sedimentation and et cetera, right? So we have a mechanism we understood this now. This is because of the compensation between fast and slow responses in precipitation when the height of the aerosol is altered. So I will actually come to what is, this explanation of what is fast and slow later on when we discuss this third mechanism. So the mechanism one, I'm actually going to really oversimplify this problem, but I think sometimes oversimplification is really important to understand at least what's going on, at least qualitatively. So we may not understand the quantitative number exactly. That's where you need multiple ensembles and etc., multiple models, etc., right? Okay, mechanism one is change in the interhemispheric difference in aerosol optical depth. So this I already have actually told you what it is. So basically, if you put most of the aerosols, this is again very highly idealized schematic. If you put reflective aerosols mostly in the northern hemisphere, the ITCC basically shifts towards the south, right? So in fact, there are studies. In fact, we have done this particular study. If you put too much, let's say, absorbing aerosols in this part of the hemisphere, then basically actually ITCC moves up into the northern hemisphere. So basically, this is basically based on some really planetary energetic principle, and the idea is a simple rule of thumb is ITCC moves into the warmer hemisphere. So this happens in the seasonal cycle, and also this happens irrespective of the forcing mechanism that causes the interhemispheric differences in basically the radiative forcing or something like that. So I took this example for this particularly from Jim Haywood. They had a paper in 2013. Basically, they were looking at actually the North African monsoon, right? And I just quote one result from that. That is basically in El Chichon in the 1980s. It basically caused an additional AOD, basically additional interhemispheric aerosol optical depth difference of about 0.07, and this basically led to a major rainfall deficit in the Sahel. So that basically justifies the previous schematic that I have. So have we looked at? So basically in our group, we had postdoc Krishna Mohan, I think some years back. So this paper, of course, got published in 2022. So basically, we took simulations from CESM. These were simulations were performed at NCAR. So here, in these simulations, aerosols were actually injected at different latitudes, single latitude injections, all right? So what we found was there were basically about 5 experiments where aerosols were injected at either equator or at 15 degrees south, 15 degrees north, or 30 degrees south and 30 degrees north, okay? So when you do that, what happens is you could create the big gradients in AOD between the two hemispheres. So in these studies, in fact, as I quoted here, we found the aerosol gradient of about 0.2 were created between the northern and southern hemispheres. So this was really catastrophic when you do this. So this paper was published in Climate Dynamics in 2022. So basically, we took these 5-6 simulations and looked at a little bit, diagnosed them. So I just show only the key results here. So what actually you see here is basically this is the injection case for AOD for 30 degrees south, 15 degrees south, equator, 15 degrees north, and 30 degrees north. So what is shown here is the interhemispheric AOD difference. So in this particular case, you really create a very big AOD gradient between the two hemispheres, close to 0.3, right? But you can see the aerosol is kind of almost same in the zonal direction. There is not much inhomogeneity along the zonal direction, but there is a huge asymmetry between the two hemispheres. So the asymmetry is slightly reduced in the case of 15 degrees south, and then in the equatorial case, you pretty much produce very little interhemispheric AOD difference. Okay, all right. So you exactly have the opposite when you inject the aerosols in the northern hemisphere. So let's look at the zonal mean precipitation. So here the results are very clear. So you can see in the case of southern hemisphere injections, the ITCC moves into the northern hemisphere, and in the case of northern hemisphere injections, the ITCC moves into the southern hemisphere. So there are, basically you see a major disruption to the tropical precipitation, monsoon precipitation, all right? So now let's look at what happens to India. So India, in fact, you can see in the case of 30 degrees injection, the rainfall almost decreased. This is mean rainfall. We are not even looking at the annual variability or anything, just a mean. The mean decreases by almost 30%, and in the case of 15 degrees north, you get about 20%. And in the equatorial case, you can see very little disruption. So because in the case of equatorial injection, the aerosols kind of uniformly spread around the planet. And of course, northern hemisphere, Okay, these are, yeah, okay, I'm sorry. This is, I think, yeah, right. So the 30, and this is, so this is the greenhouse gas induced change. Anyway, the simple story is that, when you create huge interhemispheric differences in AOD, you can really disturb the monsoon precipitation. So, there were actually some years back suggestions of let's not do, this SRM, this SII all around the planet, just do only for the Arctic. So we had a paper some years back in 2018, which looked at actually what if you do inject aerosols only in the Arctic to cool the Arctic, right? So obviously you are going to have major disruption. So this is the precipitation plot for the Arctic geoengineering, where basically we inject aerosols only northward of 60 degrees. So you can see again major disruptions to the monsoon region. So basically you have a decrease in rainfall in the northern hemisphere monsoon regions and increase in the for the southern hemisphere. All right. So I think one thing I really want to emphasize is this is not unique to aerosol forcing. I think what I would really like is look at, for example, this is a paper we had in 2015, where we basically looked at if you do deforestation in different latitude bands, how that's going to affect the Indian monsoon. So I know many of us are very well aware of the tropical influence on the mid-latitude dynamics. So this is exactly the reverse of that, where you can see how what happens in the mid-latitudes actually affects the tropical dynamics. In fact, when we first looked at this figure in 2014 or something, I just couldn't believe, and it took a long time for me to figure this out. Of course, some studies were there along that line at that time. So this is a case where the northern hemisphere boreal region, you remove basically forests. So you can see precipitation decreases in the most of the northern hemisphere, and in the southern hemisphere increases. This is global deforestation, and this is temperate, because mostly temperate region is, the land region is in the northern hemisphere. Again, a similar change you see. But on the other hand, you see tropical deforestation. There is very little, hardly any change in the ITCC area. Okay, now I think what we want to do next was a little bit quantify this. We really wanted to, at least in one model, look at per unit AOD difference between the two hemispheres, how much the monsoon region will be disrupted. So we designed some experiment, very, again, idealized experiments. These are the different aerosol distributions. So this is a uniform case, and this is, let's say, Antarctic, where aerosols are maximized in the Antarctic. Arctic, aerosols are maximized here. Tropical, more like a parabolic pattern, and this is a polar case. So basically, we want to actually introduce both symmetric and antisymmetric cases between the two hemispheres and see how this affects the tropical mean precipitation. So of course, this is the global mean temperature changes. So there are some differences. I think I don't want to get into the global aspects of that right now. But let's just look at this particular precipitation that is relevant to the Indian region. So what you see here is these are the top three, or these three are the symmetric cases where the AOD, there is no gradient in AOD between the two hemispheres. But in these two cases, you introduce AOD difference. So you can see here, yeah, so basically in the Arctic case, precipitation reduces in the northern hemisphere and increases in the southern hemisphere, right? And exactly opposite of that. So this paper came out in 2023. So yeah, so basically here is that little quantification. So we basically we looked at 4 monsoon indices, that is Indian summer monsoon index, northern hemispheric monsoon index, where basically you total up all the precipitation in the northern hemisphere monsoon regions, and then add up all the southern hemisphere monsoon region precipitation, so that you have the southern hemisphere monsoon index, and then when you sum up northern and southern, you get tropical monsoon precipitation index. So you can see here the quantification. So basically for India, Indian summer monsoon index, it decreases by approximately 8% per unit. Unit in this case is 0.1 AOD gradient between the two hemispheres. And this is for so these two regions, basically, these two indices are heavily affected. And as expected, you can see the southern hemisphere monsoon index, it actually increases because the precipitation bands move to the southern hemisphere. And the total is very little change here. But there is a change. You see this here? So this is the change that is negative, that is introduced by the global mean. So when we were working on this paper, we didn't really look at the global mean AOD impact. So we wanted to look at that one. As I said already, it's a very simple thing. So when you cool the planet, you are going to basically weaken the hydrological cycle. But the problem is, the hydrological sensitivity is larger, the magnitude of hydrological sensitivity is larger for any solar-related forcing compared to the greenhouse-related forcing. So because of that, I'll just only show this result for this simple purpose here. So this is the warming when you double the atmospheric CO2 concentration in the slab ocean model. And this is basically, so this is when geoengineering is done on that same climate. So you can see that you are nearly offsetting the global mean temperature changes. Now, this is the precipitation change for doubling of atmospheric CO2 concentration, but you should have a 0 precipitation change here, but you don't have that. Instead, you actually have 2.3% reduction in precipitation. That's because the hydrological cycle sensitivity is larger for the aerosol forcing. So, that's one reason people have said, okay, let's not offset completely the greenhouse-induced forces, right? So now I think based on this work, I think what we thought was, okay, let's basically put these things together and try to quantify precipitation changes in terms of two parameters. One is interhemispheric difference in AOD, and other is global mean AOD. So here is the simple formulation. So we have to calculate basically, precipitation change is a function of two quantities, global mean, the difference in AOD, and these two coefficients. But remember, these two coefficients actually could be very different for different monsoon regions as well as different monsoon indices, right? And all right, so I'll just quickly go into the result here. So basically, in fact, so this is very similar to the previous result I showed you for 4 different monsoon indices, how per unit change in AOD difference between the two hemisphere affects, right? And then this is basically the global mean AOD change, how it actually, so this is not insignificant. You can see precipitation change over India per unit increase in global mean AOD could be almost about 6 or 7%, right? So one thing you can see here is, here the southern hemispheric monsoon index actually increases, but here in this case, all of them decrease because uniformly decreasing the global mean AOD, right? So we just wanted to see, this result is of course only for the monsoon region. I wouldn't use this for, let's say, extratropical precipitation or something like that. There may be other parameters involved in this. So we did the model comparison versus the estimate. There is a pretty nice, so these two parameters seems to be explaining the monsoon changes very nicely in the 2 minutes. Oh, great, okay. So I have only a couple of slides. So yeah, finally coming to this sensitivity of the hydrological cycle to the altitude of the aerosol. The reason I actually, for a long time, I wanted to look at this was, there was a paper in 2014 which actually said, even read the title here, it says weaken the tropical circulation and reduce the precipitation in response to geoengineering. So, but in this paper, quickly people pointed out, in this particular paper, the aerosol was actually put very close to the tropopause, so that will actually obviously lead to, the upper troposphere will warm more, that will increase the stability, and that could actually reduce the precipitation. So, but of course, this was, so there was no height-related sensitivity study in this, so we wanted to actually look at this problem. So we have a right now, we had a postdoc recently last year, Usha. So basically, she attacked this problem. So basically, we put aerosols, okay, so for illustration, simple illustration, I show only 2 heights. One is aerosols at 22 kilometer, same amount of aerosol, so nothing else is changed. So here, the aerosol is at 16 kilometer. I'll just quickly only tell the result here because there is not much time to explain this here. So if anybody is interested after this talk, we can maybe have a conversation. So basically, larger greenhouse effect. In this case, what happens is, when you reduce the height of the aerosol here, remember this stratosphere, lower troposphere, as you go down in height, the temperature actually goes down. As you go up, temperature increases. So this aerosol layer is placed in a background temperature of lower temperature. So lower temperature means the greenhouse effect is actually larger, right? Now, but what happens is, so obviously this will lead to suppression of precipitation. This larger greenhouse effect in this case will lead to larger suppression of precipitation. But interestingly, what happens is when the height of the aerosol is reduced, you actually also, the efficacy of aerosols is also reduced. So you basically get less cooling, right? So less cooling means less precipitation reduction. But because of that fast process here, the precipitation reduction is larger. So you basically get kind of, these two effects offset each other. And yeah, this paper right now, it's a work in progress. But anyway, I'll just show you the results for India. So obviously, so okay, so this is 22 kilometer, 18 kilometer, and 16 kilometer. So what I show is only the aerosol effect. So you don't really see big difference. I think I was really looking, if the aerosols are put in lower stratosphere, some kind of catastrophe is going to happen. No, it's not so. So basically, because these two effects offset each other. So the conclusion right now is the aerosol, induced precipitation change is less sensitive to the height of the aerosol. And I think, one new paper, I just want to highlight this. Again, a qualitative science here. So this is from a paper, McGraw. It just appeared recently. So they were looking at the Toba Toba eruption, which injected apparently tons and tons of material into the stratosphere, right? So they actually say that if you put too much aerosol into the stratosphere, the aerosols could actually clump together, and when the particle sizes are really big, they could actually have the greenhouse effect because the aerosols also absorb IR radiation. So that effect could actually be more than the reflective, the solar effect. So this is basically for the Pinatubo case. So in this case, what happens is, in this case also, I'm sure there was an IR effect where the stratosphere got warmed and all that, but the cooling dominated. So so the main point is if the particles are too small, the scattering efficiency is very good. So it will lead to cooling. But if the net result of everything after all the microphysics and everything, if the particles are big, then you could actually end up with a warming. So I'll just quickly, again, these three messages I have already shown. All right, so I won't read it again. Okay, so now what is the way forward? I think the simple message is, yes, we need to do more research because many of these things where I'll tell you, were not clear even 10 years back. For instance, the first paper in 2008 by Alan Roebuck, he claimed, monsoon will be devastated by if you do solar geoengineering. But I think we are learning slowly, how, if you do, what are the precautions you should do, you should take. And basically, we are learning a lot of details about how the altitude will affect, et cetera, et cetera. So these are some of the things, in fact, probably are needed. This one, we have not looked at how monsoon variability will be altered. Yeah, we need to also, of course, look at these things, whatever the simple facts I have stated here, we need to assess in multiple models. That would help to assess the uncertainty and all that. And also, there could be a broad range of results looking at, different optical properties of these aerosols, which corresponds to different materials. And at the end, in fact, over the last 7 or 8 years, we have been looking at these kind of problems using this simple modeling framework. So if anyone is interested, more detailed discussion of this, you can go to this poster here. Usha, she is our postdoc. Yeah, she is basically ready to explain all the results that are presented here in much more detail. Yeah, with that, I'll stop. Yeah.
Thank you, Dr. Bala. Very nice presentation, and also very interesting to bring the topic, the discussion on geoengineering in a place where we can, as scientists, understand the limitation, the pros and cons, and understand. There's a lot of, it's a very hot topic and controversial topic, and I think it's important to see that researchers throughout the world also are looking at these problems. Not only initially it was very much over the US and maybe in Europe, and the fact that in India and even in China, I think it's very, very interesting. So we have time for questions.
Thank you, Bala. That was a very nice talk. So you told the altitude, if you increase, it is not going to affect the precipitation.
No. Yeah, so it doesn't matter whether you put in, let's say, aerosol at 20 kilometer or 18 kilometer or, I think our idea was we wanted to really, why we did this, for some reason, suppose you put the aerosols around 16 kilometer, which is where the tropical tropopause is, right? So you are very close to the tropopause. So what's going to happen is you are going to actually do the heating, stratospheric heating near that 16 kilometer. So what's going to happen is then your stratospheric water vapor would increase. I have not actually shown the work here. So we have actually looked at the temperature effect of putting aerosols at different altitudes. So for the global mean surface temperature, there is huge sensitivity to the height of the aerosol. If you put the aerosols at, let's say, 16 kilometer, so you increase actually stratospheric water vapor because you are heating around 16 kilometer, so that water vapor gets into that. So you basically reduce the effective aerosol forcing, so which leads to less surface temperature change.
Yeah, surface temperature is very sensitive to the height of the
Height, yes. I have a slide, but I just, because of the time limitation.
There is another paper that said that in a globally warming environment,
yeah,
there is more buoyancy and this height of the tropopause also increases.
Yes.
It will have stronger cooling effect on the surface.
Yeah, well.
Volcanic effect.
Okay, yeah.
Thank you.
Thanks for the nice talk, sir. Yeah. So is there any zonal asymmetries in the sensitivity of the precipitation to the geoengineering?
Well, obviously it should be. We have not investigated. I showed you zonal mean, right? Why to aerosol? Even, greenhouse gas induced climate change. There are actually, for example, the simple example is Walker cell weakening, right? For global warming, I think there are a lot of papers on how we would actually get into a kind of El Nino pattern, the warming pattern, the climate change induced SST change. It's supposed to have a kind of pattern that is similar to El Nino pattern. So, yeah, I'm sure there will be, but we have not looked at the zonal asymmetry in the response in precipitation or temperature. So far, we have not looked at. I'm sure that is something, but yeah, I don't know, the problem could be complicated. But yeah, people have looked at Walker circulation changes. That could lead us some kind of clue where to look at that, yeah.
Thank you very much, sir.
Yeah.
In your first mechanism, what you showed, keeping aerosols at different latitudes.
Yeah.
Even though the mean does not show larger difference, but the spatial variability in the rainfall over Indian region is very large.
Spatial, yes, right. That's because are you talking about, let's say, northern hemisphere injection versus the southern hemisphere injection?
Yeah.
Yeah, that is really the main driving point for this presentation, that if you put the aerosols in the northern hemisphere, so the northern hemisphere basically preferentially cools, right? So
even when you're putting closer, right, closer to the equator.
Oh, okay.
Yeah, then the spatial variability over Indian region, the rainfall, it is showing only 8% or less than 8%.
Okay, you mean, okay, let's see. Are you talking about this one? No, not this. This one here?
No.
Well, that's for the different
latitudes.
Oh, okay. Yeah, I think this is over India, this is the one. And this is Arctic geoengineering. And this is the zonal mean precipitation change. And then, of course, I have for this idealized experiment.
Yeah, this one.
Where, you mean this one here?
No.
I think maybe you could continue the
discussion.
discussion.
Yeah, maybe we can discuss.
Nice
continue.
break.
Yeah.
So thank you again.
Okay, yeah.
Thank you. So my co-chair is having pity of me and my jet lag, so he's taking over.
Thank you, Joe. So next speaker is Dr. Heinhold from Tropos Leipzig, and his title of the talk is Stratospheric Smoke Injections from the 2019-20 Australian Bushfires, Impact on Radiation, Global Circulation, and Adjustment. Dr. Heinhold.
Already here. Okay. Yeah, perfect. Okay. So thank you very much. So my name is Bernd Heinold. I'm from the Leibniz Institute of Tropospheric Research in Leipzig, Germany. And as the name of our institute says, we have our particular focus on the troposphere, on tropospheric aerosol. But the recent increase in extreme fires with very high or very deep injections of plumes, of fire plumes, we have to push our ceiling a bit. And this one here is about the extreme 2019-2020 bushfires in Australia. Just to bring memory back, maybe I'm showing this impressive photo here of the bushfires that have become known as the Black Summer bushfires because they were really extreme. One of the strongest on recent records, and they were caused by an exceptional drought over Australia. And this drought was, of course, linked to a specific setting of the Indian Ocean dipole and ENSO, a strong positive index or and phase in both indices. And and the results were those fires, and that produced massive amounts of smoke that was then advected from the southeastern coast of Australia across the Pacific and eventually just around the globe. And the transport of this biomass burning aerosol was very much driven by pyroconvection, so convective plumes driven by the heat of the fire. And you can see here in the Calypso imagery that these pyroconvective towers injected the biomass burning aerosol, the smoke, directly into the lower stratosphere. And by chance, the Tropos Institute also had a LiDAR here in southern America, at the southern tip of Chile. And there we also could nicely see this stratospheric smoke plume. And so in the end, more than 2 teragrams of smoke were injected within a couple of days in the stratosphere, where it stayed for more than 1 year, actually. And this meant significant or considerable disturbance, of course, to the radiation budget in the southern hemisphere. As you can see, the smoke just spread just around the globe in the southern hemisphere. And Corin et al. Put this into a context here in terms of AOD, so that the impact of these Black Summer wildfire smoke was comparable to the disturbances by strong volcanic eruptions. So quite impressive. And that was the reason why we thought we should take our global aerosol climate model and see what the effects for the radiation and the global circulations are. And here we use the Eckham-Hammertz model. It's developed in the Hammertz community. It's also used here at the IITM by Sovana Fatnavis, for example, also to do some global aerosol studies. And we run a reference, a 20-year reference run, and then we also did some sensitivity studies, used the Copernicus fire data to prescribe the emissions, and also did some ensemble runs for sensitivity studies. And the most challenging part, of course, of fire simulations is the injection still. So to get the injection height right. And so here we used as a standard setup, or the default, that most of the smoke is just emitted into the planetary boundary layer. But then in a couple of other sensitivity studies, we just toyed around a bit. And the results I'm going to show here are from a simulation where we just put, and this turned out to be the best assumption, where we just put the smoke into a layer above the tropopause, but only for the couple of days here, for these 4 days in 2019 and 2020. And this really made the game, obviously. So as you can see, we evaluated this with our LiDAR observations here in Chile, and you can see only with this modified injection height, we could actually match the observations, while we could not with the standard setup, with the default setup. And what you also see here is this gradual increase in the height of the plume core, and we could show with the model that this is actually So you can see it here in the LiDAR observations, the plume rising, but also in the model results. And we could show with the model that this continuous rising of the plume was due to radiative self-lofting. So the air is heated because of the solar absorption, and then this warm air bubble continues rising. And then we quantified the instantaneous solar radiative forcing, and that was quite impressive. So it's in the range of the global average instantaneous top of atmospheric forcing of anthropogenic black carbon. And at the surface, we saw a quite a strong dimming effect comparable to volcanic eruption. But of course, the instantaneous radiative forcing is only a part of the story. And that's why in a follow-up study, we also looked at effective radiative forcing values of the smoke aerosol. So cloud effects are included, but also rapid atmospheric adjustments. And yeah, you see this here for different wavelengths, short wave, long wave, and the net effect. And yeah, when you compare here the all-sky forcings with the cloud effects solely, then you see that, in fact, the clouds here have a huge impact, a significant impact on the effective radiative forcing at top of atmosphere that really make them positive. And that was a bit in contradiction to many other studies that came out by that time that only considered clear sky conditions. But of course, in the southern hemisphere, in the mid and high latitudes of the southern hemisphere, we had a lot of clouds. And also in Antarctica, we have these bright surfaces covered with ice and clouds, and that also turned it to the positive values. But there are also rapid adjustments in the atmosphere that you can also see here that also balance this initially very strong positive forcing. And then, of course, we thought this would have an impact on the global circulation, on the stratospheric circulation in particular. So here we looked at the residual circulation, so stream functions for the stratosphere, but also looked at the adiabatic heating in the stratosphere just to see what the impact is. And what you might guess is, of course, that the wildfire smoke causes a strong local warming, but not only local, but also, of course, a non-local warming. And this is, in the first instance, of course, compensated by long-wave cooling. But there are other effects that play a role, and that are those stratospheric adjustments. Yeah, so the point is here that we have less adiabatic heating needed here in the residual circulation because of this local warming. And as a result of this, we also see then a weakening of the southern hemispheric stratospheric circulation. You can see this here. So by the way, the lines are the stream lines for the reference run, and the colors indicate the change or the impact of the fires. And in this case, of course, as we are in the southern hemisphere, red colors mean weakening of the circulation. That's what happens in the southern hemisphere. Here we have this weakening, but for the tropics and also for the northern hemisphere, you see that the circulation is slightly strengthened, and that means that energy is transferred from the southern to the northern hemisphere, and that means that this relatively local, even though it was a very strong and extreme event, that this is then transferred also to the northern part of the globe. And you can see this also here in the adiabatic heating. You see this heating caused by the fires in the northern part of the globe. So quite interesting. And this, of course, had an impact on the hydrological cycle. Here you see different types of hydrological parameters, precipitation, liquid and ice water paths for different sensitivity studies of a different strengths of emission. And yeah, the signal is relatively clear for all these sensitivity studies here that we performed. We see a decrease, even so it's a slight decrease in the cirrus cloud cover, but we also see reductions in surface precipitation and evaporation, ice water paths. And yeah, so this is quite interesting, even though it's complex, and I guess it still needs further investigation. So, and with this, I would already like to come to my conclusions. We have seen that those extreme fires in Australia considerably perturb the southern hemisphere aerosol load and also the radiative balance there. And the interesting outcome was that, other than expected, we see by these interactions, interconnections, we see a global impact, and it would be interesting also to have maybe a closer look at the Indian monsoon, also what the effect were there. We haven't done that yet. But for sure, I think we can say that with the anticipated increase in those extreme wildfires that really reach higher with their plumes, we have to make our climate models fit for such events, because this is something we would need to consider to get the energy budget right in our models. Yeah, and that's all from my side for the moment. Thank you very much for your attention. I'm happy to take questions.
Thank you. In the interest of time, we'll keep the questions for the break. Let's welcome the next speaker, Dr. S. Sridharan. He's going to talk about influence of meta-volcanic eruptions on the stratospheric vapor pressure.
That is better. No, not this one. Not this one. This one. No, this is full screen. Okay. Thank you very much. Good evening to all of you. The title of my talk is Influence of Meropic Volcanic Eruption on the Stratospheric Water Vapor. Sandhya and myself. Sandhya is currently working in NCMWR of New Delhi. So, stratospheric water vapor, why it is important? Because it is important for two reasons. One is a greenhouse gas, and the other one is second one is it plays a major role in ozone chemistry, particularly in delaying the ozone recovery. In spite of its low abundance, its radiative effects are very significant. So there are different pathways for the stratospheric entry of the water vapor. One is the convection and mean transport circulation in the tropics. That is vertical upwelling and then meridional circulation and then downwelling back to tropical region in the lower atmosphere. So the other one is the rapid transport across the isotropic level. So oxidation of methane also can cause water vapor in the stratosphere, but it is more prominent only in the upper stratosphere. So water vapor can directly enter into the lower stratosphere through the tropical tropopause, where the tropical tropopause temperature basically determines how much water vapor should enter into the stratosphere. So in addition to mainly the tropical tropopause, in addition to this quasi-biennial oscillation, El Nino southern oscillation, and brew adsorption circulation. All three can contribute significantly to the water vapor entry into the stratosphere by changing the tropopause temperature mostly. And then volcanic eruptions also can significantly influence the stratospheric water vapor amount. So if you look at the seasonal variation of the water vapor, during January to May, the value will be around 3 to 3.5 ppmv, and it slowly increases from May onwards to what is it? And then maximum it reaches around August, September, where the value will be around more than 6 ppmv, and then followed by a decrease. So seasonal variation of water vapor in the stratosphere, lower stratosphere, follows the seasonal variation of the tropical tropopause. That is very clear. So it also exhibits a considerable interannual variability, year-to-year variability. If you see anomaly, if you take water vapor anomaly, there will be a negative anomaly in some years and a positive anomaly in some years. Particularly, we are interested in the positive anomaly that took place, that was there during 2010-11 winter. And then what caused this positive anomaly we are discussing. And then there are other positive anomalies also. This 2016 is due to El Nino and many other things are there. What causes this particular positive anomaly, positive water vapor anomaly, that we are going to discuss. So we know the water vapor variability mostly influenced by many factors. One is the tropical tropopause temperature, and then quasi-biennial oscillation, El Nino southern oscillation, and brew adsorption circulation, etc. So it is as expected, the tropical tropopause temperature is positive during this time. But GCMW general circulation model results show that water vapor can increase by 10% during the El Nino events. By increasing the tropical tropopause temperature. So, but if you see multivariate El Nino index, that means if it is positive, that means El Nino. Negative means La Nina. During, though it is positive during January to February 2010, but winter time, that means 2010-11 winter time, it becomes negative. So La Nina was prevailing over time, during the two for about 2 years, from 2010 May to 2012 May. That means it is not caused by ENSO, El Nino southern oscillation, that is very clear. So QBO also can modulate stratospheric water vapor entry into the stratosphere by its secondary meridional circulation. If you see, when the eastward winds are descending, that means QBO has alternating westward wind, eastward wind, eastward wind alternately descending. No, so when eastward winds are descending, so we can expect tropopause temperature will be warm. So that can allow more water vapor entry into the stratosphere. But during this time, if you see, there is not like this. So what is this? The winds are eastward throughout the stratosphere, not like when during the end of 2011, if you see, there are westward winds at the top and eastward winds at the bottom. There is a large shear that will enhance the meridional circulation. Here it is not the case, where the meridional circulation will be very weaker. So QBO also cannot, is not expected to cause this large positive anomaly in the stratosphere. So also when ENSO, warm ENSO and QBO are in phase, that means when there is an El Nino and eastward phase of QBO, then we can expect tropopause temperature to be warmer and it will allow more water vapor entry into the stratosphere. But here we have just seen that La Nina was prevailing over that time. So eastward phase is not there. If La Nina is there, then westward phase should be there. That is also not there. So both QBO and El Nino could not cause this large positive water vapor anomaly. So BDC, brew adsorption circulation, can cause because it can transport water vapor, tropical water vapor into the extratropical region. So we expect brew adsorption circulation. If it is more, then we can expect anti-correlation between brew adsorption circulation and tropical water vapor. how to prove that? Because it is maintained with the planetary wave activity. We used eddy heat flux averaged over 45 to 75 degree north and 45 degrees to 75 degrees south, averaged for these latitudes, as a proxy for the fluid absence circulation. And we have plotted over here. That shows clearly the BTC is more during the winter of 2010-11. That means when BTC is more, we normally expect low water vapor, because there will be the water vapor, whatever it is there in the tropical region, that will get transported to the high latitudes. So BTC also appears to play a minor role for the water vapor increase in during 2010-11. So when all these things are not there, so finally we consider maybe Marapi volcanic eruption. This is the period when major volcanic eruption occurred, because huge volcanic eruption can also inject large amount of water vapor into the stratosphere, like the one, the recent one, Hangatonga volcanic eruption. There is a direct injection of water vapor into the stratosphere. But it can also increase the tropopause temperature indirectly. It can increase the tropopause temperature, and thereby it will allow more water vapor into the stratosphere. That is also possible. In this case, a major volcanic eruption occurred during 26 October to 12 November 2010. So large eruption day is 5th November 2010. So water vapor is one of the principal components that got ejected into the stratosphere during volcanic eruption, followed by sulfur dioxide. But in the present case, water vapor by volcanic eruption did not happen, because we could observe water vapor increase only during the first week of December, whereas the Marapi volcanic eruption occurred in November, October to November. So it is not the direct injection, it is indirectly through increase in the tropopause temperature. So if we see the SO2 vertical column by OMI data, that clearly shows the injection of sulfur dioxide, SO2, over Indonesian sector. And then there is a spread of ash clouds from 110 degree, where it occurred, to 90 degree, even 90 degree. And also the Calypso observation, 532 nanometer total attenuated backscatter on 5th November, where the major volcanic eruption occurred. That also shows the presence of an aerosol layer around 17 kilometer and an aerosol cluster around 15 kilometer. So, and then later time, maybe for about a week also, SO2 vertical column shows further spread of aerosols. SO2 to the eastern, western longitudes for about 60 degree east also it got spread. So, once it gets ejected, once SO2 got ejected into the stratosphere, the chemical reactions will follow. That will form an aerosol layer that will persist for about a long time. Our Me LiDAR observation, we have Me LiDAR at Gadangi. The observations during December, NRL Gadangi, during December, January 2010, that clearly shows the presence of aerosol layer around 17 to 18 kilometers close to tropopause region. That is persisting for about 1 month, a very long-lasting aerosol layer. Very rarely we observe this type of event. So this aerosol layer formed during volcanic eruption can lead to stratospheric warming by absorption of solar radiation, and tropospheric cooling by reflection of solar radiation back to space. So that's what we observed here. We have seen the MLS temperature anomaly over 50 degrees south to 50 degrees north, over 60 degrees to 110 degrees east. That clearly shows the solid lines are mostly stratosphere, and then dashed lines are upper troposphere. And that one is lower stratosphere. Solid line is lower stratosphere, dashed line is upper troposphere. That clearly shows a positive anomaly in the lower stratosphere and negative anomaly in the upper troposphere. That means there is a cooling in the upper troposphere, warming in the lower stratosphere. That clearly indicates the heating is due to this aerosol layer.
I request you to wrap up.
Yeah. Earlier, this volcanic eruption can modify the thermal structure. So there will be a large cooling in the upper, Free and Angel in 2002, they published a paper. There will be a large cooling in the upper troposphere after eruption they have seen, not at the surface, only in the upper troposphere, and the lower stratosphere there is a warming. So different volcanic eruptions, affect the thermal structure in a different way. The transfer from cooling to warming occur at a different pressure levels. One at 100 hectopascal, it may happen at 200 hectopascal, it may happen at 300 hectopascal for different volcanic eruption. But in the case of Merapi volcanic eruption, it occurred at the 100 hectopascal. So we conclude that the positive anomaly of water vapor in the stratosphere is attributed to Merapi volcanic eruption. This is a summary. The message is this: the positive anomaly of SW water vapor in the Merapi eruption is attributed to the Merapi volcanic eruption. The role of other possible sources, for example, QBO, ENSO, BDC, CH4, appears to be minor. Thank you.
Thank you very much. We can save the questions for the break, and let's go with the next speaker. So we have the next speaker, Dr. B.L. Madhavan from NARL. He's going to talk about stratospheric aerosol characteristics during the volcanic eruptions using the SAGE-3 ISS observations. Thank you.
Take this particular work is that existing surface-based or satellite-based LIDARs or in-situ observation techniques have limitations of the number of wavelengths at which the measurements are available. So in this context, OMPS LP, which is a limb profiler based measurements, and SAGE-3 onboard ISS provides a multi-wavelength aerosol extinction profiles. So we use occultation instruments that provide more reliable, accurate information of this aerosol extinction coefficient profiles in this study. And earlier for SAGE-2, there were attempts to infer the size distribution, but for SAGE-3, there were no such an attempt. So we tried to develop an inversion algorithm to retrieve the aerosol size distribution information from this SAGE-3 extinction profiles. So these are important because for modeling of radiative forcing of aerosols, size distribution is an important parameter. And to evaluate the aerosol effects on ozone due to heterogeneity of the chemistry, it's also important to understand the size distribution. So for this, we have taken Ambe eruption because this is the onset of a series of several stronger and record-breaking moderate and large eruptions. Before that, there was a period when there were no eruptions that were available. So after the Ambe eruption is unique in terms of it has 2 times the eruption happened, one in April 2018, and again it erupted in July 2018. While in April 2018, only southern hemisphere was influenced, while in July 2018, it was transported to the northern hemisphere through Brewer-Dobson circulation. So then after Ambe eruption, there is a series of eruptions like Raikoke, Ulawun, and Honga Tonga were the ones that were there. So here in this study, what we did was we tried to segregate the global region into 5 different regions. So like northern hemisphere, southern hemisphere, global, and we have taken a latitudinal belt of 10 degree to 20 degree, which consists of this Ambe eruption location, and also 10 degree to 20 degree, where Gadanki also is present. And also we divided the time periods into 4 different time periods: pre-Ambe, when Canadian wildfires were there, and Ambe 1 and Ambe 2, and then post-Ambe periods. So the objectives of this present study includes presenting you the inversion method to infer the aerosol size distributions, then examine the spatial temporal variability of stratospheric KOD and size distributions, evaluate temporal evolution, growth and decay characteristics. Then finally, I will be showing the assessment of radiative impact of these Ambe eruptions. So the method actually takes the idea from the ground-based instrumentation. So it is like inversion technique that is applied for a sun photometer spectral AOD measurements, from where we derive the size distribution measurements. And also we take the hints from the previous methods that were adopted for SAGE 2. So we assume refractive index of stratospheric sulfate, and then we assume multimodal log normal size distributions, and optical properties of spherical properties are calculated using the ME theory. So there are some 8 wavelengths were considered in this. Though SAGE 3 has 9 wavelengths, we consider 8 wavelengths because the shorter the wavelength in the around 300 nanometers is mostly, it has largely systematic biases were present because of the large molecular scattering. So we ignore that particular wavelength. So we consider only 8 wavelengths here, and then we provide this radius range from 0.1 to 1 micrometer at different mode radii, and then parameter Ni is optimized to the measured scattering stratospheric AOD with the maximum likelihood method. So here we consider stratospheric AOD by integrating the aerosol extinction profile from tropopause altitude plus to 30 kilometers. So the retrieval assessment involves, on the left side, you see that there are 6 models that were provided by earlier for SAGE 2 by you. So the same models we were taking, and then we are trying to see the simulated versus retrieved or effective radius. So what we find here is that the model and the retrieved spectral AODs are almost comparable, and the size distributions, number size distributions in the middle, and here we can see that volume size distributions, we can see that there is a overestimation in the fine mode that has little influence on the effective radius that we derive here. So the effective radius between the retrieved and simulated were differing around difference between 0.03, which is around 15%, and size distribution particles with radius less than 0.2 microns was not retrieved accurately. So we see here that in number size distributions, we see that there's an overestimation by the retrieved things using our method was overestimated, fine mode. But when you see in the volume size distributions, they are almost comparable. So now coming to the spatial variability of these parameters, spectral stratospheric AOD in different regions, we see that there's a distinct spectral behavior of the stratospheric AOD was noticed. And in terms of the size distributions, we see that monomodal number size distributions appear to be similar with peaks around 0.12 microns. And the total number concentrations are different at each region at different periods. While you see in the volume size distributions, the bimodal and trimodal size distributions vary distinctly. So what we have also done is we try to make some sensitivity analysis by removing some of the wavelengths and see which of the ones are able to provide a realistic size distribution. And in that we notice that inclusion of 1544 nanometers and exclusion of 384 nanometer wavelength has tends to strongly modify the amplitude of the first principal mode and the shape of the second and third modes. So now coming to the growth and decay characteristics of this Mbe eruption, we clearly see that there's a steep increasing slope in the stratospheric AOD observed in the southern hemisphere during the Mbe 1 and Mbe 2 periods, which is around approximately 249 days. Although there is a similar increasing slope that was noticed for the stratospheric AOD in global and northern hemisphere, they have a different starting and ending days in both regions, indicating that there is a time lag with respect to the dispersion from southern hemisphere to the northern hemisphere. So another aspect is rate of decrease of this stratospheric AOD is more drastic in the northern hemisphere than in the globally, with different starting days and same ending days. So there's also another aspect you can see from this angstrom exponent, wherein you can see that there's a dominance of the small sulfate particles that were mostly prevalent during the Mbe periods. So which is like angstrom exponent greater than 1.5 indicates the dominance of small sulfate particles. So coming to the temporal characteristics, as you can see in the top, the stratospheric KOD corresponds to the latitudinal band depicted to similar patterns and as represented by their respective extended regions. And angstrom exponent values were lowest 0.6 and above during the post-Ambe periods, we can see here. And this is possibly because of the Reikoke eruption, which is largely associated with the larger ash particles. So here we see that the derived parameters, total number concentrations and effective radius, wherein we see that strong fluctuations in the total number concentrations were seen. And the possible reasons we listed that the temporal variation in the angstrom exponent and retrieval algorithm might have resulted in this temporal variation and overestimation of the fine mode. While the effective radius remains stable with no significant change during the pre-Ambe and Ambe periods here, possible and Ambe periods in all regions, possibly because the microphysical changes associated with the Ambe plume were not evidently visible in the derived effective radius obtained from the number size distributions of spectral stratospheric KOD corresponding to altitude and range, because we have integrated. So that might be one reason wherein this might not be changing evidently the effective radius.
Dr. Madhavan,
Yes,
please wrap up here.
Last but one slide. So we have consolidated the radiative impacts of these different moderate eruptions in the periods where we see that Ambe eruption, though the estimated sulfur dioxide loading is very less, we can still see that the top of the atmosphere estimated radiative forcing was very large compared to the ones wherein the larger sulfur dioxide loadings were all present during other eruptions. So we consider there's a strong climate impact was associated with this Ambe eruption for the year 2018. And coming to the last slide, we have segregated the conclusions in terms of our retrieval method on the left side, and on the right side by the direct observations that we have obtained from the stage 2. So that there's a scope that our retrieval algorithm needs to be tested with observations that were available from in situ, wherein number size distribution and all these things, how well our retrieval algorithm can improvise in future. We will be doing that for other eruptions. So with this, I will conclude my talk.
Thank you very much. We'll save the questions for the break. We have the last speaker for this session, Dr. Basha. So he will be talking about disturbing the middle stratospheric balance, the enduring impact of Honatonga volcanic eruptions.
Okay, welcome, Professor Palmer. So I'll quickly give his brief introduction. Professor Timothy Palmer is a Royal Society Research Professor Emeritus at Oxford University. He was the division head at ECMWF, where he pioneered and led the introduction of operational ensemble prediction systems on medium-range, monthly, and seasonal mesoscales. He has won the Charney and the Rossby medals of the American Meteorological Society, the Royal Astronomical Society's gold medal for geophysics, the Institute of Physics Direct Gold Medal for Theoretical Physics, and the 2023 IMO Prize of the World Meteorological Organization. As well as being a fellow of the Royal Society, he is an international member of the US National Academy of Sciences. So I request our director, Professor Dr. R. Krishnan, to kindly chair the session.
Welcome, Tim. Looking forward to your talk. You can make it. You can start your presentation.
Thank you very much. Let me get my slides hopefully share my slides. Okay. Can I check that you can hear me and that you can see my slides? Is that okay? I can't hear anything, but put your thumb up. Thumb up. Okay, great. Fantastic. Okay, so I'll start talking, and hopefully, if there's a problem, let me know. Okay, great. Thank you. So I'm going to give a talk which is partly historical and partly making predictions 1 or 2 days ahead with regional models. But by the 1960s, people were asking, well, if we could develop global models, how far ahead could we predict in practice? And people like Leith and Mintz and Smagorinsky, and Smagorinsky won the IMO medal. There's some very illustrious names that have won this medal in the past. So Smagorinsky won it in 1974. He was director of GFDL. But a group of people did experiments, and this was done by looking at what might be called identical twin experiments, where you just have very slightly different initial conditions consistent with initial error, and see how far ahead there is some kind of predictability in the forecast. And the idea arose in the 1960s that limit was around 2 weeks. And this is often called the limit of deterministic predictability. And it's a phrase which I think is a bit unfortunate, because I think it's been misunderstood. What it means is that on average, with a deterministic model, there is some level of predictability out to about 2 weeks into the future. In any case, these models were the basis for establishing ECMWF, which started in 1975, but was preceded by these basic experiments from Leith, Mintz, and Smagorinsky. Just to give a little bit of my own history, I joined the UK Met Office in the late 1970s after a PhD in theoretical physics. My initial work was actually in the stratosphere, dynamics of sudden warmings, and with Michael McIntyre from Cambridge, we discovered the world's largest breaking waves. These were Rossby waves in the stratosphere. But the way the Met Office works, I was posted to a new branch in the early 1980s that was focused on long-range forecasting. So this is month to seasonal forecasting. And in those days, the forecasts were made with what then were called empirical statistical models. Today, we would call them data-driven models. They would basically take past data and try to construct prediction models based on the correlations and so on that exist, for example, between sea surface temperatures and atmospheric variability. Now, necessarily, these monthly to seasonal forecasts were probabilistic. The statistical empirical models would produce probabilities, for example, probabilities of different types of weather regimes over Europe. And my job was to try to introduce dynamical models, which had been successful in weather forecasting, onto this long-range timescale. And the first problem really was that the models were deterministic, and yet the statistical empirical models were probabilistic. And if we want to somehow merge together dynamical models and statistical models, then the dynamical models somehow have to be used in a way that they would also produce probability forecasts. And we realized the way to do that was using to develop ensembles of forecasts. So to run the model with multiple times with slightly different initial conditions. And with my colleague James Murphy, we introduced an operational, so real-time ensemble forecasting system, which could be combined with the statistical empirical models to produce ensemble forecasts. And that was done. The first forecasts were done actually towards the end of 1985. This is a write-up in a Met Office journal called the Meteorological Magazine. So this was, I think, the first use of ensembles in operational meteorology. I want to say I was very strongly influenced and motivated, and somebody who was very much a mentor for me in this area was Jay Shukla, who I think at those days was at NASA, but he's now president of the IGES organization in George Mason University, and also an IMO winner in 2007. Now, I had, I'm going to call it a light bulb moment. I'm not sure it was, at the time I thought it was particularly profound, but in any case, let's call it a light bulb moment. That really we should be doing ensemble forecasting on all timescales, not just the monthly and seasonal, but also the medium range and even the short range. But I got a lot of pushback from colleagues about this, and the typical response was to quote these papers, for example, by Smagorinsky and others, that inside the limit of deterministic predictability of 2 weeks, then we should be trying to forecast deterministically. We don't need ensemble forecasts inside the limit of deterministic predictability. And I tried to find arguments to justify the idea that just because there is some deterministic predictability out to 2 weeks, on average, it doesn't mean that every forecast will be predictable out to 2 weeks. And I ended up, making a lot of use of Lorenz's idealized model, which shows very clearly if you have, if it shows very clearly that predictability is not like a constant. It's state dependent. It's variable. It varies from one initial condition to another, and this just shows how an ensemble of initial conditions representing points around that initial kind of circle. In fact, in some cases, they don't actually even grow at all. When you're on the top part of the attractor, it's so stable that the ring of points actually shrinks. But as you move down the attractor, then you get to more unstable situations. And the bottom one is where you hit a strong region of instability, and there the predictability is very small. So this was my argument for many years, that we were sort of being lulled into a false sense of security, thinking that we can make predictions out to 2 weeks on every single occasion. I think, again, most people's reaction to this was that this was such an idealized model, it maybe isn't particularly relevant to the real world. So again, some resistance to this idea. The kind of turning point, particularly in the UK, was a very famous storm which hit southern England in October 1987. And the then weather forecaster, in those days, the weather forecasters were employees of the Met Office. So he was basically representing the Met Office. And the evening before the storm happened, the evening weather forecast was for a fairly pleasant day, and maybe a little bit breezy, but certainly no warning of extreme weather. and yet literally hurricane force winds hit southern England and caused, incredible damage and some fatalities. And the BBC anchorman in the morning TV, the morning kind of news show, I remember this very distinctly, saying to the forecaster, well, you chaps were a fat lot of good last night. If you can't forecast the worst storms for several centuries 3 hours before they happen, what are you doing? And this led to enormous media stories criticizing the Met Office, and there were calls for John Horton, who was then the Director General of the Met Office, to resign. Well, we ran at ECMWF with colleagues, we ran retrospectively this October storm case from a couple of days before the storm hit the UK, running with very slightly different initial conditions. And you can see there the stamp maps, what we call the stamp maps of the ensemble. And I have to say, at this range, this is as unstable and as unpredictable as you can almost imagine. I don't think I've ever seen a more unstable situation. So you literally do have forecasts where you would predict a fairly pleasant day, slightly breezy, but nothing very serious, to ones where there was an intense low pressure system coming in. Now, the question then arises, what do you do with this information? How do you sort of synthesize it? And again, in ensemble prediction, and it's something that still happens to this very day, it's something I try to argue against. People just try and reduce all this information down to a single ensemble mean deterministic forecast. They average together all the 50 forecasts. And indeed, you can show, and I think Chuck Leith showed this originally, that the root mean square error of an ensemble mean forecast will be lower than the typical deterministic forecast. But in a way, that is a misleading result, because when you average the 50 forecasts together, you just get something that's fairly smooth. And it certainly doesn't warn you that there is a risk of some very intense weather system. So making use of the work that I had done with James Murphy on the monthly timescale, where we were forced to use probabilities because that's what the statistical models used, then instead we created these probability maps. And the one on the right shows the probability of hurricane force winds on that morning of October 16th, 1987. And the probabilities are around 30 to 40%, which is not, is not 80 or 90%. But on the other hand, if you think about the a priori probability of a hurricane in southern England, which is virtually identically zero, 30 or 40% indicates, a million times at least the prior probability of such an event. And of course, this can be used to influence decision-making. At the very least, I would suggest people who had cars parked under trees, with a 30 or 40% chance of hurricane force winds would be well advised to move them somewhere safer. If you were planning a trip across the channel that morning, you would perhaps do well not perhaps to go out. And there are certain things, that you would do. So I'll come on to this in a second. Anyway, the 1987 event was transformational. I mean, nature had spoken. This was clearly a situation where the deterministic forecast completely failed. And it was a perfect example of this idea in Lorentz's model that there are exceptionally unpredictable states. And we need to know those ahead of time. So ECMWF, I led a team which moved full speed ahead to produce an operational ensemble forecast system in the medium range. And in parallel, Yehenia Kalne at NCEP was doing the same. And, you know, this was the era where we discussed different ideas for creating initial perturbations, what was called the singular vector versus breeding vector wars. I use the word wars in, you know, somewhat jokingly, but there was some kind of rivalry about who had the better method for producing an ensemble. But the point really is, the important point is that both our systems went operational pretty much actually at the same time towards the end of 1992. And I think it's fair to say that numerical weather prediction has not looked back since then. It's become a central part of operational activities. And in fact, I want to give an example of this for tropical cyclone or hurricane prediction. So here are three ensemble tracks, if you like, of, on the top, a tropical cyclone that with a very high probability is forecast to hit Bangladesh in about a week's time. The middle one is I call semi-predictable. It's the famous Hurricane Katrina, which hit New Orleans. And you can see at this range of a week, it's not at all certain where the hurricane will go and where it'll hit land, or indeed whether it'll just track up the East Coast. And then the bottom one is one that had no impact really at all, except, you know, you can see even the direction, whether it goes towards the east or towards the west, is profoundly uncertain. I think one of the, what for me is very exciting developments out of all this is the move of humanitarian agencies and disaster relief agencies to finally be able to use forecasts for taking action ahead of time. And the basic, if you like, philosophy behind this is that they can estimate beforehand what is a kind of a reasonable probability threshold for a severe event, above which, a forecast probability above which it makes economic sense to take precautionary or anticipatory, they call it, action, to send in medicine and food and shelter and water and so on. And when I say economic, you know, so that they're not acting every time there's the smallest probability, because then they'll just run out of resources very, very quickly. But on the other hand, they're not just waiting for a sort of 100% probability, which means there would be lots of events that they would miss and people would suffer as a result. So the point is that they can determine ahead of time, based on their own, their budgets and so on, what is a probability threshold above which precautionary or anticipatory action is taken. And the point is that ensembles provide this. You know, for example, I would imagine that something like Cyclone Cider at that range would probably pass the probability threshold, and that the agencies would probably start to move medicines and food and warn people to move off very low-lying islands and so on. But with Katrina, it's much more difficult. I think at that range, the probability, for example, of it hitting New Orleans is sufficiently small that it would be, it would be foolish to put masses of resources into, say, just supporting New Orleans. So obviously the thing to do then would be to wait a couple of days, and indeed by 5 days, it was much clearer that the hurricane would be indeed going across the Gulf of Mexico. I want to say something because I'll come back to this. This is kind of an important slide. I mentioned about the initial perturbations and the singular vectors and breeding vectors and so on. But that's actually only one part of the ensemble system. And the other part is how you represent model uncertainty. And at ECMWF, we developed, with colleagues Roberto Buizza and Martin Miller, we developed a stochastic parameterization scheme. I argued back in the 90s that parameterization should not be thought of as deterministic representations of subgrid processes, but should be stochastic. And so the ECMWF, and I think nowadays most ensemble systems on the weather timescales at least, use these types of stochastic parameterizations where there's random numbers in the model. So even though the equations of motion at the level of the mathematics may not be are deterministic, nevertheless at the level of the computational representation, they have stochastic terms. And I want to show this result very briefly, which is a paper by Linus Magnusson and colleagues. And because over the years, there has been two different approaches to representing model uncertainty. One is indeed the stochastic scheme that I mentioned. The other is to try to use multiple models, to try to get model diversity by taking advantage of the fact that there are multiple models in the world. For example, in the medium range, we have global models from ECMWF, from Métier France, from the Met Office, from the Canadian Met Service, from the German Weather Service, from the Japanese, and so on. And what Linus Magnusson did was to try to see whether which gave, if you like, a better representation of model uncertainty with the stochastic approach in one model or the multi-model, deterministic multi-model approach. And the answer is quite interesting. The bottom, the green and the blue lines, show that in the extratropics, it's pretty much an even tie. They're very similar in terms of the spread generated by the ensemble. In the tropics, on the other hand, the stochastic physics, in fact, does better. It generates more spread compared with the multi-model. So I'm going to come back to that because this is an important point for me. There's also the issue, by the way, that adding noise can help reduce systematic errors. This is an interesting diagram from an ex-student of mine, Josh Dorrington, who showed that adding stochasticity to the Lorentz model can make the regimes persist much longer than they would deterministically. Okay, well, we get now to pretty much the present day. And I have to say something happened which I would not have anticipated. So I mentioned to you that I first started working in a group where the forecasts were made with data-driven models. We called them we called them statistical empirical models in those days. But I would not have envisaged that one could do as well with data-driven models as with numerical weather prediction for the medium range. And a couple of years ago, there were some papers, for example, by Pangu Weather, which is a Chinese Huawei group, who showed that deterministic AI models could do as well as NWP. But I thought, well, they'll surely never do as well for the ensemble. And then just last year, the DeepMind group in London produced an ensemble forecast system based on diffusion AI models. And what we're looking at here are three sort of standard skill scores, where the 0 line is the ECMWF ensemble, and the blue line is the GenCast, is the AI system, and where it's negative, it's meaning that the GenCast is looking more skillful. Well, I'm not sort of particularly bothered by the ensemble mean one on the left, because as I mentioned, the ensemble mean is actually not a good indicator of usefulness, because you just end up with overly smooth forecasts. So I kind of discounted that. But it's also doing better if you look at the second and third ones in terms of some of the probability scores. Now, these are not like super large differences, but they are differences nevertheless, showing that the GenCast is doing pretty well. And indeed, this is a revolution in the way we do our science. This is a statement by the Chief AI Officer of the Met Office, whose name is Kirstine Dale. We're in the midst of a revolution in AI where the world's fastest growing deep technologies have the potential to rewrite the rules of entire industries, changing the way we live. And I think this is true in the meteorological sector because most of these advances, so I mentioned Pangu Weather came out of Huawei, which is a commercial organization, and DeepMind is very much a subsidiary of Google, which is a commercial organization. And one of the other big players at the moment is NVIDIA, again, another commercial organization. So it kind of raises the question, will end-to-end weather forecasts be provided by commercial providers in a few years? Do we need NWP? Is there a role for physics-based models at all in weather forecast systems of the future? Now, this has really interested me, and it raises the question, can we trust these AI systems? Now, one thing one often hears about in the literature, or at least certainly in what can I say, in promotional material, is that AI systems have somehow learned the equations of motion. We haven't coded them explicitly into their code, but they've had enough access to data and so on that they've really learned, for example, the Navier-Stokes or the laws of thermodynamics. And the question is that really true? I mean, have they learned the Navier-Stokes equations? So I have been, for many years, interested in an aspect of the Navier-Stokes equations, which I wrote about in 2014 and called it the real butterfly effect. I'll try to say what I mean by that. And in fact, I've written about it again in the very latest issue of Physics Today, which is the American Physics Society's kind of in-house magazine. What I call the real butterfly effect is something which comes out of Lorenz's, not his 63 paper, but his 69 paper in TELUS, where he's looking at the question of what is the predictability of a flow which has many scales of motion. And of course, in the atmosphere, turbulent atmosphere is an example of a fluid system with many scales of motion. And the point that Lorenz made was that the predictability of such systems may be fundamentally limited, and by a fixed horizon. And the reason why that is in his model is because as you go to smaller and smaller scales, the error doubling time gets shorter and shorter. So eventually, you add more scales, you don't improve your predictability at all. I sometimes put it, like a kind of a set of Russian dolls. And you can imagine, with a coarse resolution model, maybe you can predict ahead a week. And then you might say, well, let's add some more resolution. Well, okay, if I double the resolution, does that double the predictability time? And according to the theory that Lorenz discusses, and ultimately it's to do with the Kolmogorov scaling of turbulence, you don't double your predictability time. You get a reduced predictability time. And if you double the resolution again, you get another reduction in the predictability time. And when you sum all these things up to infinity, you don't get a divergence series, which would mean you'd have infinite predictability. You have something finite. Now, So I want to discuss, with that in mind, a rather, I think, fascinating paper by Seltz and Craig, which came out last year, basically asking this question of whether AI can simulate this butterfly effect, the real butterfly effect. And what I'm showing here is part of a figure where they went back to doing the sort of experiments that Smagorinsky and Leith and Mintz did back in the 60s, by looking at the growth of two integrations where they're perturbed by they're perturbed by an initial perturbation to the initial conditions, which is very small. And I need to say what I mean by very small. So what they did was they took a typical perturbation from the ensemble of four-dimensional variational data assimilations that are made every day now to initialize an ECMWF ensemble prediction. So they took one of these analysis perturbations and reduced its amplitude by a factor of 1,000. Now, the point about reducing it by a factor of 1,000 is that at the very small scales, let me back up a minute. If they had taken a perturbation that was identical to one of these analysis uncertainty perturbations, then the synoptic scale error would be small and would be growing. But as you got down towards the resolve scale of the model, the errors would be largely saturated. They were as large as they would ever be. And so with the full initial uncertainty, then the growth the growth of the perturbation is occurring mostly at the synoptic scales and maybe slightly subsynoptic scales. But by reducing the perturbation by a factor of 1,000, the small scales, the scales say on the order of let's say if the model had a resolution of 10 kilometers, we're talking perhaps of perturbations on the scale of 50 kilometers or so. These are no longer saturated. You've reduced the amplitude so much that those perturbations at 50 kilometers and 20 kilometers and 10 kilometers can grow. And in the Kolmogorov-Lorentz model, the growth rates for these very small scale perturbations is much larger than the synoptic scale perturbations. So they did two experiments, one with a low resolution, this is Seltz and Craig, with two models from German NWP model with low resolution and high resolution. And what I'm showing with those two dashed lines are how the differences in the pair of integrations increases with time. And what you can see is initially there are extremely large growth rates. The perturbations are growing very, very quickly because they're growing at these very subsynoptic scales. And then as the perturbations grow, they start to propagate up to the synoptic scales where the growth rates are smaller. And so you can see the growth rates sort of start to level off and they don't occur as quickly. Remember, this is a logarithmic scale on the y-axis. Now, the point about this is that the NWP models have been coded with the Navier-Stokes equations. So they know that the small scales grow quickly. But the AI models, all they know about is the growth of perturbations or initial uncertainties, which are basically at the synoptic and subsynoptic scales. They don't know directly from the data that the much smaller scales, the 20 kilometer scales, should grow faster. On the other hand, you could say, well, if they've learnt the Navier-Stokes equations, then they should know that. But what you can see from the bottom dashed line is that they fail completely to grow these small scales according to how they should grow according to Navier-Stokes. So the AI models have not learnt the Navier-Stokes equations at all. They have not learned this aspect of scale-dependent growth. So can high-res NWP models simulate what I call the real butterfly effect? Certainly yes. Can AI prediction models simulate the real butterfly effect? Well, so far the answer is no. It'll be interesting to see how this develops. So I want to finish with a few remarks about what I think all of this means. My own belief is that we can't trust pure AI to do the job of weather prediction for the reasons I'm mentioning, and that really the best way forward is to try to combine NWP and AI together. And I think that should be the role of NWP's, of National Weather Services in the future. Not to try to, outdo what NVIDIA and Google can do, but to make use of NWP, combine it with AI, and in that way do better. And at Oxford, we've been working a lot on this for the last few years, doing this combination of NWP and AI. And one way one could look at it is that we're trying to add AI to the NWP system to get a much finer resolution forecast than would be possible from the NWP alone. I mean, this is just an example where the truth we've been using radar, shows some kind of orographic features associated with the flow, which are kind of completely missing in the global forecast, which is just a resolution issue. And then we've got three sort of ensemble members from a generative adversarial network AI system, which has been combined with the NWP. And it's starting to pick up some of these orographic details. And I think, and certainly with the paper we wrote, Harris et al. Showed that the objective scores with the AI system is improved. And our belief actually is that this is will be a better way forward for National Met Services than using limited area models to do the downscaling. Because it's easy to run, large ensembles with these GAN models, and not only that, you can run them out to, to the full 14 days or more if you want. So there isn't the same restriction on computer time. So we're currently working with the Kenyan and Ethiopian Met Services to try to show how this type of hybrid, if you like, NWP AI scheme will work. But it does raise the important point that you have to train the AI on data. And if you want to get extreme rainfall, you have to train it on high quality data. For the UK, we had radar. For these other areas, without radar data, we have to rely on rain gauge data. So it is important, in developing these systems that we have access to the rain gauge data when it's available. Now, I want to come to, I'm almost done, but I want to come to what will certainly be a something that not everyone will agree with. But I think to be able to compete with the commercial forecast providers, the global NWP centers should be starting to think about pooling resources. And if physics-based models are to be competitive with just the pure AI models, we've got to work towards developing kilometer scale global NWP. And this would be combined with the AI methods that I talked about. And from a physics point of view, kilometer scale allows convection, orographic drag, ocean mixing to be partially resolved. Now, the standard argument against pooling resources and developing a single model is that we need model diversity. That's always been the standard counter argument. However, I would argue, and I'm quoting and I'm using that result from Magnuson et al. To show that it's far from clear to me that you need to maintain multiple models. Model uncertainty can be represented, in my view, better with stochastic parameterizations rather than rather ad hoc multi-model ensembles. So I showed that with the French, the German, the Canadian, the American, the so on models all combined in the tropics, they actually don't do as well as a single stochastically parameterized model. So I think this idea of multiple models we needing multiple models for diversity doesn't bear scientific scrutinization. And I think that the problem with it is, if we had infinite resources, of course, maybe it wouldn't matter, but we don't have infinite resources. And when human computing and financial resources are sort of channeled into individual models where the wheel is being reinvented several times over, then it's sort of holding us back in R&D, in my view. And this becomes critically important also for the climate change problem. CMIP models, have improved in resolution, but at the present rate of change, it'll be 2060 almost before we are down to a few kilometers in resolution. And I would argue it's too late for that. So again, if we believe in seamless prediction, which is an important, I think, principle, then an ability to pool resources both in weather forecasting will actually also have a big payback in terms of climate change as well. I've been part of a program called EVE, Earth Virtualization Engines, which Bjorn Stevens is leading, trying to move to that goal. I just thought it was interesting to note that even in the UK, which hasn't always been the best country in the world for international collaboration, a recent government review by Paul Nurse, who's he used to be president of the Royal Society, he's now director of the Crick Institute, so he's a Nobel Prize-winning molecular biologist. His report on strategic infrastructure or research investment says that there are research areas of global strategic importance where new multinationally funded institutes or international research infrastructures could be contemplated, an obvious example being an Institute of Climate Change, built on the EMBL model. The EMBL is the European Molecular Biology Lab, which of course is an area well known to Paul Nurse. Such institutes are powerful tools for multinational collaboration and bring great benefit, not only internationally, but also for the host nation. So I hope that countries around the world, and I'm sort of, India would be a wonderful example if they could, endorse this EVE concept and maybe become one of the hubs for EVE in that part of the world. This is an unashamed advertisement for my popular science book called The Primacy of Doubt, and I've talked about pretty much everything I've talked about, and a few more things to boot are discussed in this book. So if you are interested, please buy it. I think I read it out as an audio book, so you don't even have to read it. You can, if you can stand my voice and my accent, then you can listen to me reading it. Anyway, I think with that I shall stop sharing my screen, and thank you for your attention, and happy to take any questions. Thank you very much.
Yeah. Thank you, Professor Tim Palmer, for that brilliant talk. We really enjoyed. Hope we can have some interaction if there are questions. Yeah.
Any questions from audience? So you have given an unquestionable talk, Tim.
Well, that's fine.
But there should be some questions, definitely. Yeah.
This is Rolf Müller. I was at the Kigali meeting in something like half a year ago, and Bjorn Stevens introduced EVE. I'm sure he talked to you about that. But at this meeting, the EVE concept was criticized quite strongly as being too Western, Northern Hemisphere oriented, and putting concepts to places like Africa, in this case, that are perhaps not that what the people there want and need. And basically, I think the problem was not enough consultation of what is needed elsewhere rather than coming with a finished Eve concept. So I would be interested what you have to say on this.
Well, if you don't mind me saying, I think that's nonsense. You know, climate change and extreme weather are as much problems in Africa as they are in any country in the world. And I think a project like Eve can actually bring together scientists in ways which hitherto we've not managed. And I give you an example. I mentioned that you know, we are working here in Oxford actively with the Kenyan Met Service, the Ethiopian Met Service, and an organization called ICPAC also in Kenya, of doing precisely this idea of adding AI systems to the global ECMWF ensemble forecast system to produce forecasts, sorry, to produce forecasts which are extremely relevant. In fact, the whole point is to make them relevant to, you know, to farmers, to the government emergency services, and you know, and so on and so on, in these countries in Africa. And whilst it is true that, you know, the global north, if you like, historically has taken the lead in the development of NWP, this area of AI is completely different. And I would say actually most of the really big breakthroughs have come from, you know, what we traditionally call global south countries. So rather than, yeah, I would say, you know, this attempt to create a new paradigm for both weather and climate, which will combine the traditional physics-based models with AI, is ideally suited to international organizations where we actively collaborate with scientists from the global south and global north. So I can't understand. I wasn't in Kigali, but it makes no sense to me whatsoever, that type of criticism. It just makes absolutely no sense to me whatsoever.
Professor Tim Palmer, there are two questions on the chat box. Can we just read that?
Can you show the?
Yeah.
Can you read it?
Yeah. The first one, I have a question to be posed to Tim. Is it possible to do online? Question is, I want to know his views on how to go about solving specific issues like predicting clear air turbulence to promote aviation safety. How good or bad is AI, since NWP models are simply not able to predict that?
I mean, that's a really good question, because I mean, I don't know. I'm feeling like I may say things that are not. You know, there may be people in the audience who know more about this than I do, but of course, you know, just in the last few days, that there's been a lot of news about the aeroplane that encountered turbulence somewhere over the Bay of Bengal, was it, or somewhere, Myanmar, somewhere like that. And somebody died, and a lot of people were critically injured, and the plane, I think it was due to go to Singapore, ended up having to land in Bangkok or something. Now, absolutely, the turbulence is not predicted directly by the NWP model. My guess is that this, and this is where I'm speaking a little bit off the top of my head, my guess is that this must have been some kind of convectively forced gravity wave that maybe was just on the point of breaking when the plane ran through. So it kind of hit this incredible, downdraft of a breaking gravity wave forced by convection. Now, with models that can start to resolve convection, we probably won't be able to predict these gravity waves precisely, but an AI system, trained, if we have enough training data, and we have the convection output from the models, then the AI I would imagine, would give us a very plausible probability of, of a breaking gravity wave at that altitude where the planes are flying, and would therefore warn the pilots to avoid those regions. So again, I think that this is it's just this will be a really super interesting area of research. But my guess is this is exactly the type of thing where a combination of AI and NWP will do something that just is impossible with either AI or NWP by itself.
So, any more questions?
Yeah, there is a question.
Thank you. Hi, this is Peter Hitchcock speaking. Thanks, Tim, as always, for very insightful talk. I was wanting, or I was hoping you could say a little bit more about prospects for combining AI with the climate problem as opposed to the weather problem, where we have a lot less historical data to train on the climate problem, and in some sense we're going into something that's by definition unknown and out of sample. I think, I'm sure you think that there's still lots of prospects for using AI in this context, but I wonder if you could say something about approaches that you think are most promising for that longer range projection problem. Thanks.
Well, I have one specific interest in this area, which is perhaps a little bit different to what I've spoken about so far rather, which is that again, one of the criticisms which people might raise about Eve is that if you put all your computing resources into a kilometer scale model, then you're never going to be able to run large ensembles, of hundreds of members and things, which which you may need to get reliable probabilities. Now, my let's call it hope is that if we have what I would call a skeleton ensemble with a kilometer scale model, that we can actually generate synthetic ensemble members with AI trained on the model output. So I think one of the applications of AI will actually be in generating synthetic ensemble members to make good probabilistic forecasts. But one of the goals of Eve, this is just slightly more generally, one of the goals of Eve is that if you're an agronomist, and you've got some very specific questions about how certain crops will grow, it should, in principle, be possible to, almost to type your question in to a kind of ChatGPT type of interface, and that would then kind of create a kind of meta program which would say, okay, for that particular crop, we need to know about rainfall, wind, temperature, cloud cover, and go and retrieve the data from the Eve archive and put it back together in a form which tells the agronomist, well, the probability of getting good harvests from this particular crop is going to increase or decrease or whatever it is at a certain rate, or so in other words, the AI here would become an interface that currently is very painful, I think, for humans to do, but maybe much easier for AI systems to do, which will just make the whole enterprise much more user-friendly. So an agronomist or a health specialist worried about the growth of certain diseases, dengue or malaria or something, wouldn't have to sort of have expert knowledge about the meteorology, but could just go in and the AI would do the analysis and then do all the data retrieval and calculations. So those are two areas where, yeah, I think AI can be, super important in the climate field as well.
So, team, there are two last questions.
Yeah.
One by Mohan. Can you go ahead?
Hello, sir. This is Mohan from NCMRWF. Very nice informative talk, sir. So out of curiosity, I'm just asking, if you want to have an skillful ensemble prediction system, how many ensemble members, minimum ensemble members that one need? Like, is it 50 or can go on, or how to deal with that? Like, how many ensemble members?
Yeah, well, again, that's what I'm saying. I mean, one of the I mean, ECMWF, for, say, medium range, ECMWF produces 50 ensemble members. I mean, for most applications, 50 is a good number. But, I mean, I'll just give you an example of where it could be insufficient, which is, think about renewable energy, for example. Renewable energy is a combination of output from solar panels and wind turbines. Now, these are two very different meteorological variables, cloud cover on the one hand and wind strength on the other. But if you're an energy provider, you maybe don't care so much about what the meteorology is, but you do care that your renewables can provide enough energy. So you want to know, I mean, so a critical feature will be the probability of, let's say, high cloud cover and low wind together. And it's where you get these kind of, if you like, multivariate types of forecast variables where 50 starts to look perhaps slightly inadequate and maybe, 100 would be better. But again, I think that's where this idea of using AI to generate synthetic ensemble members will come into its own. So we don't have to, I think, going forward, we shouldn't feel that, the NWP system has to provide all the ensemble members. As long as it, and I don't know exactly what the right, what the answer is exactly, but my gut feeling is that the 50 members that ECMWF has is probably the right number. We don't want to perhaps reduce that. But we can certainly imagine situations where we can increase it at relatively little cost by using AI to generate synthetic ensemble members. And that's easy. That's easy to do. If an NWP, if a National Weather Service, wants large ensemble members of very high resolution, fine scale output, and it has an AI system to do the downscaling of the say of the global model ensemble, it's really not going to be very expensive to produce large ensembles with hundreds of members. That's going to be straightforward. So I think there's no great barriers, if you like, to adopting AI for AI. I do think, just speaking as a scientist, look, I've got no kind of, I'm not trying to make a political point here, but I just think that in the future, limited area models, I mean, they'll be useful in research, but I'm very skeptical that they will be useful in operations. And I think in the future, we'll find that AI will replace the limited area models. But the global models, I think, will continue to be important.
Thank you, sir.
Hi, Tim. This is Ramaswamy. Sitting here in India. So I have two questions, and perhaps these go beyond the NWP timescales. One is, the kilometer scale models. When one starts using them to, address some particular issues and questions, like the one that I'm kind of familiar with in the US is the Western US hydroclimate. And you run these models, and you still start discovering that the physics in the models needs as much attention as what you want to do with the resolution. And that's become, I guess, a nagging problem, because I think you don't get to the practical aspects till you solve the physics dicore convolved problem. And how do you see that as progressing? Because that seems like important in order to justify running kilometer scale models to especially people who fund us. The second question is perhaps more on the climate side, which is, when you start thinking about the physical system integrated with the increasingly biogeochemical aspects, ecosystem aspects, there's a level of understanding, scientific understanding, that has to probably prevail, much like, in the earlier days of coupled atmosphere-ocean models, when one had to sort of ask some fundamental questions. So, do you see kind of a place for a hierarchy of models leading up to kilometer scale, but maybe progressing gradually from, high resolution to ultra high resolution? Because I think unless we get that understanding, we're going to be tying ourselves in knots, I suppose, trying to understand both the physical system and the physical system coupled to the chemistry systems. Thanks, Tim.
Yeah, thanks, Ram. Nice to hear from you. Just on the last point, I mean, absolutely, I absolutely agree that we need hierarchies of models. I mean, there's no question about that. And I tried to argue that for years. My main argument for ensembles was based on the three-component Lorentz model. So that's the ultimate in hierarchical jumps, if you like. But yeah, I mean, I'm talking here about specifically about operational types of forecasting, and of course, Ram, you're 100% right that we need understanding, and of course, there are going to be problems, like paleoclimate problems, where we're never going to be able to run kilometer scale models, over paleo timescales for the foreseeable future. I do hope that the operational, if we do go down the road of operational kilometer scale modeling, it will really inform the whole parameterization problem, for the more traditional 100 kilometer or 50, whatever you want to call it, kilometer scale models, which will continue to be used and continue to play an important role in understanding, in doing counterfactual experiments, and in doing very long forecasts to understand, paleo variability. So this is not, this is not one versus the other. I mean, I have to say, I find some of this debate puzzling. When I was at ECMWF, I mean, nobody ever doubted that improving the resolution would improve the forecasts, and over the years, that's been very, very clear. It's just that I mean, I myself, I never argued against high resolution. I just said that we should be developing high resolution once we have ensembles. Otherwise, we put too much faith in just one integration. So yeah, I want to certainly, I'm absolutely not saying, like we need one model for everything. I'm just talking about what we need in operational research, where we're providing data to agronomists and health experts and people doing climate adaptation, spending large amounts of money on climate adaptation. So this is not, this is where the rubber hits the road, if you like. And it's important that we get our best possible results, or best possible models for that. On the other point, I mean, I do clearly, just going to 1 kilometer is not a panacea. It's not like everything immediately becomes sorted out. And you're right, we have to worry about how, cloud structures that aren't subcloud structures that aren't resolved get properly represented in these models. And I'm not under any illusion that that's a a straightforward problem. Except to say, I do think it has to be done in a stochastic way. I think we're kidding ourselves if we don't think that. But again, I come to the point that I think we would free up resources if we could treat this problem in a more pooled way. If we could share resources, then there'd be more people, more computer power to explore some of these difficult issues about the interplay between the resolved dynamics and the unresolved parametrized processes. But yeah, I mean, I'm not claiming this is easy, but it's just a necessary step. It's unfortunately, this is a little bit catch-22, that it's very hard to prove that this will work unless you have the resources to do sufficient experimentation. Just running a model once or twice by reducing the resolution to 1 kilometer is clearly not going to be good enough. But on the other hand, people want to see very clear results, before they will commit to investing, large amounts of money in this type of project. Well, when I say large, I don't mean large in an absolute sense, but relative sense. So it is a little bit catch-22, unfortunately, but I hope in the next year or so, I'm trying to organize a meeting at the Royal Society about a year from now, where I hope some of the first kind of demonstrator results will suggest at least we're moving in the right direction towards reducing some of the long-term biases that we have in these lower resolution models. But there's a bit of an act of faith in this, except in a way I do have faith in the laws of physics, and increasing resolution at the end of the day is about representing the laws of physics more accurately and more reliably.
Thank you, Professor Tim Palmer. So we come to an end here. Thanks a lot. We really enjoyed your talk.
Thank you very much. It's a great pleasure to talk to you all.
Yeah, it would have been nice if you had come here in person.
Next time.
Next, sure. Yeah.
Thank you.
Thank you. Thank you. So we come to the end of today's session. Any announcements?
Thank you, Dr. Krishnan, for chairing the session. We are sorry for cutting short the earlier session. We'll definitely accommodate and continue with it tomorrow morning. So for now, we'll break for tea and for the poster session. And for the poster session, that is put up adjacent to the Okay. We'll present the mementos to the speakers of the previous session. I invite Dr. Vernier to present the memento to the speakers. Dr. Krishnan. Dr. Simone. Dr. Bala. Dr. Heinold. Dr. S. Sridharan. Dr. B.L. Madhavan. Thank you, Dr. Vernier. Now we can proceed for the tea and coffee break and the poster session. The posters is put up I'm very sorry. I request Dr. Suvarna to present the memento to the chair. I request Dr. Krishnan to present the memento to the co-chair, Professor Tarun Gupta. Thank you, Dr. Krishnan. And the poster session, which is put up just next to this auditorium. Thank you all.